to the same topic. We cover the entire day. This session is chaired by Maya Ilieva from SARMAP and myself, I am Michele Crosetto from CTTC. We have five presentations. The presentations are in slot of 15 minutes plus 5 minutes for questions. We have all the presentation uploaded, so we can start. The first presentation is given by Davide Nitti, and it's about passive and active reflector for INSAR application in urban areas.
Actually, my name is Fabio Bovenga. I'm from National Research Council of Italy, and I will present this work dedicated to using active and passive reflector for basically in urban areas. And so this kind of reflector have been used in the framework of solar interferometry basically for improving the measurement points where coherence coherence is low, and so there are no coherent targets on the ground. And of course, active and passive reflector have complementary advantages and disadvantages in terms of size, cost, hardware, complexity. But we are specifically interested in assessing their use in the framework of urban settings where further and more challenges occur related basically to the interaction of structures around the corner, which corrupt the signal both in amplitude and phase. And we started to set up this experimental sites in the campus of University of Bari. Basically, we deployed 6 reflectors, both active and passive. You can see here the location on the rooftops of buildings, specifically the physics department. And these pictures are pictures of the reflectors. You can see there are some look quite old-fashioned, some quite new, but I will describe with more detail during my presentation. And we combine these reflectors with 3 Sentinel-1 datasets and 1 Cosmos Camera dataset to derive more than 13 configurations that we use to assess the use of these reflectors for displacement, basically for displacement monitoring, and compare results coming from passive reflector of this different size from active and passive reflector, and we also test a new operational mode and a new kind of reflectors. And concerning the processing, we set up a multi-temporal processing scheme concerning performing standard multi-temporal interferometry. And at the end, we have both displacement time series and a stack of amplitude. And by exploiting the amplitude, we recognize, of course, the response of the reflectors. And then we compute the radar cross sections, and we compare with the nominal one. And then we are able to analyze the time series of both amplitude, so radar cross section and displacement. A few words about so this is an example of backscattering coming from both active and passive, and possible interaction, because as we will see, these are quite close each other, and they in some way interact. And then a few words about the radar cross-section estimation, because the nominal one is straightforward, because comes from the standard formula, but the estimated one includes the estimation of the scattering coefficient, and then starting from this we compute the radar cross-section, which include both the signal from the artificial reflector and the clutter. So in order to remove the clutter, what we did basically is to exploit acquisition before the deployment of the artificial reflector. Then and then we use two different approaches. One very simple, so we compute the radar cross-section and remove and subtract, and the other one which involved fitting of a Rayleigh distribution for the acquisition where there are just the clutter, and Rice distribution where we have clutter and the reflector, and this, so by fitting these two distribution we derive the radar cross-section. And just let me start with some results. So this is for, I'm start with the corner reflector number 1, which has an edge of 1 meter. It works in C-band, and is was set to point descending orbit. And here you see the table present result from the optimal pointing angle, and you see that there is a very good agreement between the nominal and estimated radar cross-section, but also for a suboptimal pointing configuration with a difference in 10 degrees. And so, of course, in this case, we have a loss in the radar cross-section. Then we also experimented the interaction with the active reflector, which is located very close to these two corner reflectors. So this is the active one that I will present very briefly later. This is a meta-sensing active reflector in C-band. And we see that by exploiting acquisition before and after this active reflector was switched on, we see that the standard deviation of both backscattering and the displacement derived by the analysis of the multitemporal stacks, the standard deviation of course increases because the two signal interacts. And then let me show you some results concerning the displacement. Here you see the time series, and you see that by looking at the displacement, you see periodic trends related to temperature changes, and also you can see here a jump in response because in July 2025, because of the roof pavement renewal, the corner was moved, so this induced a shift in the line of sight of about 6 millimeters that can be precise, 4 millimeters that can be precisely measured by removing the periodic signal. We also use the multitemporal processing to derive the 8 to perform a precise measurement thanks to the standard multitemporal approach of the elevation with respect to the ground of the corner, and also in this case we have very nice agreement with the estimation performed by in situ devices. And also we tested and improved the sensibility to target 8 due to the larger orbital tube starting from mid Sentinel-1 orbital tube starting from mid-April 2024. Here you can see the distribution of the scattered of the temporal and normal baseline. You see that the wider range of value of the normal baseline. And according to this, we have we measure the root mean square error related to the synthetic error of 10 meter, 8 error of 10 meter induced into the data, which indeed increase the sensitivity. So the phase sensitivity increase after the range of normal baseline increased. And let me move to the other passive corner reflector, so CR0. A, because it was first in one location that it was moved to another building to perform another experiment that I will present later. And this is a triangular trihedral with an edge of about 70 centimeters, so smaller than the previous one, and so we expected a reducing radar cross-section, and indeed we measured as we measured and estimated. And this reflector was set to point ascending orbit, acquisition from ascending orbit, and it was also moved up and down in order to measure the precision in estimating its displacement. And before showing the result, let me introduce this other reflector. This was designed ad hoc. It is an hexagon of side about 46 centimeter, made by a grid of triangular trihedral with edge of about 10 centimeter. It is made by aluminium with a penetration of about 0.3 micrometer in C-band. And it has a response very directional, as can be seen from this electromagnetic simulation, and with a radar cross-section of about 26 dB for square meter. And it was mounted on the top of the CR0, and then I will show you the time series of both the radar, the backscattering and the displacement, and you can see that by exploiting for instance, the mean and the standard deviation of the backscattering, you are able to distinguish the different behavior of the corner on the ground. For instance, after a few months from the deployment, we have some restriction due to the COVID-19 emergency period, and so survey was not possible. And indeed, during this period, both leaves and water layer accumulated within the corner reflector, and this, of course, worsened the response. And you can see a larger standard deviation in the sigma naught. But soon after, we of course maintained cleaned the device, and then we can very nicely follow the up and down displacement induced artificially. And so here we see the displacement, here the backscattering, but also the deployment of the hexagonal periodic structure reflector, which indeed increased both the backscattering, you can see here, and also changed the scattering center of the reflectors. Indeed, you can see from the displacement, and also, of course, we are able to follow very nicely the linear displacement that we artificially provide on the reflector. But we also acquired some Cosmos Skynet images, of course very few with respect to Sentinel-1, and we see, for instance, that we had a very high sensitivity to the water layer during the period of where the water accumulated within the reflectors. And by summarizing the results, so the backscattering values estimated are very close to the nominal one. We also experimented the interaction with the passive reflector with the active reflector ECRC. And in this case, this impact is even worse than in the case of the first corner reflector, because this is smaller than the first one. And we also measured the hexagon periodic reflection increase, and we are able to measure displacement values very close to the one expected by the one that we induced on the corner. And just I will mention this ECRC active reflector. This is the first one that we deployed. It is from MetaSensing, and it works for C-band, and it very nice because it works for both. It's set for both ascending and descending acquisition. But what we experimented that we had some problem with the works of this device. So there are several periods it was switched off for maintenance, and we also measure a displacement standard deviation higher than in the case of the passive reflector. But now let me move to the last part of my presentation that concerns the use of these two active reflectors, one in C-band and the other one in X-band. These were designed in the early 90s for supporting calibration and activity of such sensor from on board of NASA airplane and satellite mission. And the ARC-C works in C-band, of course, and pointed for descending orbits, while ARC-X pointed for Cosmos Skymed ascending passes. And moreover, the ARC-C horns, this one, were rotated to at 45 degrees in order to perform in quad-pole sensing. And also it was moved upward by 7 millimeters to check the displacement estimation. And here you can see the time series of both sigma naught and the displacement, but I will spend few words about the displacement time series that we are able to derive on both VH and VV, of course, images of Sentinel-1 because it works in a quad pole, and you see here the jump of 6.4 millimeter in line of sight, which is in agreement with the vertical shift that we induced. And these are for the ARC-X, so the active reflector in X-band from these are acquisition from Cosmos Skymed. Are quite few with respect to the Sentinel, those from Sentinel-1, and we also see some quite unstable phase behavior of this active reflector. By summarizing, for the ARC-C, the measures backscattering value are close to the nominal values, and the measured displacement value are in agreement with the vertical shift, while ARC-C, there is a disagreement with the difference in the estimated backscattering coefficient, because basically we overestimated the nominal one because probably we did not take into account the loss of the hardware components which are quite old. And then also the phase stability is quite poor. But now I will conclude my presentation by these two experiments that we set up in order to assess the possibility of measuring differential movement within a resolution cell. So what we did basically is to put very close the corner reflector CR0 with the ARC-C, and so both working on C-band, of course, and these responding in VV, and this was set to VH polarization. And of course, the distance is 1 meter, and they are so well within the resolution cell of Sentinel images. And we also moved the passive reflector in vertical direction in order to verify the possibility of measure within this resolution cell, the this movement, and indeed by processing both VH and VV Sentinel-1 images, it was possible to identify the response of coming from the two reflectors. Here you can see the passive one, and here the active one, and also to measure, of course, this is for the VV image and this is for the VH image, and it was possible also to measure the displacement induced by artificially on the corner reflector. So this proves the fact that we are able to distinguish these two scatters moving differential movement within a single resolution cell. The same can be obtained just by exploiting temporal diversity. In this case, we set the active reflector on VV polarization. The distance is again within the resolution cell, but we also include a delay line of 30 meters, which induces a time delay of about 123 nanoseconds, which means 8 pixels in range direction. And indeed, by looking at the response of in this case, in a single VV Sentinel-1 image, we see the corner reflector here. We see the response from the active reflector 8 pixels far away in the range direction, and we are able to again to look at the time series and to measure the displacement. In this case, very small, induced artificially on the passive reflector. So. I concluded my presentation. These some final remarks. I will just I already included these comments during my presentation. I will just say that this site will be included into SEO's Carnet and may become an open experimental facility. And further work will be devoted to experiment active reflector in L-band. So I concluded my presentation. Thank you.
Thank you very much. Unfortunately, we do not have time for questions now. Please keep your questions for the end of the session. And I would like to invite the next speaker, Adriano Nobile.
Hello everybody, thank you for coming. It's early. So today I'm Adriano Nobile and I'm working in NASA in Rome. And today I will show you some insight on the Isabel project. So the project was funded by the European Space Agency with the Abruzzo region and the city of Turin. And the scope of the project was to monitor infrastructure in one of the two areas. To monitor infrastructure health and make risk assessment using both satellite and in situ data. The other important thing it was to use the 5G connection to transfer the dataset. So we wrote this project that is called Integrated Satellite and Ground-Based Monitoring for Bridge Health Lifetime Assessment. The target area were two bridges located in Turin, and both were occasionally monitored before this project, even if they are affected by both natural and human activity hazards. The team working on this project are composed by NASCA, that has expertise in natural hazard and infrastructure monitoring using remote sensing technique. S2R, that is a consulting engineering working in both civil and environmental engineering. The Politecnico of Torino, in particular the civil engineering department, and N+, that is a company working mainly in monitoring health infrastructure like bridges and viaduct. The two bridges are located in the Amedeo 8 bridge, located in the northern part of the city. It was built in 1933, and it crossed the Sura di Lando River. Instead, the other bridge is the Regina Margherita, and it's located in the central western part of the city, over the Po River, and it was built in 1972. The structure of the two bridges are completely different, the length and the number of piers, number of stands, but together they are representative of the bridges of the entire area. For the project, we used satellite images, so in particular SAR technique to study the ground deformation over the structures and on the area surrounding the bridges. Then we use photo monitoring to evaluate change detection over the bridges, and also to evaluate local displacements. And then we installed accelerometers and inclinometers for structural analysis. Inside dataset were transferred through the 5G connection directly to a web platform where the dataset can be analyzed automatically for real-time monitoring, even early warning in case of some threshold were overcome, and mainly for smart asset management. Furthermore, we provided a digital twin of the bridge that were really useful for the risk assessment. For the INSAR technique, we use persistent scatter technique. In particular, we use Cosmos Skymet images provided by the Italian Space Agency, X-band and high resolution, so very useful for this purpose. We use both ascending and descending orbit to get the redundant information on the ground deformation, and most of all to be able to convert it in vertical and horizontal displacement that is quite easier to explain to a customer. The observation period was between 2011 and 2025. These are the results for the Amedeo 8 bridge. It's quite stable. Only a few PS located in the abutments of the bridge are moving away from the satellite with a rate that is less than 2 millimeters per year. The decomposition is the vertical component of the deformation show exactly the same, so there is subsidence in the abutments of the bridge. The bridge instead is stable. We also produce an interferometric section that is quite interesting because it shows that the central part of the bridge, that corresponds to this part, is oscillating during the entire period. Probably this is due to the water level changes during the years. Just to conclude for Amedeo 8 bridge, this is the cumulative displacement in the vertical direction, and overall the bridge is stable. Let's move to Regina Margherita bridge. As I was saying, the structure is completely different. Here we have only one stand, and the stand is moving again, both line of sight in range increase. This time some pixels are moving up to 4 millimeters per year. If we look at the deformation time series, we can see that, however, it is linear mainly, and there were no big changes during the 14 years of monitoring. Instead, when we make the mean and we reduce the noise, we can see that there is a very nice thermal deformation on the data. One important thing for this bridge is that the upstream side of the bridge is moving faster than the downstream part of the bridge. This is very important for structural information. We also use photo monitoring technique to assess some information on this bridge. So we installed cameras on both bridges. Here I'm showing only one on Amelia Way. The camera has two lenses. One is a wide-angle lens that can cover the entire, almost the entire bridge. And the other one instead is pointing a specific area, in this case one of the piers. The image frequency acquisition is one image every 5 minutes. All the images are directly sent to the web portal where the IRIS software provided by Nazca is installed and process the change detection of the images automatically. But just in case an operator can do some specific analysis. So in this case, we can monitor, for example, the level of the water, or we can monitor the accumulation of debris below the bridge. This is very important for maintenance purpose. We can also monitor the displacement of specific pixels, like in this case, and I will show you another slide. So we detect some, for example, some fracture, some fissure on the bridge. We make the change detection just to see if the fissure changes during time. But we can also take one pixel and check if it moved during the entire analysis. Finally, we installed the inclinometers and accelerometers. As I was saying, in the platform there is an early warning system. So if one of these instruments show overcome a specific threshold, a red alert will arrive directly to the customer. These data were used also for to calibrate the final element model that we used for the digital twin of the bridge. Everything started from the original project that, as I was saying, were built in 1933 for Amelia Way and 1970 for Regina Margherita. We made some studies with the self-load of the bridge to check its stability. Then we used also we made some tests with other load data just to see how it behaves. We also compared the displacement produced by the temperature changes, and we compared them to the oscillation that we observed with the INSAR deformation. And finally, we made a model analysis to evaluate which are the oscillation frequency of the two bridges in this case, and we calibrated them with the accelerometers installed in on the bridges. And as I was saying in the beginning, these data are fundamental to evaluate the risk and also to estimate the threshold for the accelerometers for the early warning system. I think I can skip this one. So I finish here my presentation. Thank you. Yesterday at Nazca we had a poster, but tomorrow we will have another poster in the poster session. Otherwise, you can find us at our booth in the poster hall. Thank you.
Thank you very much. We have time for a couple of questions.
Yes, thank you for your presentation. I was wondering if you do this kind of analysis, the accurate geolocation of the scatterers on your bridge is very important probably. What did you do in order to align a scatterer to a particular position on the bridge?
So we make some, let's say, tests just to verify if the position is correctly provided by the software, by the output of the software. Otherwise, we can move it, let's say, manually in a certain way to find the right position of all the PS.
Thank you.
Yes, thanks for your presentation. I was curious about, you showed one slide about also about the loading. Could you link the number of vehicles on the bridge with a deformation in your time series? Like link the loading with vertical movement or something?
This is a tricky question. Probably the engineer behind you can reply, but
maybe I'm part of S2R, that is one of the other companies that is involved in this project. I didn't follow directly these topics, but maybe the number of vehicles on the bridge as a different time of observation with respect to the ones of satellites. So in that case, the finite element models could be more appropriate to evaluate local trends, while satellite data can give us an information about general deformation trends that the bridge is undergoing in this case. I hope I answered somehow.
No, my question was mainly there because we are trying to do something similar, but we don't have images of the whole period. And because you have images, I thought maybe you could have an image of the bridge at the same time of satellite overpass and see whether there are vehicles on the bridge and whether you see it back in your data. But
I mean, probably, yes, we need to check specifically the single PS and compared to the deformation, yes, the oscillation of the bridge, but probably I don't think the photo monitoring can observe really this kind of deformation. I don't know, you were talking about, or you want...
No, I thought in the photo monitoring, you should be able to see at satellite overpass whether there's something on the bridge. That was mainly,
okay.
I thought.
Okay. No, yeah, one short one.
Okay, thank you for your presentation. I have actually a follow-up question from Ramon and face centers the location of the bridge, because if you look at two sides of the bridge deformations, is it possible that from the face from the low side lights, the movement of lights, but not actually a particular section from that bridge? So I think it's quite important to the geocoding, geolocation of the scatter. Just a quick comment. Thank you.
Okay, thank you.
So thank you. I think we can move to the third presentation. It's given by Francesca Cigna. It's about mapping differential land subsidence risk using INSAR and urban settlement data, national scale assessment in Italy.
Okay, thank you for the introduction. So, where did we start from? By looking at the INSAR-related literature over the last decades, what we observed is an increasing trend in the transformation of INSAR observations into risk-related information for urban infrastructure. So as you can see in the plot here, And in the map, what we observed starting from 2008 approximately is an increasing number of studies using INSAR, for instance, for the investigation of hazard induced by land displacement, in particular differential displacement. And as you can see from the maps, these studies were mainly focused in Central America, but also in Europe and Asia. In 2021, we also started to develop risk assessment workflows incorporating INSAR into these sort of investigations, looking at urban areas, and also more recently a boost in the number of studies looking at the exposure of infrastructure and communities. So the goals of our work were to try to revolutionize the risk assessment workflow by combining INSAR information together with urban segment characteristics and apply this new novel workflow to assess present-day land subsidence-induced risk in the country of Italy. As you probably know, this is one of the most affected countries by land displacement, so a perfect target to test our new methodology. So geographically speaking, we focused on the 15 metropolitan cities of Italy, and they host more than 21 million inhabitants across more than 54,000 square kilometers. And as you can see from the urban growth pattern over the last 50 years, these cities were moderately expanding, incorporating more and more urban areas and more people that could be potentially affected. So looking at the exposure to ground displacement, this is the overview that you can get by looking at the European Ground Motion Survey data for the last years. As you can see, we have a number of hotspots within the 15 metropolitan cities. Many of them are very well studied and known. But what's important here is to try to assess the overall impact that can be achieved by these land movements. As you can see, in terms of the vertical velocity, we are talking about more than 3,000 square kilometers affected by more than 2 millimeters per year, either in the upward or downward direction. And these involve more than 2.8 million inhabitants. Looking at the horizontal rates, we are talking about more than 2,000 kilometers affected and more than 1.5 million inhabitants. So the impact in general can be very significant across the national territory. So what we focus is not simple magnitude of the land displacement. We are talking about different ground displacement. So anything related to the process of differential displacement and causing something like that. These are examples of impact that we observed in Central Mexico. For instance, you can see undulating roof lines in Mexico City, because this part of the city was actually sinking more than this part. You can have house fisherings and cracking. You can have surface faulting also affecting transport infrastructure. So this is the process that we are looking at, differential displacement and deformation. So to quantify that, we focused on the structural stress that the differential displacement can cause on urban structures, so either buildings but also transport infrastructure. And we focused in particular on these two stress parameters called angular distortion and horizontal strain. They can be derived simply by the amount of differential displacement in the vertical direction direction or in the horizontal direction, divided by the distance between the 2 points that you are comparing when doing this assessment. And in terms of numbers, this is an example of what these parameters means. For instance, if you have an angular distortion 0.22%, it means that you have 22 centimeters difference in the displacement measured between 2 points located at 100 meters distance, to give you a flavor of what the numbers means. So what have we done in practice for the 15 metropolitan cities? We consider the European Ground Motion Service data, the ortho product in particular, to get the vertical displacement velocities, the east displacement velocities. We calculated partially the angular distortion and horizontal strength for all the cities, pixel by pixel, referring to a reference period of 10 years. So we assume that what we observed in the European based on the European Ground Motion Service was occurring for a period of 10 years. This is true in some cases. It's a bit an underestimation in some others, but something that we can discuss more in detail later. And the result is basically an assessment of level of hazard scored according to a reference scale from H1 low, H2 medium, H3 high, and H4 very high. And how did we get these ratings? Basically, we compared what we observed in terms of structural stress from the angular distortion and horizontal strain against geotechnical thresholds for the allowable segment of buildings. So by comparing these numbers against the thresholds, what we can get is the scoring and a map like this, scoring the hazards, especially within the metropolitan cities. Looking at the exposure and vulnerability, we considered in particular the type of building, so either residential or non-residential, and also the height, so the number of floors involved in each case for each building, and last but not least, the age of the building. So what we assumed is that non-residential buildings are more vulnerable than residential ones, because the non-residential ones include hospitals, churches, schools, so they are assumed as more vulnerable. We also assume that taller buildings are more vulnerable than shorter ones, and also that older ones are vulnerable because potentially they are not following engineering and technical construction laws that are more looking at the structural safety of buildings. So by using this scoring approach, what we've got is a map ranking exposure and vulnerability from low to very high, similar to what we did with the hazard, so from EV1 to EV4. And how does it work in practice? So we collected information that I mentioned about the type, age, and elevation of the buildings from these globally available data sets. So the one on the left is the global human layer, providing information about the type and height of the buildings. And then on the right you have the world settlement evolution layer, providing information about the construction year. So we consider the year 1985 as a threshold to distinguish older from newer buildings. This is what is available, so the best we could do. And the result is a scoring map of exposure vulnerability at pixel level according to the scale that I mentioned before. So what happens with these two layers? So considering the definition of risk as the combination of hazard, exposure, and vulnerability, what we did was to just partially combine the exposure vulnerability scoring with the hazard scoring to get a risk map according to this risk metric. So you have basically four combinations, so 16 possible combinations of the levels of hazard and exposure vulnerability vulnerability, and for each combination you have a resulting scoring of risk. Of course, this is a tailored matrix, so it's built according to your engineering knowledge and many other considerations that you can do in terms of hazard, in terms of the areas of interest. And what you get as an output is a ranking of risk according to scale. For instance, in this case, we decided to have three levels, so low, medium, and high. And it provides you with the prioritization of attention that you should put, spatially speaking, into your investigated area. So for instance, for R1, we consider an acceptable risk level, and no particular actions were suggested, while for medium and for high, of course, as the likelihood of structural damage is higher, of course, you should go into detail by, for instance, continue the monitoring, or also going on site to check actually the presence of any damage already occurred, or incipient damage that could occur at single infrastructure level. So in terms of maps, what we've got is for each of the metropolitan cities, we've generated the different intermediate risk assessment level maps, and also the final risk maps. Here we have a zoom on Rome and Naples, and as you know, we are not talking about a single type of processes, but we are considering all possible land displacement processes involved. So we are not just looking at subsidence induced by groundwater or volcanic activity or landslide, but it doesn't matter at this time. So you can see in Naples, there is a lot of land displacement and deformation related to the activity of Campi Flegrei, and this is the result in terms of risk. There is a wide area involved in the higher risk level due to significant differential deformation induced by the Campi Flegrei deformation pattern. In Rome, the situation is more yellowish, so mostly in the medium class, but as you can see, there are hotspots of high risk. For instance, this is in the Justinian Emperor Street quarter, where actually a few years ago, one or more buildings were demolished due to the occurrence of differential deformation, differential displacement. So actually is an accurate assessment of what's going on the ground. So overall, to show you some statistics, here is the total amount of land involved in the high-risk class according to our study. So we are talking about 1.44 square kilometers overall within the 15 cities. And within this area, there are more than 2,700 buildings that could be potentially impacted. So as you can see here, the figures are quite interesting and worrying in terms of land management and urban management. Here you have the split city by city, and as you can see, the presence of high-risk classes is not concentrated on all cities, but on a few hotspots. Like we have a significant amount of high-risk areas in Rome, we have in Naples, and so on. As you can see from the statistics, you can see here is the number of buildings involved within each city. So a quite worrying situation. Here is another approach to visualizing the result, and it's quite useful, especially when you deal with communicating with decision makers and stakeholders, as we did within this project. So instead of looking at pixel-based maps or raster maps, what we did is to create a sort of traffic light visualization approach where each town was coded according to the highest risk level that we observed within the administrative boundaries of the town. And this is quite straightforward, especially for non-experts to know where to look at, where to zoom first to look at our risk mapping products. So what I showed you before was about present-day risk, but we also made an assessment about what could happen in the next decades in the future by considering mainly climate change projections and parameters, and also human-related factors and behaviors like the use of groundwater in each metropolitan city, and a projected use in the next decades in 2050 and 2100. So considering projected data for precipitation and temperature and the effect on evapotranspiration and all the other processes involved, we try to, with a simple modeling approach, we try to estimate what could happen in the next decades. And basically what we did is to consider 2 emission scenarios, 4.5 and 8.5, which are the medium and tragic, let me say, emission scenarios. And what we did is to project our hazard estimation into the future to try to understand what could happen if nothing changed with respect to what we observed in the past and the predicted precipitation and temperature data for the next years. So to conclude, our main achievement is to create a baseline assessment at national scale that could act as a starting point for any future risk assessment to run for the national scale in Italy, and to create layers of exposure, vulnerability, hazard, and risk that could be used by stakeholders. What's really important, technically speaking, that of course there are a lot of assumptions made when we do such a mapping exercise, and most of them are discussed within the paper that we published last year, but we can of course discuss about them in detail now or even later. But the key point is that we used open data, globally available, but also open workflows that can be exported as they are somewhere else in the world. They can be improved by incorporating higher resolution data or more detailed about the vulnerability of buildings and other information that can feed into the risk assessment workflow. So this can be reproduced openly and exported everywhere. And what's important to say is that even if somehow this can be considered a qualitative approach in some of the components of the workflow, it's a step forward from the simple observation of INSAR data and INSAR-based mapping of moving areas into something that can be used by the stakeholders. And this was demonstrated during this project because we were in contact with stakeholders from Emilia-Romagna region. They were involved from the very beginning of our project into the development of the methodologies and the products, so we are aware of their needs and how they could use these maps in their daily assessment. So I leave you here with a few references. They are all open access, so you can get a copy of them to get more details about what we did. And all that we did is also openly available in the project website, is subrisk.eu. And most importantly, we've created a control room, so it's a web platform opening access to all our mapping products. So you can visit the control room and access the intermediate and also final risk assessment products. You can query them, you can ask for statistics and export whatever you need from our assessment. So you are encouraged to visit the website and the control room. Thank you.
Thank you very much. Questions? One question?
Thank you very much, Francesca, for the remarkable effort, especially using openly available data. That is very important and allowed to expand potentially to the whole Europe. one point I was trying to figure out and having your feedback is the potential mismatch between the resolution that you have from, especially the ortho data is 100 meter, correct?
Yeah.
And the differential settlement that you're looking for in buildings that are much smaller. So how much you think this affect the results? And how much you think using high resolution data at maximum, not just the ortho that reduce, but at the maximum level, can improve the quality of your work? Thank you very much.
Yeah, this is an important point and is part of our technical discussion within the paper and also within the project deliverable. So yes, as you said, EGMS ortho products are at 100 meter resolution. So we use them by considering that all our assessment is based on a 100 meter by 100 meter pixel. This means that what we can see is only at that specific spatial scale, and we assume that everything is homogeneous within that pixel. Of course, within that pixel, there will be plenty of buildings, and each building will behave differently, probably at the local scale, so we are aware of that, and we also worked in the same project at the regional scale and then the local scale to study the scale effect of this spatial resolution and other parameters. Of course, at the scale of a single building, high resolution data like from TerraSAR-X or Cosmo are much more suitable to be more accurate in the differential deformation assessment. And at the scale of a single building, you can capture even smaller differences, and probably you can go up to the single building block scale with a much more reliable set of information. So of course that's what is needed at the local scale, but this study is aiming to provide a national scale overview to know where to look at, and this is what we did within the project. Thank you.
Thank you very much. I would like to invite the next speaker, Niels van Baldrick. Opportunities, challenges and limitations of INSAR for complex and dynamic civil structure monitoring.
Yes, thank you for having me. I'm Niels. I work for the Dutch Ministry of Infrastructure and Water Management. We're working with a very small team of about 5 people in an organization of over 10,000 people. We did a case study on the Botlek Bridge in preparation for our European tender to upscale the INSAR monitoring within our country. So a little bit about our organization. We're responsible for our nationwide portfolio consisting of the road network, the waterways, the water bodies. And so the ongoing deformation monitoring campaigns are becoming very resource intensive, very costly. So we're looking into alternative ways to monitor our assets. And so today we will be focusing on the bridges. We've had some successes with roads. My colleague Gert also has a poster on this, so I suggest you check it out. And as a case study, we consider the Botlek Bridge in Rotterdam. This is a very nice asset of ours. We have 2 separate bridge decks that are both liftable. We have these massive support pillars which make us radar shadow. We have these steel trusses which may be subject to double bounce effects. And in the surrounding areas, we have a tunnel, we have a railway that has been refurbished in the recent years, and we also have some adjacent viaducts leading to the bridge. Now, we did this in collaboration with SatSense. Tom also has a brief poster on this, so I suggest for the INSAR processing to check him out. So thank you for them for doing the INSAR processing. Here we have a top view of the Botlek Bridge. And so for the time series itself, we use TerraSAR-X data, strip map data, from 2 tracks spanning roughly 3.5 years, from 2022 onwards. And in addition to this, we have sensor-based bridge opening times, as well as a high-resolution DEM of the Netherlands, which yeah, is very much a luxury. And then for the products, we derived level 2 time series, so this is on a point level, and then we did some aggregation to derive the decomposed time series, so the horizontal and vertical, also to communicate this to the constructional experts within our organization. Now, briefly, how we go from these point data to polygon data. We aggregate the point data based on some quality metrics, and then we perform a vector decomposition to derive horizontal and vertical displacement under the assumption that there's no deformation occurring in the latitude or the longitudinal direction of the bridge. And what's important here is that we define these segments in accordance with structural boundaries, such that we're not mixing signals from different points of the structure. Now I'll take you through some of our findings. What we saw is that, as mentioned before, these support pillars, they cast massive shadows on the bridge deck, which essentially means that we can't really retrieve information from a particular line of sight from that direction. And what we also see is that those trusses, they cause a lot of double bounce effects, so vertical misplacement of scatterers, even though these scatterers may contain information of the bridge deck. Something about the motion that we observed for the project. As we can see there, we have a fixed joint in the middle and then 2 expansion joints at the other support pillars. And if we look at the time series, we see that these are very limited in motion. And if we compare this to the motion around the expansion joints, we can observe an annual signal of roughly 20 millimeters. Which also poses some unwrapping problems because of the magnitude and the wavelength that we're using to observe these motions. We also, because we perform subsegmentation on the bridge, we can also see a gradient in horizontal expansion. And our constructional experts are, for example, interested in what the behavior is on the expansion joints. And so this is a nice way of kind of approaching this annual signal, which we don't really observe using our traditional methods, unless we have some sensors that are observing this. But on a national scale, this isn't really viable to implement. And what's also really important is that if you weren't doing this subsegmentation, then some of the signal might be lost. Because if you look at the segment that's highlighted here, on the right-hand side, we have very little horizontal expansion, and on the left-hand side, there's a lot. And so if you consider this as a singular element, some of this signal will be suppressed in the product. And it may not be representative of what's happening on the expansion joints themselves. Yeah, some of the lessons learned from this project. First of all, this was a big success for us. This was an experimental project for a European tender, and we weren't really sure what to expect in a bridge context, also because of the highly dynamic environment that we considered throughout this project. Something that we will be taking into account for future projects, for the upscaling of INSAR implementation, is that the segmentation really must accommodate these structural properties. It's very important not to mix signals and suppress certain aspects to retrieve this meaningful deformation that our constructional experts can use. Furthermore, the radar artifacts such as shadow and double bounce I've highlighted, but layover also occurs. It's important that we can assess these artifacts prior to any processing, which really helps us determine which objects are viable to monitor with INSAR and which objects may not be as viable to monitor with INSAR. And furthermore, as we saw, there's a gradient in this observed horizontal expansion. Alongside the horizontal and vertical deformation that we normally retrieve, there's also an internal expansion that's occurring, which we don't observe during our regular monitoring of a leveling campaign, let's say every 1 to 5 years. But it is observed in the signal of the leveling campaign. So this internal expansion can also be a deliverable for us in particular. So some of the next steps for Rijkswaterstaat. Right now we have a tender going to examine more bridges and essentially come up with these object type processing guidelines to essentially derive meaningful information on the object that relates to the constructional experts. What's also important to us is to, because we have a very large portfolio, is to assess where INSAR will be beneficial and where INSAR might not be so useful for us to start monitoring. And we're also facing a challenge of integrating INSAR as a recognized methodology within Rijkswaterstaat. And yeah, we want to upscale it to a point where we determine the scope of our deformation campaign guided by INSAR, because we can more or less see where most deformation is happening. That summarizes my presentation. So again, thank you to Tom, who was responsible for the INSAR processing of this project. More details on that you can get from them. And yeah, for the road context, I suggest you check out Gert's poster. Thank you very much. That was my presentation.
Yeah, thank you very much. Time for questions or comments, please.
Thank you very much for your interesting presentation.
Yeah, 1 second, 1 second.
Yeah, thank you very much. I'm just wondering about the orientation of the structure. I mean, when you're talking about, the gradient in the horizontal component, east-west, north-south. Mm-hmm. Can you comment on that, please?
I'm not sure I understand your question. We observe a gradient in the horizontal expansion, but this is, the orientation of the object is very favorable compared to the line of sights that we have in terms of observing this. But I'm not sure.
To make it clear, my question is that, for INSAR, the limitation is this. It's not sensitive to the north-south. Mm-hmm. If you have the motion, in the north-south component, then maybe when you're writing guideline or you're coming to the suggestions, maybe that cannot applicable to all type of structures, in different orientations. Just wondering, I don't know. Yeah.
No, sorry, I misunderstood the first time, but that's a very good point that's being raised. This is something that we are taking into account when determining the suitability of INSAR prior to any processing. Because obviously, if we're interested in horizontal movements, but the orientation of the object is, perpendicular to this pretty much, we're insensitive to this deformation. And so the scoring, let's say, of object suitability for INSAR goes down because of the object's orientation. But again, this is very much under development as we speak, but this is something we will be taking into account, yes.
Thank you very much also for a very interesting presentation. I was wondering about this metric on the axis, horizontal seasonality. What does seasonality mean?
Sorry, that's just the amplitude of the model estimation. So
peak to peak, or is it the amplitude?
It's the amplitude.
Amplitude.
Yeah.
So it's double of this.
So we see roughly at the yellowish line, we see an amplitude of roughly 20 millimeters, so that coincides with an amplitude of 10 millimeters, so roughly 20 millimeters of deformation, yes.
Okay, you mentioned at the end shortly the layover that you might be dealing with alongside the shadow. I was wondering, pillars seem to be quite common on a lot of bridges. Do you have any strategy to deal with the layover, or do you mask out these areas and do you consider them just unsuitable for INSAR monitoring?
So far, we haven't really explicitly dealt with layover. In some other projects, we've seen that layover caused by vegetation, for example, decorrelates certain periods of time. I think the main takeaway is that also layover can be estimated, let's say, prior to any processing that's going on. So you can more or less have a good guess of where you're going to get PS coverage and where you aren't going to get PS coverage. So in terms of mitigation, I think that happens prior to starting a project. So far, we haven't had any concrete methodology of dealing with layover effects during processing. Thank you.
Thank you.
All right, thank you for your presentation. So in these slides, you mentioned about the sub-segmentation. So what do you mean by sub-segmentation? It's like you process those PS points separately on a different section of the bridge, or what does it mean?
Thank you for your question. When I speak of sub-segmentation, we looked at the construction and we delineated, let's say, structurally uniform segments which are separated, for example, by these expansion joints. Now, these segments are quite large, and so their internal movement might be very variable. And so when I speak of sub-segmentation, we expect the highlighted element to move relatively uniformly in terms of trends. But just to see, for example, the internal expansion, we subdivided this element into 5 or 6 adjacent segments. Again, also because this was experimental for us, just to see what information might be revealed or hidden when we do this.
All right, thank you.
Yeah, just a short follow-up question. It's quite interesting. We know that bridges expand with temperature, so the seasonality or the variation of temperature is expected, I guess. But did your bridge experts, if you subtract the known thermal component from your signal, do you see something that is really gives any indication on the health of the structure?
I assume it would. This is a step that we're yet to take. The discussions are ongoing with the constructional experts on how to utilize this information. Also because there's a lot of information that we normally wouldn't have. I think for Rijkswaterstaat in particular, we have a leveling campaign of most of our objects, but during this leveling, we don't really observe this internal expansion, let's say, because the points are so sparse in terms of temporal sampling. So this is relatively new information for them also. Obviously, this is taken into account during the construction. Yeah, as of right now, we're still trying to find out on how to use this information ourselves.
So I think it's all. Thank you very much. We can move to the last presentation of this session, which is given by Michael Fumelis, From Surface Motion to Differential Settlement, an infrastructure-aware approach using Copernicus Sentinel-1 INSAR over Roma metropolitan area.
So good morning from my side as well. This presentation had to be presented by a postdoc student, but here I am. And in fact, it is quite new because we start working on that for a couple of months now. So it is not presenting something mature, but like the initial idea of moving forward with this. I think Francesca did a very nice introduction of this differential motion idea. And we can agree that I've seen for several years several groups transforming the PSI measurements directly into colors into buildings. But this is nothing more than showing the motion of the building. But in fact, the main problem when it comes to infrastructures is the settlement, the differential motion of the building itself. It can be induced by the structure itself due to bad constructions, but also can be due to soil conditions like separate very locally for each of the buildings. We don't check right now which is the cause, but we see the potential issue that might have for this based on PSI measurements. Since we were not like reinventing the wheel here, we did some, in this first initial work, a review. And we have seen that these ideas of differential motion, angular distortion, structural health, they come from engineers. They have been working from that for many decades now. It's the only difference is the way that we are calculating things. Now we try to do that with remote sensing and specifically with INSAR. I need to say that I was inspired more with the work of Francesca and Deodato about working with buildings and measuring this angular distortion. Also, the terminology can differ because some people did discuss about structural health, angular distortion, differential motion, so on. There is also in all of these studies the way we calculate the differential motion change. So most of the cases we are using, I will go forward later on, the measurement itself, the PSI itself, but I've seen like a work like from this group, I think it's the group of also Michele Crosetto, that they did like the points over the structure and they did the interpolation and they get the gradient from that. So there are several ideas. Also, another important is that some points are located on the building, some points are so referring to the motion of the building itself, other referring to the motion of the ground. So we tend to put all together, which is also technically not correct when we try to identify things for specific buildings. So, like going to the metrics, not even the way we calculate that, but even the metrics themselves can be different. So some people refer to differential motion only from the subtraction, the difference between the motion within the building. Then others introduce the idea, the distance between the work, which is more or less the strain coming from GNSS world and what we measure there. But then some people are measuring using this ratio, but then others convert it to percent of slope, and then it's degrees. It's also difference. Another difference that we can add is that we can use the velocity, but also we can use the displacement, the cumulative one. So all this changes the way that we calculate things. And also this is this approach of the gradient. And I'm not here today to say which is better than what, but I'm just presenting what we did over this last 2 months. In fact, we started thinking that it would be very simple, and as normal, when you start working on that, you realize all the issue that comes with this. Here we thought initially to separate our work into 3 different algorithms to do that. So the first one, which we call differential motion demo, that was named by the PhD student, it's not mine. I find it interesting. It's the grid, I say, approach, which is more or less what Francesca presented today. Like you have a grid which you average PSI inside the grid, or you start with resampled data sets, and you measure between the 8 neighbors the differential motion divided by the distance of the points and so on. Then we thought a good idea would be also to use triangulation of the PSI network, and I will go to detail this later on, and then to move a bit further to focus on the structure itself, so to generate a different way. In this aspect that I present today, we didn't go forward with the interpolation technique, but we focus on these three ones. So in fact, the most simple way to do it is to have a grid of measurement, of terrain motion measurement from INSAR, and there apply the normal things that, like you calculate the slope from a DM, so you do exactly the same here. And then you have a set of buildings, and you transfer, possibly depending on the side of the building, an estimate of the angular distortion, the differential motion to the building. Here comes also the question, do we take the mean, we take the maximum motion, differential motion that we have calculated, what exactly? Then in the other approach we propose is that you have the PSI already there. You build a delineate triangulation around this one from adjacent points. You find the differential motion along the structure for these specific points based on the triangulation network. We thought also approaches to take one point in all the neighbor ones, but this caused a lot of noise in the measurement, so it didn't work well. So this is direct measurement for around the building, along the structure itself, the differential motion. And then based on that, we find the location of the max motion, and we transfer that to the building. But we know also the location, which part of the building is more affected by this differential motion. Then we have the other way we thought that could be another approach to do. As I said, we are not like 100% what would be the option, the best option. But here, we don't measure the differential motion directly on the structure, but we measure the motion, the motion rates, the PSI, we interpolate them within the structure, and then within the structure itself of this PSI, we find the pair that is causing the maximum differential motion, and we consider that as the differential motion for the building. And with this way, also, we could also estimate the direction at which the building is tilting. So this is only for the initial generation of the PSI. We used the JEP platform. We used the snapping service, which is based on the stamps developed by Andy Hooper and some improvement that we did over the year. This is already operational since 2021. So we use this service to generate our measurements, and there is an online tutorial for whom wants to use this service to generate these PSI measurements. So we focus on the city of Rome because there is a known motion displacement field there. We process all the ascending and descending acquisition. So there was around 2.3 and 2.7 million points in ascending and descending tracks. And then we use two approaches to measure the decomposition. The normal grid approach, where we average over a grid, like this is more similar to the EGMS one. But there is another also approach that we used which is called NNV. I go back. Which gave a bit more higher number of points, but also we maintain the location of the point itself, and we don't go to a regular grid. I'll go more on that. So this is the ascending and descending. Most of Rome is stable. We have here the Fiumicino area, which is a known signal, so we focused on that. There are some areas along the Tiber that also show some differential motion, and also in the harbor here. So this data set is the last 3 years over Rome. And what we did, it was like a very approach that we proposed many years ago. So we don't do averaging with grids, but we find the nearest neighbor from ascending and descending, and we try to link this measurement to estimate the differential motion. So If we have the up component, we focus now in this study only on the up component. So we have, this is the vertical motion from the grid approach, and this is from what we did in order to ensure to have a bit more dense measurements. So if you see the area of Fiumicino, it looks like that. So it's a grid approach. This is 100-meter grid considered. But if you go to the other approach, you maintain more or less the density of the point, and you can use them in order also to investigate the effect of, because it was a question to Francesca, what about the gridding and so on. So we use this as the initial data set to work on with that. So we used also, like the previous presentation, open data sets. So the goal is to use open data, so we don't need to go to local authorities to ask for that. So this is the building, and this is the measurement from the gridding for up component, and this is the measurement from the decomposed up with the other approach, and we use this as input to further analyze our data sets. So this is over the entire Rome. One of the problems we have is that the data set becomes super large. So CSV shapefile is, in fact, not applicable anymore. So this is the demo, the grid-based approach, and I will go to more details here. This is the motion field. This is the grid for which we measure the differential motion using the grid approach I mentioned before. And then this is the mean differential motion for each building, but if we consider the max, you see the colors can change. So this is also an option which is the best way to do it, because you see that you can change considerably the estimate of motion, of differential motion, sorry. So this is what you get. The advantage of what we did is that also that you can go do the same for the entire time series, not only for the velocity field. So what you can get is the differential motion time series, so you convert that. So you can, of course, get an idea of the average differential motion of this building, but you can identify if there is a specific time over which a specific event happens. So this is different ideas of time series over these buildings. And then we go to the triangulation approach. So we have the initial PSI, and what we do is we build all this network of triangulation lines. We reduce this into maximum segment of triangulation to 100 meters in order to be consistent with the other approach as well. And then from there, we have the differential motion along the buildings, and by this also we can extract the differential motion of building. And you see that this is a bit also different from what we estimated from the previous approach. And also we have the location at which it is identifying as the maximum differential motion for this building. Then it's the final approach that we follow. It's the structure one. So we move from this motion field. We interpolate the points over each of the buildings, and within each of the building now we try to find the pairs generating the maximum differential motion. So this is it. So I need also to say that when you put thresholds here, it's a problem because, of course, you can follow engineering ideas and define this much better than what we have done here. But also there is a problem of each building might have different thresholds. So depending on the structure and how it's built and so on, the material, we cannot apply these kind of thresholds to all the building at once. Okay? So we need to consider also the structure itself. Here we have also the direction at which the tilt is expected for this specific building. And one issue that was brought with to Francesca in the discussion was about the scaling. And we have seen that if we do this regular grid approach at 100 meters, you divide by 100 or 144, 144 meters to generate that. But once you move to a different approach of calculating the differential motion, like the triangulation and so on, the distances become smaller. As a result, all the calculation of strain or differential motion increase a lot. And then you cannot directly compare these two. So this is very similar to what happened in GNSS when you have a regional GNSS network and you calculate strain. And when you calculate strain on a very local network of GNSS point, dense one, you see that the strain is different. So this is the same here. So this is something that we need to have in mind. So when you start comparing approaches, areas, and so on, you need kind of normalization to be applied. This is all from my side. I don't go to more details. The only thing that here are some results. What we try to do is that we do a bit more research on that. Hopefully next Fringe I can have a more complete work to show. Apart from these ones, I have noticed a few things that are quite important. Is the geolocation of the point itself. So in Sentinel-1 we don't have the major geolocation accuracy. So this can introduce major problems when we try to translate that to the health of the building. And the resolution. So if we go to TerraSAR or Cosmos SkyMed, I think it will be better because we will have the measurement of each building, and we will be able also to separate if these scatterers are referring to a building or to the ground, and separate that when we do the differential motion thing. Another thing I mentioned is the scaling, so this needs to be considered. The threshold I mentioned, which this needs to be adopted not only based on engineering, but also on each structure itself. We plan that after we complete this kind of work, that we have also kind of in situ validation by putting clinometers for some buildings in order to ensure that what we measure is okay. And just like a final hint from my side, it is a bit more complicated when we consider not buildings but roads, because there you need to understand if you segment the road, what distance to take around it, especially in intersection of roads, what you do. So in terms of calculating the whole approach is a bit more tricky. So many thanks for hearing me, and I'm here for any questions you have.
Thank you very much. Very interesting. Questions?
Yeah, thank you very much, Michael. Very interesting. I was wondering, every point scatterer that we have has its own quality, right? So so it also means that if you use a velocity like you do in most of your metrics, that for one point the velocity may have a bigger standard deviation than for the other. Did you take that into account, or did you consider the metrics that you got deterministic in the sense that they are all the same and you can treat them as they are?
Yeah. So we don't take only the velocity, just clarification, we take all the time series. So for each one, we do the time series. Yes, this is fully understood. For now, this is the deterministic one, so we didn't look of the error. And in fact, the next step is exactly to consider that. And we are thinking how to do that, because it's a bit tricky. You cannot combine like when you do ascending, descending, and say more or less the average error is this equation, and you apply. It's different because it's also depending on the distance itself from the point. So if you have a point which is far away not with high standard deviation and another one more accurate, you need to scale also the errors depending on the distance. Yeah. So this is something that we need to think of, right, of how to do later on.
Something that we need to bring into the discussion is significance, right? So
yeah,
maybe some of the numbers that we get are there, but cannot be considered significant, right?
Yeah.
So somehow we need to find a way to bring that.
Yes,
yeah.
Yes. This is definitely what we need to do. Otherwise, you introduce like a number which might not be significant.
Right. Yeah.
Yeah.
Yeah. Thank you very much. I know very well this site, so that's the reason of my comment and suggestion. One thing that is that you mentioned correctly in this specific case, and that is a limitation with Sentinel-1 with respect to other constellation, is not only the resolution, that is one point, the ground resolution, but it's also the elevation point.
Yeah.
Because exactly in these buildings that are very known and famous for having also some structural problems, some of them I think has been closed recently, is that there are strong differences between the ground very close to the building itself, and so the capability, for example, with the constellation like Cosmos, Chimedon, TerraSAR-X, or others, are the better capability to identify the elevation, and so discriminating the ground level with a higher level. Otherwise, you mix, and you have probably a reduction of the real deformation that you have on the building, because most of these buildings are deforming due to the settlement, due to the loading of the building itself during the construction. So this is surely one point that probably, I want to say, in view of future mission for Sentinel-1, allowing him to better discriminate elevation, having a worst orbit tube could be an option, because in this case it could be better be able to do this. Another point is probably that these buildings have strong structural deformation, so I think it would be very nice for you to make a sort of validation on site to do how much is capturing, because if using data that are open source, easily available, you can approach so much what is the real truth. That could be really a great success. Thank you very much.
Yeah, thank you. I fully agree with what you mentioned. Yes, this is a problem that we realize, and we try to solve it. It's not so easy with Sentinel. So we have also data set from Cosmo and TerraSAR, so we will move forward with that. About degrading the Sentinel-1 orbital tube, I think it's also already happening with Sentinel-1A we can do. In fact, I don't know, that's a question to Isa, I don't know what will happen with Sentinel-1. Is it going to be decommissioned directly, or we can keep it there for some period to allow some tests that we can do? So that would be beneficial, but I don't think it will happen. Okay. Yeah, many thanks.
Yeah, no, just to say, we were working on the same topic. We did not find a big limitation on the elevation of the PS, because we have a standard deviation in the elevation, which is in the order of 2 meters, 3 meters, which is quite okay to separate point on the ground, on point on the first floor, on the top of the building. What is really critical is the number of OPS, especially if you want to use the European Ground Motion Service or Sentinel-1 based results, is the number of points per building. In our research, we found that we need at least 15 points. And in averages, you can estimate well for building starting from 1,000 square meter above. So basically industrial building.
Yeah.
Okay? This is the most important parameter.
Yeah, and I think we can start not from level 2 data, not the ortho one from EGMS, but we can go one step behind and start with these points for doing the analysis. Yeah. But I didn't show, but I mean, the triangular network that you build and the differential motion network, I mean, there are gigabytes, so CSV shapefile, they don't work anymore. You cannot deliver things like that. So I've heard studies discussing about geodata packages, also GeoPack. There are other formats, I think, in the future, because it's very complicated even to visualize these things. Yeah. That's why, in fact, I show a very small area. It was complicated.
Yeah, I know that we are entering the coffee break, but last question.
Yeah, I was wondering whether you considered calculating the tilt just from the line of sight movements, because I think the switch from line of sight to vertical and horizontal is quite tricky, because you combine these neighboring points, which could be like from different locations. So if you maybe you can also do the calculation of the tilt just based on line of sight.
Yeah, for the time being, we used only the vertical component one. So we didn't use the line of sight to convert for that, but this is not a bad idea. But then, yes, indeed, you need to have some assumption, because anyway, the ascending and descending will never be in the same location. So either you take the centroid of them and you do there some calculation, or you transfer just the data from one another and try to do that for line of sight. You mean for line of sight for each layer alone? Yeah.
So do it for ascending and descending just separately, and do not bother about the decomposition.
Yeah, that could be also a good approach to do. Yeah, because you avoid one of the assumptions that you do. Yeah, I agree.
Okay, thank you very much. Very nice discussion. It's time for coffee, but I really want to invite you for the roundtable in the end of the day. Please follow the rest of the sessions in this topic, and hope to see you in the end of the day for the roundtable. Thank you.
Sorry. Se parli italiano te lo spiego in italiano, se va benissimo. Allora, questo qui preferirei che lo usassero solo come cambia slide, perché questo si scarica dopo un po'.
Sì, guardato, ma
Quindi-
non parlare, no.
E niente, solo questo e poi una cosa a lui che quando ha
No,
fatto...
sì,
si è messo davanti alla telecamera,
sì, io ho guardato.
e non potevo mandarlo perché veniva a fuoco lui e sfocato lui.
Sì,
e
sì,
quello era un po' un
sì,
casino.
sì, ho guardato, ma non posso... Gente lo parlano e non posso...
Tranquilla.
Sì, no, grazie
Perfetto.
mille. Sì.
Ciao. Comunque non c'è uno schermo qua davanti.
No, non c'è.
Per quello che tutti sono così.
Sì, è per questo si dice.
Sì, devo parlare dopo per quello che sono venuto, appunto. Sì.
Questo qua perché poi si scarica e non cambia più le slide.
Questo per andare avanti, questo per andare indietro. Questo sarebbe il pointer che però non si vedeva niente.
Ah, okay, so just a second. So this is for the changing the slides?
No, per rivedevo.
This is for changing the slides. This is next slide.
This is backward or forward?
Forward.
Forward,
The big
okay.
one, the middle is for forward.
Yeah, okay.
But if you want to use the laser to show better, use this one because it's stronger and they see it on the camera better. So see, this is much stronger. It's quite bigger and it's better to use
There's
this
also
one.
a laser here?
Yes, but it's very little and it's not visible on the camera.
Ah, okay.
So it's better this for changing the
Just for the
slides
slide.
and this for the pointer.
And I don't see anything here, so I just
No,
have to see.
yes.
Okay.
Yeah. Ah, sì, hi. Sorry, I was because we didn't have time before to tell the speakers, we just made the note that this changing of the slides, but it's better to not use this laser because it's very little and they don't see it on the camera. Yeah, it's better this because it's bigger and they see it on the camera. And the other thing is that when Michela was standing, there is the camera there, and he was standing just in front of the camera. And he was asking the questions and we were just so just these things that the technical guys told. And we were sitting there because we otherwise here we can also see. Yeah, but it's not like that. I have to look and It's not 10 by 10. I mean, and then there is only one on the other side who's sitting here. See there. So it's it's fine.
They're like, all right.
Yeah. But the thing is that it's better to use this as a laser because it's stronger and they see it on the camera. Because there is the live camera there that Michele was in front of it. And then this is for the slides. Yeah, but better use this for and here I don't know. I don't
Can
think
one use this? Like I haven't seen anyone like stay away from that.
But if you want to make a show, I would. Going around and now see my butt here.
Okay, thank you.
Yeah. Nice to see you in person.
Yes, we will have lunch later, I guess.
I know. I don't know where we can convene.
Manuela will
Send something around.
send something,
But I guess if not, we can meet at the booth of Nazca.
Oh, okay.
Yes.
Oh, okay. I got it. Okay. Yeah, indeed. Yeah, indeed. Sure. Yeah, indeed. Yeah. So I grab some water. Yeah.
Grazie, Fra.
Then actually you can see what kind of infrastructure you got out there. If you'll be standing there, you don't have the screen where I have.
Yeah, like then the screen is on my back or in front of me, so I need to go like this or this one. I don't know. I don't
I
also.
don't know if there's like
I don't have timer too. Is there a timer later?
No.
Oh.
You don't see the notes, the timer. You only
I need
this
to
one.
see this.
Yeah.
Okay.
You got more
Weird.
cameras than I did.
And the mic is. Oh,
Yes.
can I use that? But.
For the question.
Oh, okay. For
This
the
one for the
question.
presenter,
For
the
so I need
slide.
to stand here. I cannot stand there.
Yeah.
Okay. Okay.
Good luck.
I will manage. A bit different with the other room.
Yeah, sorry.
No worries. Okay.
Yeah, I have a screen here
I
with in
will-
actual presenter mode with
I will
timer.
start my own timer with my phone. I think I need the timer. Otherwise I will get lost.
So during the first session, the two chairs were also just sitting here because they couldn't see anything either.
Oh, true.
So I
And
think
then
they
during the
were, they
question
might have
period.
been in the and I couldn't see. And then during the questions, they came back. But they couldn't see anything from there either, so they were just sitting in the front row during the presentation.
It would be nice if I can have that. And then I will stand there. And then,
Yeah.
right?
Yeah, they
I will
watch you
just
there.
ask. Yeah, and now I will just ask if I can use. So I think it's better if I stand here. So I can see and then you can see. And then I will have pointer when I write.
Well, there's also, I think it's also on camera, so maybe the camera is then out of, I think that one is just pointed at there, so
Ah, you are a Sì, ok. Sì, scusi, mi vede fa schifo, quindi... Allora, ti volevo dire, visto che...
Aspetta, non l'ho mai fatto prima, quindi
Ok, no. Perché io sto qui per le presentazioni. Esattamente. Sono 5. Manca. Ok, è arrivata adesso. Perfetto. Prima infatti
ci hanno detto, gli hanno detto, è pericoloso dire avete fino a 15 minuti prima, ci hanno detto.
Molto pericoloso. Questo però è un sistema molto carino, perché di solito vengono da me, ho una presentazione, tieni, non ho la chiavetta, noi ci vanno là, fanno tutto e noi funziona smooth.
Ok, quindi ci abbiamo 1, 2, 3, 4, 5.
Esattamente. Pure nominati così. Sì. Perché l'abbiamo chiesto che sennò era un casino.
Quindi tu li metti su, ho visto che tutti gli viene il torcicollo perché non c'è uno schermo.
Esattamente.
Non possiamo mettere un computer lì sul collo, vero? Cioè, perché questo
purtroppo
ce n'è due, vedo, però.
Io ne ho due, però uno mi serve per... Uno mi serve per la registrazione per le camere e uno per mandare qua. Prima è Strozzi.
Sì.
Uno glielo mando così, vedete come arriva. E
Sì.
poi lì sopra.
Quindi uno deve per forza.
Esattamente.
Il microfono comunque è questo qua.
Esattamente.
Sì, non c'è un microfono portatile o questo è portatile?
C'è, però è per le question.
Ok, quindi questo tocca comunque stare qua.
Esattamente.
E quindi te devi girare un po' a destra e un po' a sinistra, così forse non ti viene il torcicollo.
Quella telecamera che inquadro lo speaker.
Sì. Ah, giusto, quindi se lo speaker si muove non
Esattamente.
funzionerebbe quella parte lì.
Esattamente. Poi l'altra cosa, questo serve per il cambio slide, the next.
Vediamo se va.
E
il puntatore?
Il puntatore devono usare questo. Qua.
Ah, quello sembra.
C'è un pulsantino.
Ah, pulsantino. Ok, quindi quello non funziona?
No, funziona, solo che usando questo si scarica subito.
Ah, ok.
Quindi poi mi si scarica il telecomando e non va più avanti la slide.
Ma io ho pensato, non possiamo parlare col microfono.
Perché poi ho quella telecamera là.
E quindi devo stare fermo qui, come Fidel Castro.
Tu sei condannato al torcicollo,
Sono
Dazio.
condannato al
Sono le
torcicollo.
istruzioni che mi hanno detto a me, quindi...
E ho chiesto anche se potevamo mettere un laptop, ma no.
Se no parlo a ruota libera, appunto come Fidel Castro, di qualsiasi
Allora, se
completamente indipendente dalle slide. Come?
Un computer, magari ve lo potete mettere qua e
il tuo
mandare
computer,
avanti le slide sia sul vostro
Sì,
computer
sì,
che...
però poi diventa un po'. Dopo c'è questo, poi c'è questo, poi c'è
lo so.
Vabbè, però giusto, almeno quello ti può risparmiare il torcicollo.
Non sono una donna, non riesco a schiacciare
Sì,
3 bottoni.
Sì, perché c'è il puntatore.
Al puntatore, questo è per fare andare avanti, poi se c'è anche il mio laptop da fare
sì,
andare
sì,
avanti,
no,
allora dopo sono
Non è il
perso.
puntatore, è proprio l'originale di Star Wars.
Sì.
No, perché questo qui dopo un po' si scarica e poi non vanno più avanti con le slide. Quindi è questo motivo.
Così è.
Questa è la sua presentazione.
Però io posso farlo andare, cioè posso puntare anche qui questo.
Sì,
quindi-
questo funziona perché tanto
funziona, sì.
lei dovrebbe puntare qua.
Sì, però comunque anche se punto lì
Sì,
funziona.
sì, esatto. Quindi lei magari questo se lo tiene qua al suo computer, preme e basta.
No, ma ormai faccio così, adesso devo vedere perché non è tanto che devo, ogni tanto non so esattamente cosa. Ecco qua.
E poi la sessione prima mi si sono messi davanti alla telecamera.
Possiamo mettere qui anche
Sì, prima
giusto per vedere le presentazioni.
Usava il microfono, poi giustamente si levava di mezzo, si metteva qua, si metteva. Quindi a me la testa del signore andava a fuoco e lo speaker andava sfocato. Esattamente.
E poi quando ci sono le domande invece i microfoni.
I microfoni ce l'hanno uno i volontari.
Ah, ok.
E uno voi qua davanti che magari se parlano questi in prima fila.
Ok, e qui c'è solo il
pulsante muta e smuta. Esattamente. Prima funziona, check.
Funziona pure questo.
Perfetto.
Ok. E posso provare anche la mia presentazione che è anche Cazzo, tu sei diligente, hai usato il template.
Come?
Tu hai usato il template, sei di lib...
Non lo so se...
Io invece ho usato DTU, vediamo se si vede. Tutto si vede, ok, va bene. Ok, va bene. Ok. Funziona tutto, sì sì. Poi...
Yes, so, okay, so yes,
And then,
one should put the timing.
okay, I can keep the time.
Yes, so I think it doesn't have to be very strict, but maybe we can somehow either communicate, I would say more than 2 minutes.
So when we're 2
3 or
minutes...
4 minutes. No, I would say.
Because we aim for 15, right?
Yes. No, it's the end 20.
Yes, but...
So, but of the 15,
time
we
for
could say 4 minutes.
If we approach 16, do we give a...
Yes. So, I think we should go there.
Yeah, and we will not
so
stand in front of the camera.
Yes,
So we can go there.
exactly. We go there, and so while sitting, if the speaker looks at you, you can. I would say for.
You can tell the speaker.
And otherwise, you have to stand out somehow.
So it's very rare that and so we do you want to introduce the points and then I take questions? I go around the questions. There are also volunteers.
Yes, I think
A bit like that.
I would say you should maybe 2 speakers or so because people take notice of you. I think it's good if you. So, for example, I can introduce the session and then you introduce the first 2 speakers and then you have the whole presentation. Yes. So maybe towards the end I will.
So I think the first 2 will take the last 3.
For example, yes.
And then for the questions.
And for the questions, I think we will go.
So maybe the one who introduces the speakers also says, okay, questions. Okay, so I think the first 2.
Yes.
And then we will take a bit of, I think a bit of notes on the way, then we...
Yes, exactly. I suggest you take notes because
Yes.
you will be there, so you understand what you wrote down and
Okay, maybe now in the, well, we have the lunch break right after, maybe we have 10 minutes in lunch break, we can put together some points.
So, yeah. Yes.
And the presenters so they should advance with this, but point with this, because otherwise this will discharge the gases. So pointer and present. And yeah. And unfortunately, one must just turn the neck. There is no other.
Yeah. For the presenter, it's bad.
For the presenter, it's bad because you have to, at the same time, speak into the mic. Deformations. Oh no. So it seems that we have done basically a grouping of natural terrain deformations. They're quite well grouped.
Find the right session. Yeah, displacements.
presenting yourself?
Yes, this afternoon. Pulsar 2, 3, barometry.
3? I thought they started 4.
ALOS 4, but Pulsar 3.
I didn't know they. Okay. I didn't know there was a mismatch with the.
Yeah, exactly. Is Tazio the first?
Tazio's the first, yes.
I saw GP pair already. So the second one I saw at coffee.
All we have to deliver their presentation. I checked with them.
Okay.
So we have all 5.
That's all 5. Okay, that's fine.
Yeah, and Guido is around. I must ask, actually, that's the name of the. Or you will be introducing the complex name.
Yes.
You will correct us. That will be hard.
So for you, is it John, Peter, Merriman, or
Merriman, Boncari,
all of them?
Or just John Merriman?
Yes. Yes, I keep it.
Flocking in. Yes, or 11 past.
Damon, we would like to sit there.
Sorry? Just
We would like to sit there. Can you
as long as there are 2
move a little
seats.
further, please?
As long as there are 2, sorry.
Good morning, ladies and gentlemen. Thank you for being back from the break. I hope the rest will also soon be here. We welcome you to the session Displacements and Deformations 2. And the chairs are myself, Urs Wegmüller, and John Merriman. And we have again 20 minutes time per presentation, and we give a warning after 15 minutes and tell the speaker that it's 4 more minutes. So we have at least a 1 minute reserve for questions.
Okay, so I'll introduce the first presenter, who is Tazio Strozzi from Gamma Remote Sensing, who will talk about regional scale assessment of slope instabilities across western and eastern Greenland using Sentinel-1 persistent scatter interferometry. Floor is yours, Tazio.
Yes, thank you very much. Good morning. As said, this talk is about the assessment of slope instabilities in Greenland. And before starting, let me thank my co-authors at Gamma Remote Sensing in Switzerland and at the government of Greenland. Thinking about Greenland, I had in mind this huge island fully covered by ice and snow without any infrastructure, so basically a nightmare for interferometry. Then, of course, if you take another projection, you see that Greenland is still considered the largest island on Earth, but its size is not that big. It's around half of that covered by the European Ground Motion Service. Then you also have some infrastructures, nice, colorful houses, but in particular you have a nice free coastline which is prone to slope instabilities. This is something which is well known, so there is evidence of these instabilities that you can see in the fields. There is an event, there are registered past events, so it already happened. What you see here is, for instance, an analysis that Handicap at the University of Oslo did with planet Earth images, 2 images in June 2017. And you see here on the right-hand side a big rock avalanche that came down from this ice-free coastline. The problem with these landslides, it's not really the infrastructures on top of them or below of the landslides, it's mainly the tsunamis that they can generate, because most of the settlements in Greenland are at low elevation, and so if there is a big rock avalanche coming into the water in the fjord system, this could generate a tsunami with potentially effects on these landslides, on these settlements. So the aims of our work, I'm sorry, here I have to turn to read a little bit there because we don't have a screen in front of us. So the aims of our work were to evaluate the feasibility of monitoring slope instabilities within different fjord systems around western and eastern Greenland using satellite radar interferometry. So the idea would be to identify potentially hazardous sites, and for the most dangerous sites to support the development of an early warning framework using satellite data. So we developed a multi-stage analytical approach. So the first step was to establish an overview of slope instability, so basically analyzing persistent scattering data over large areas of Greenland, identifying hotspots. For this hotspot, trying to characterize the activity levels. For the most dangerous site, to concentrate on the deformation patterns, to try to reconstruct the history in the last 10 or more years, and then for some of those also implement a kind of data portal where we have a near real-time updating of information. So Greenland poses certain challenges for interferometry. So it's 85% of it is covered by ice, but we have also a long-lasting snow season. So for several months, you see here on the right side the results from 2 ground stations. We have the presence of snow cover. So basically there is a short period in the summer where we have snow-free acquisitions. Then we have a mountainous terrain, narrow coastline, deep fjords, towering mountains, tidewater glaciers, so we have all problems of layover, shadow, poor offline sensitivity. We also have disconnecting islands with this fjord system that we have to try to connect. And ionosphere might also be more severe at polar regions than to mid-latitudes. So what you see here is actually, it's not a sentinel image, it's a nicer image on Svalbard, the one I could find quickly to show you some ionospheric effects. But the problems also with ionosphere, with snow, with water is also the co-registration of the sentinel images. And in some cases, you have this, you see jumps of phase in the burst. Okay, so regarding the processing, the first thing to say is, over Greenland, you have a very rich archive of Sentinel-1 data. So because of the ice sheet monitoring, all the areas were covered with a very good number of images. It's not always ascending and descending data that are present, but we have a very dense number of images. What we do is single reference persistent scatter analysis. You see on the top right a plot of baseline versus time. And the second thing to say, it's also that it turned out that the snow is, so the snow-free season is really snow-free, that there is really a winter season with snow and a summer season without snow. What you see here is a point coherence computed for one of the sites. I don't remember the parameters that we use, but basically by choosing a threshold on this coherence, you can quite reliably detect the snow-free and the snow cover images, and so you can concentrate on the summer images without snow cover for your processing. Another thing that turned out during the processing is actually the troposphere is not a big problem there. So you see there at top left an original point target interferogram spanning maybe a couple of years with the atmosphere. If you just compute a simple phase-to-A relationship, you can remove most of the atmosphere and you don't have a lot of turbulences. So really, you can also expand your network to connect these islands because the atmosphere remains quite the same in these different places. You might have some ionospheric effect. I'm not 100% that the one you show in the bottom line is a ionosphere, looks like. On the left again with this high dependent atmosphere, on the right without, but it's a very large scale signal as well. And we are interested in small scale landslides that can be also filtered out. So basically, what we did at the beginning was to focus first on some small areas because we were not quite sure about this, the processing, how it will turn out. Those are 3 areas that we analyzed with our first analysis. It's about 20 by 20 kilometers, and the processing turned out to be very robust, so we could achieve quite good results. You see here the mean velocity map with a color scale up to 1 centimeters per year. There are some nice signals that you see, for instance, here or here, that could be detected over these areas. And so this gave us more confidence in our processing. These are the 3 areas that we analyzed at first. One north to the capital of Greenland, Nuuk, the other one on the north of Ilulissat to here. And taking into account the good results that we could achieve with this processing that was first focused on small areas, we could enlarge it to bigger areas, so on the order of more than 100 kilometers. So we did all the fjords around Nuuk. We did the fjord around this settlement on the east of Greenland, Tasiilaq, and now also on the north of Ilulissat. So when you enlarge it, then you get more into computational problems maybe, the data set get large, processing time get more longer, but actually from the persistent scattering point of view, the processing is very robust. And now let's have a look at some of these results. On the left, you see Disco Island and some of the fjords on the north. You see all these red and blue points indicating the motion. And what the geologists at the government in Greenland are doing is to identify the unstable areas. And they made a differentiation here between these 2 yellowish colors. One is related to potentially tsunami, related slope instability, the other one without any danger for a tsunami. What is also indicated in this map of unstable slope is the registered mass movement, so the events that already happened in the past. So zooming in on one of these areas, you see on the left our PSI results, on the right the interpretation. So you see, for instance, here all this reddish area, they were mapped here, like tsunami potential, slope instability. This, for instance, falls into within an area where a past event already happened. You have other areas, like here, where you see instabilities where nothing was happening before, and you also have some unstable slope up here where we do not, or some past events up here where we do not see any motion in our analysis. Looking into time series for one of these, the most prominent landslides, here the color scale is changed to 2 centimeters per year, so you see different sectors with different motion. There are also a lot of periglacial processes going on, and some time series, of course, the time series, because we consider only the summer data, they are not as nice as some of the others you have seen in other areas. You might recognize maybe changes of velocity during the summer season, but filtering this data set is more difficult, so it's not that easy to see changes of velocity within this time series, because as I said, there is a long period without information from the snow-covered area. And if you take a single reference and you jump over several years, then the interferogram, they're basically decorrelated. This is another area, so you don't see only slope instabilities, you have also some periglacial effects. This is, for instance, a big rock glacier complex that you see here. There are some others here, and there are also some areas without any information where a slope instability was detected. So this is, as you know, we might have in the cases of interferometry, some data gaps. Where motion is too fast for our kind of analysis, then it turns out that we don't have persistent scattering points. And I concentrate here close to the settlement of Ilulissat. So this is a town which is built here on rocks. And when you do the persistent scattering analysis, you get a lot of points over the rocks, so the stable areas. And here within, with this kind of analysis, you don't have any information. But if you consider a sort of interferometric baseline approach that you take all the interferograms within every season, so every time we start, every year we start from the beginning where the snow disappears, and then we compute a time series until the end of the season when the snow appears again, then you can see this motion relating to the thawing and freezing of the permafrost. So this is a soft layer with ice, which every summer smells, so you get the ground going down, and then in the winter it freezes again and it's going up. And here, if you see the scale, we are talking about centimeters per year motion, if you transform it from the summer motion to the yearly motion. And here, you have these two kinds of products that they can somehow mirror the Svalbard ground motion service. So you have a mean annual deformation rate over several years, and then a mean seasonal deformation rate. Going to one of the most prominent landslides, Atta, which is shown here. You see here a registered event here. There's some red points, some blue points. There are some areas which are missing. This is a very active area where the interpretation of the persistent scattering analysis is quite complicated. If you take a time series, you see there was some motion and then maybe some noise and then again some motion, but would say this is basically wrong in that sense that a big event happened in 2021. There was a rock avalanche, and this is a little bit pushing the technology to its border and trying to get as much as possible of information. So you see this is an active area, you have a lot of motion, you have some information which is missing, but probably PSI here is not the right technology to use to identify, not to identify, to monitor the displacement. So it can be used to identify the areas where there is motion. If you take the real motion monitored by other technologies compared to PSI, you will have some discrepancies. And what we do here is actually to consider interferograms. So here we have a series of 6 days interferograms spanning from 2018 to 2026. If you concentrate up here, to the scarp of the landslide, you see maybe half of a fringe motion in 6 days in 2018. Then it's one fringe in 2019. It's several fringes in 2020. And in 2021, during this period, there was this big rock avalanche, so everything is decorrelated. Now in 2026, you see that the scarp here is stable. We see the signal down on the deposit of the landslides, which is still moving. On the other areas, like here, we have similar signals that we had in 2018. And at the end, we also show a one-day interferogram, which is nicely showing the signal of the deposit, another signal like here. So this one-day interferogram, they're very nice to see the very fast-moving areas. So coming to the conclusions of the talk, from the geological point of view, so the geologists at the government of Greenland, they made an interpretation of this motion, and this helped them to prioritize detailed analysis and also field visits. You can imagine doing a field visit in Greenland is quite complicated, and so if you can prioritize, you can go to the sites where you know something is going on, can help their work. From our processing point of view, we really demonstrated that PSI is working. Despite this long winter and the problem I mentioned at the beginning, we are getting a robust processing chain, which can deliver useful information. We know PSI is limited when velocities get larger, and in that case, we can use interferograms. And here I put on red. I know it's not possible anymore to get one day, but the recommendation for Ms. Luisa is to really highlight the benefit of this data. To remember, they're very nice, very good, and we can see a lot of information on those. And what we want to do in the future is to expand our analysis to progressively cover all the coastline of, or the ice-free coastline of Greenland, which is on the order of 4,000 square kilometers. Just to compare, the European Ground Motion Service is 4 million. So it's large, but it's not that huge. And having said that, thank you for your attention.
Thank you, Tatsu, for the interesting presentation. We can take some questions.
Hi, thank you. So that's really interesting to see all these patterns of deformation. I'm not sure if you mentioned it, but did you have issues trying to align the referencing in this area? Did you have any external controls on that, or was it all relative?
You mean the reference point?
Yes.
Yes, basically everything is moving, yeah. And then, yes, it was a little bit try and guess. I would say there is some outcrops. And then there are some many outcrops. So basically, you somehow deterministically try to find a point which is moving or which is not moving compared to other points, and all the other are moving. But yes, in particular in some, so we process this in batches, and some of the batches, it was difficult to find a stable area, yes, for reference.
Other questions?
Hi, so thank you for the presentation. I just have a question about the choice of single reference processing. Because in your case, if you are looking into fast movements, by taking single reference, you are limiting the short-term interferograms. This way, you know for sure that you will not see the faster movements.
Yes, that could be also a possibility to expand the analysis, as we did in Illulisat for in some other areas. You can just process the summer data. And the idea behind using that is that we didn't have many images in the summer. And so by taking the single reference and going over many years, so you can get a robust number of images to do the processing. But I'm sure there are also other possibilities to do processing. As I said, what came out here is a very robust processing chain that we can apply all over Greenland. And then once the product is out, then we can think about other way of processing the data. This is also what we plan to do for these specific sites where there is more hazard.
Other questions? No, I maybe have a quick one, Tatsu, myself. You mentioned that there are PSI, seasonal SPAS, single interferograms. There are different motion rates. Maybe several of these results could be interesting for an end user trying to say something about the hazard in these areas. How would you suggest, let's say, presenting these results in a homogeneous way to an end user? You can't give them a wrapped interferogram, I guess. How would you...
If they're trained, yes. You can also give, I mean, if you're really interested into the fast motion, and then I would say this kind of interferograms, this is also what the end user are trained to consider. And if you try to unwrap the 6 days interferogram, you always come into issues. You have to learn it, but I think it's for the most hazardous sites, that's also a way to train them and to show them. So we are always in favor of interferograms. But as I said, the starting point was doing the persistence scatter analysis where you have more quantitative data.
Okay, so we must train the end users. Thanks, Tatsu.
Thank you.
So we move on to the second talk, which will be given by Gideon Baer from the Geological Survey of Israel, who will talk about immediate and multi-year consolidation at a retreating shoreline, evidence from high-resolution INSAR at the Dead Sea. The floor is yours, Gideon.
Thank you. Good morning. So we make a small jump of about 40 degrees in temperature and go down to the Dead Sea. The level of the Dead Sea has been dropping by about 40 meters during the last 50 years. And due to the consumption of water by neighboring countries in the watershed of the Dead Sea. And in this talk, I will focus on 6 years of water level drop at an average of 1 meter a year. I will first describe some features of shoreline retreat and subsidence, then show measurement of the immediate, seasonal, and long-term response to the level drop. And finally, I will discuss some subsidence mechanisms which do not appear in the title nor in the abstract because they were done just in the recent months. So two types of subsidence are well known along the Dead Sea. The first are related to the sinkholes. They occur either before, during, or after the sinkhole formation. And they are more circular in shape, concentric. And the second type is a shoreline subsidence, which has attracted less interest because of its less hazardous, or assumption that it's less hazardous, but it's really conspicuous, and you can see it. They're separated in space, but in some places there are also sinkholes along the shoreline. So it is important to know how to distinguish between them in terms of hazard analysis. The data we use is TerraSAR-X images, 11-day acquisitions. For DM, we use LiDAR, airborne LiDAR, at 1-year acquisition, 0.5 meter pixel size, and we are doing the processing by Gamma software. The data is similar to the data that we have been using for the sinkhole monitoring and early warning, which has been described in previous talks. So the best place to demonstrate this level drop is at the southwestern corner of the Dead Sea, the Tse'elim Bay, which is marked there in rectangle. And until recently, it was a bay which was connected to the main body. So this is a picture from 2020. At spring 2024, the sill between the bay and the main Dead Sea water body was exposed, and they began to become disconnected. The water was flowing from the bay into the Dead Sea, and currently they're totally disconnected. So before the disconnection, there were one water body. The level drop of the bay and the Dead Sea was similar. And as you see, the shoreline subsidence is also continuous and similar in the bay and the Dead Sea. But immediately after the two were disconnected, the level drop of the Tse'elim Bay was slightly lower because of influx of water into the bay, which, and therefore the level drop was lower. And immediately we can see that the shoreline subsidence in the bay is almost non-evident or smaller than the one along the Dead Sea. Another way that we can see the immediate response is after flash flood. This image shows the 2024 satellite image. And in December 2025, there was a big flash flood that caused discharge of enormous amounts of water into the Tse'elim Bay. They broke the sill. The sill was breached by the water, and the water from the bay was drained to the Dead Sea for the few days. If we look at the interferograms before the flood, 11-day interferogram, then the subsidence was almost similar in the bay and in the Dead Sea. But immediately afterward, the next 11-day interferogram, we see significant subsidence in the Tse'elim Bay and no subsidence in the Dead Sea. So this is an immediate response to the level drop after the flood. So in order to quantify those processes, we carried out tens of shore perpendicular profiles along the entire Dead Sea shoreline, marked by white lines. I will focus on two areas, the Tse'elim and the En-Gedi area, and at the final stage, I will show some more profiles from other areas. So let's look at the first profile, the A-tag profile in Tse'elim. These are 33-day interval interferograms, profile of subsidence from the area which is not subsiding to the shoreline. And we can see by the red colors are the warm months, the hot months over there, the summer months, and we can see that the subsidence is significantly higher in the hot months and low, very low in the winter months. So there's a clear seasonal effect of subsidence in this area. And if we look at September profiles, we see another feature, which is the retreat of the shoreline. And we can see that the area of maximum subsidence, the shoreline itself, is migrating northeastwards, and the maximum subsidence also migrates together with that to the northeast. If we take the point that was on the shoreline in 2019 and measure the subsidence at that point during the year, we can see that the subsidence at a certain point decreases with time. So the next slide will show two time series, one of the shoreline one, which is migrating, but the maximum subsidence, and the second one will be the fixed point of the 2019 shoreline. So on the left is the shoreline, the maximum subsidence, the migrating one. We see the clear seasonal effects, maximum subsidence in the red, it's the subsidence. In the blue, it's the changes in the Dead Sea water level. And so during the summer, the subsidence is maximum, and the rate in water level drop is also maximum. And in the winter, it's minimal. Both of them are minimal. In places, the water level even rises. In one of those winters, the water level even has risen. And on the right, we see the fixed point subsidence time series. Same seasonal effect. We also see that the amount of subsidence decreases with time towards the later years, which doesn't happen so much along the shoreline. To see the lag, or to try to calculate the lag between the two, we use the cross-wavelet transform. In this case, the horizontal axis is the time. The vertical axis is the period of common behavior between the two time series. And the power, the colored bar marks the power of common behavior of the two time series. The red contour marks the significant level above noise. And the arrows show the phase differences between the two time series. So vertical means that they are in phase, vertical downward, the opposite phase, and quarter phase to each side of the horizontal axis. And we see that and the maximum lag is marked in the point with the X, the white X. So we see that for the shoreline, the lag is very, very small. On average, it's a few days, and it's really non-significant. So they are in full phase with each other. And the fixed point one also lags very minorly, a little bit more than the maximum subsidence, 9 days of lag between the two time series. Now let's go to the other one, the Engedi profile. On first sight, we already see that there is no seasonal pattern. The blue and red and green, they all have the same magnitude, and there's no change in subsidence along the shoreline throughout the year. We also see that there is no migration of maximum subsidence like we saw in the previous one. And if we look at the cross-wavelet transform, we see that the shoreline subsidence shows some seasonal variation, low seasonal variation. The lag is 20 days, and the fixed point plots do not show any common behavior. So they are not in phase, and they are not even within the significant contour of above noise. So the power is high only due to one of the two data sets, but not due to the other one. So now let's try to understand what could be the subsidence mechanisms. There are three basic mechanisms that could cause subsidence along the Dead Sea. The first is consolidation. It is occurring mainly in fine-grained sediments, clay, silt, marl. When water level drops, the pore pressure decreases, there's increase in effective stress, there's a time-dependent expulsion of water, and consolidation. And the equation relates the settlement to the thickness of the layer, the compressibility index of the layer, the void ratio, and the stress changes due to the water level drop. The second mechanism could be elastic compaction, which occurs in coarse grain sediments, sand, gravel. The water level drop causes stress change, elastic strain between the grains, instantaneous drainage of the water, and compaction. And the process, I forgot to mention, the consolidation is decelerating with time, as we saw before. And this process is semi-linear. It's depending on the stress changes, on the thickness, and on the Young's modulus of the layer. And the third process is caused by surface dissolution. It requires soluble layers like salt or gypsum. The ground level drop causes replacement of the brine with fresh water, which dissolves the soluble sediments, and then the gradual sediments occurs above the growing cavity. And this process is shown to be accelerating. There's no single equation that describes it, but it has been shown to be accelerating in time. So let's go to the two areas that we saw before. First with Selim. The Selim area, the nearby boreholes show that the sediments are intercalations of clay and salt. And so we try to use the consolidation theory to model this subsidence. In blue, we see the measured subsidence, the cumulative above, and the incremental month by month at the bottom. And in purple, we see the predicted one by the consolidation using those parameters that we already have from previous studies along the Dead Sea. And we see that there is a good agreement between the subsidence and the predicted subsidence for the both for the cumulative. At the bottom, we see actually average subsidence of the four Selim profiles. So the predicted one is well within the standard deviation of the four profiles, four time series. On the right, then Gedi, the nearby borehole shows that we are in an area of 100% gravel. And so we try to model it with elastic behavior. Using the lowest Young modulus that we can afford for very loose sand, gravel, we still see that while the measured profile is accelerating in habit and much larger than the predicted one. The predicted one is semi-linear, but it is much lower, both in the cumulative and the incremental plots. So we go back to previous studies and see that in all our sinkhole precursory plots, curves, we saw the accelerating habit, which is really prominent, both in observations and in simulation that we have presented also before. So we might think, or we might conclude even, that some of the subsidence along this profile could originate from salt dissolution. We see here the two types of subsidence, the one that's related to sinkholes that are marked here in white, further to the west, but still we can see that there is already one sinkhole at the shoreline north of our profile, so maybe this indicates that we are dealing with some kind of contribution of salt dissolution at the subsurface. So adding some more data, we can divide our time series into three categories: the decelerating, the semi-linear, and the accelerating, and may use these patterns to identify the three different mechanisms: the consolidation, the compaction, the elastic compaction, and salt dissolution at the subsurface. So, to summarize, we've seen first that the shoreline subsidence responds instantaneously to the Dead Sea level drop, really instantaneously, as a matter of days. The main subsidence mechanism that we were dealing with was the consolidation of clay-rich sediments elastic response of alluvial material, and dissolution of subsurface salt. And it is very important to distinguish between the three mechanisms, and we can do it by INSAR because it is crucial for hazard assessment along these highly attractive shorelines. And you can see how highly attractive they are. They are very, very much toured by groups and by individuals. And our goal is to try to delineate the areas that are really hazardous for sinkhole, by these methods for sinkholes. Thank you.
Thank you, Gideon. Are there any questions?
Okay, thank you very much. Very interesting topic. And I have questions about, you mentioned there's a multi-layer of mechanisms, different mechanisms. So did you apply like the independent component analysis to decompose the different deformation resources from the INSAR data? Or is that they were mixed together, the different mechanisms of the deformation pattern?
Yeah, they were actually done separately, using basically starting with the known parameters and then trying to change them in order to fit the curve within the limitations of reasonable coefficients. So finally they were fit to each other in for certain values, but they were done separately.
Okay, that's it. Thank you very much.
There's a question down here.
Thank you. On one of your first slides, you mentioned something like sinkhole monitoring. Is this a dedicated system or database or something? Are you doing some special processing or some additional data for that?
Yes, this is an early warning system that was, we were asked by the government to form an early warning system. It is Runoff who is taking care of all the processing, and we're just doing it, currently we're doing it manually. We are using this data to delineate areas of subsidence, and during the time, subsidence that changed into a sinkhole is marked in a different color, and it's open to the public, and it's used by the public, it's used by the authorities and by the road construction authorities. And so this is already in operation for the whole time between 2018 and now.
Okay, thank you.
Should move on to the next presentation.
So the next presentation is on the future of sinking coastal cities in Java, and it's presented by Holly Howerston and colleagues.
Right, hello everybody. My name is Holly Hurston. I'm an Earth observation scientist at the British Geological Survey, and I'm here at my first Fringe presenting some work that we've done with our colleagues in Indonesia, which are listed up on the board behind me, about the future of sinking coastal cities in Java. And so we're going to be talking about subsidence, but also about sea level rise and what happens when we're dealing with these two hazards at the same time. So in case anyone needed to know, this is Java. It's one of the largest islands in Indonesia and one of the most populous island as well. It's home to its capital city as well, of Jakarta. So we've got this presentation is going to hopefully outline kind of this tale of two geohazards that we're thinking about, this subsidence and also flooding and sea level rise as well. So Indonesia is rapidly growing in terms of its population, which requires rapid urbanization to keep up with the people and the demands of the people who live there. So here is an example of how we have increasing rates of subsidence and increasing extents of spatial subsidence as well, from population growth, requiring more infrastructure, requiring more water, more materials are needed, more groundwater is extracted, and therefore we get more subsidence. But what happens when we're thinking about climate change separately? We get more sea level rise, more frequent and more severe storms, leading to more coastal inundation and more flooding as well. both of these things can compound together as a multi-hazard to make an already vulnerable population to both of these hazards even more vulnerable to this combined multi-hazard system. So this is something that I just wanted to go over quickly before getting into it, because I work on loads of different geohazards in my job. And so lots of people that I meet usually think of are like one hazard specialist. And a lot of what we do is actually thinking about multiple hazards at the same time. So here's kind of infographic that I've made in PowerPoint animation to show that sea level rise, if you think about it from 2026 until in 75 years' time, at worst, I think in some parts of the world, it's going to be around 0.8 meters. So this is a problem, obviously, if your land is static. So we talk about sea level rise, but then if we need to talk about relative sea level change, this is when the subsidence comes into play in the vertical line motion. So if your house is also sinking and you also have the sea level rise on top, then the combined sea level change is actually much greater than what the sea level rise alone would suggest the flooding and the inundation will be. So the current state of knowledge, I had a quick Google on Google Scholar, and I just typed in Indonesia subsidence INSAR, and 2026 alone, there's been 330 papers already this year, which is quite impressive. So it really shows how big and how much of a point of interest this topic really is. It's already highly exposed to coastal flooding, but also loads of other geohazards as well, and tsunami hazards, for example, which is where this picture is taken from, tsunami inundation. And most regional studies only look into sea level rise projections alone when they talk about people who are exposed to flooding hazards, but it doesn't often talk about the subsidence, so you're underestimating your risk. So as multi-hazard scientists, what we want to know is who's exposed, where's vulnerable, and where's the combined risk. And most of these answers can be found in your 330 papers on Google Scholar. But what we're doing or trying to contribute is what's going to happen in the future, or what could happen in the future, at least. So we're going to do that by looking at INSAR, but also other data sets as well. So firstly, we made an INSAR deformation map. So we used C-band Sentinel-1. I won't spend too much time on this because I want to get into the population metrics and things that we've actually found, but we made our own deformation map to use using LIXAR system, and then we multi-looked it to 500 meters resolution, just because we felt with the ancillary data sets that we had, 500 meters would maybe work, but this does mean that we have lost some spatial resolution. This is how it looks. One thing I want to explain that I think the figure up, the top figure 8, is a little confusing, is that the current coastline is actually the really thin outline of the island. That's it right now. And the thicker line is a 50-meter elevation contour, which we've selected to highlight where the low elevation coastal zones are in Java. And you can see that it's kind of picked out most of the northern coast, which is quite flat in Java. But it also happens to be where most of the population lives as well, which is highlighted. You've got Jakarta, Semarang, Surabaya pointed out on the map as well. So then we can start thinking about the exposure right now from our INSAR time series. So we've taken in geological maps, a DEM, the land cover maps, building locations, and populations, or current populations, histories right now for the last 20 years. All of these data sets are open access. And we also resampled all of these to 500 meters to match our INSAR grid. So this does mean that anywhere that there isn't an INSAR measurement point, we don't have ancillary data matched to it. So most of our population estimates that I'm going to go over are an underestimation of the real picture. So this is a nice little box plot we made to highlight where on average has the quickest subsidence. So we see immediately this area called Demak points out, which is just to the east of Semarang, and the city of Pekalongan as well is pointed out as having the quickest subsidence rates from our deformation map that we've made. And I've also put the population in a color bar up here as well. So you can see, so like Jakarta kind of Jakarta regencies are coming up between Demak and Pekalongan. So you can see they're like bright yellow, lots of people living there, but the subsidence isn't actually that extreme currently in Jakarta, which is interesting because it still gets an awful lot of media attention, I think because it's such a massive city. But yeah, these other cities are actually maybe more deserving at this point in time of our interest if we're interested in subsidence. Okay, yeah, so we've also calculated that around 62% of the exposed population that we've matched to our INSAR grid is exposed to any kind of subsidence at all, currently. And also 58% of buildings, so yeah, like 2/3 nearly of the population in the low elevation coastal zone is experiencing some kind of subsidence right now. And this is just showing the proportion in terms of area of each regency in the low elevation coastal zones that are experiencing different rates of subsidence as well. So the dark blue is more extreme rates of subsidence, more rapid subsidence. And the lighter blue is more like stable to low, anything subsiding within 1.4 centimeters. So again, you can really see that Pekalongan and Damak are pointing out. So not only are they the places that are subsiding the most on average, but they're also lots of the area it's happening quite widespread in that regency as well. So it's not just hotspots that are subsiding really quickly. It's not random measurement points that are subsiding really fast. It's actually the whole area. So how are we doing for time? So what does the future have in store? This is the question. So we're going to say projecting. We're not predicting. That's an issue that we run into a lot. So we've combined our present day subsidence rates with sea level rise projections. Up to 2100. We're going to look at the worst case scenario, which is a high greenhouse gas emissions and high coal reliance scenario, which in Java, according to our open access datasets, is expecting to be around 0.73 meters by 2100. And then to predict the population, we've used the shared socioeconomic pathways, or SSPs as I might call them, which actually provide 5 population estimates for 2100 every 10 years. 5 years or 10 years, I can't remember. But it's linked to the IPCC climate change scenarios. So it takes in whether your population is projected to grow in a sustainable way, or in a way that uses lots of green energy, or in a way that's maybe less sustainable. But yeah, the important caveat here is that we assume that current subsidence that we've measured from our INSAR time series is constant until 2100. This is not... It's not true, because like you're imagining infinite subsidence in this case, and every material will have some kind of maximum compression point, but this is something that we're dealing with in the second part of the project, and if you'd like to speak to it, the project lead is right there. So you can annoy him with your questions. So yeah, so here we've got, for 2100, the elevations below sea level, just according to sea level rise. It's pointed out in these blue. It's mostly to the east of Jakarta. But the red area are areas that could go below sea level when you only take into account the land subsidence that's occurring as well. So thinking about these two things together is quite important. So yeah, this Java's been studied for quite a long time, and its subsidence, because it's got such a massive population, it's a point of interest. So these are some rates that were found in a paper published in 2013. And we can see from the INSAR gathered 15 years later that Jakarta's decelerated by quite a considerable amount, which is pretty good for Jakarta, right? But it's bad news for other places like Pekalongan, unfortunately, which has accelerated. It's nearly doubled in its subsidence rates by median average. So in the case of Jakarta, we can see that it's not an uncontrollable, inevitable geohazard. It's something that can be mitigated, and you can put in policies that work. But yeah, this is the importance of also like looking at a country as a whole as often as we can. And our results are also kind of consistent with more recent regional and city scale studies that have been published in the last 5 years, which is happy for us to see. But these future predictions, these are kind of harder to validate with other papers, because yeah, I haven't been able to find too much on this. But these are our projections for different socioeconomic pathways of development. SSP3 is actually the worst case scenario. I don't know, in my head I think it should be 5, but the way that it's structured in the paper, SSP3 is like the highest greenhouse gas emission. You can see its population has completely spiked. And this is the population that will be exposed to the combined relative sea level change by 2100. So yeah, this is obviously, it's still an underestimation because of our INSAR coverage limitations, but I hope this can demonstrate that the variability that is still possible. So yeah, it's not it's not a doomed hazard. It's something that we can do something about. I'd like to highlight some specific results from Pekalongan to further demonstrate this point. So Pekalongan as a city is projected to sink by up to 6.8 meters just from our INSAR analysis. But when you consider relative sea level rise, it'll sink to 7.5 meters. So this is quite an important distinction if you're trying to build mitigating measures. This actually happened in a town near where I grew up in Scotland, where they built like a flood wall, thinking that it will handle a 1 in 100 year flood event fine. And then a flood happened and it completely was underestimated. So these things are really important. And also Pekalongan is a UNESCO creative city. It's a huge textiles and textile design industry. So it's not just people and infrastructure, but it's also like culture as well that we, I think as scientists, have like quite an interesting role in being able to help protect. So yeah, as I said, a couple of caveats and limitations of our approach. The C-band INSAR from Sentinel-1 over a highly vegetated area, obviously, does not have ideal coverage. And also our methodology relies on INSAR measurement points to match with our rasterized population, and therefore our predictions are a vast underestimate. So we have potentially twice as high, twice the number of people exposed to this hazard as we're saying right now, and up to 4 times higher for the buildings as well. This is just due to how we rasterize the data. Okay, so our next steps. We're thinking about doing some further investigation into the current and short-term effects of urbanization. This covers like material consumption to ground loading and geotechnical models, that kind of maximum compression. This would be really difficult, obviously, to do for the entire north coast of Java, but you've got to start somewhere. So how much subsidence is actually really possible, and then build this back into this framework which we've outlined here. We also want to look into what role is local construction material demand playing in the subsidence. You know, if you're building loads of new places, then you need sand, you need ground loading sediments, and that groundwater extraction as well. How is that going to change? Where are they going to get the water from to build all of these things and make concrete? We want to repeat analysis with different wavelengths of SAR to hopefully increase our coverage as well, and reduce that kind of issue that we were having with 25% coverage. And yeah, hopefully expanding this study to other cities. I think first on the list is Kuala Lumpur in Malaysia. So overall, the main kind of points that we want to go over is that in Pekalongan City, 1 million people may be facing forced internal migration by 2100. This is under like the worst case climate and the worst case subsidence scenario. The number of people exposed to flooding due to relative sea level change increases by 6 times as compared to the figures when we ignore the effects of subsidence. So it's really, you cannot think about flooding if you don't think about subsidence as well. Our results should be interpreted as a minimum exposure estimates rather than exhaustive counts. And yes, these coastal megacities are continuing to grow, not just in Indonesia, but all over the world in every low elevation coastal zone. So integrated multi-hazard assessments that take in climate-driven data, but also geological data are going to become incredibly important for safeguarding livelihoods, infrastructure, cultural heritage all across the globe. So I'll leave this up, but that's me done. Thank you very much for your attention.
Thank you very much for an interesting presentation. So we have plenty of time for questions. So maybe I can start with a question. You mentioned compaction as the process that causes the subsidence. How much is this related to the management of the water, like pumping groundwater or using too much of the surface water that it doesn't go into the system?
I'm not personally too sure. I'm more of like the data, EO data analyst rather than a geologist, which feels quite bad considering our work at the British Geological Survey. But yeah, I'm sorry, I can't really answer that question.
Yeah, I ask because to mitigate the effects, of course, that's where you can somehow become more efficient.
Yeah, definitely.
Better using the data, like
yeah, definitely.
The water. But
I think what we can hopefully do is provide the data and to the government, and they can make their own decisions. Mm-hmm. But yeah, I mean, it's a really hot topic right now, and all of our partners in Indonesia are hopefully speaking with the relevant people, and they'll know better than I do as well. But you would hope so, yeah.
Mm-hmm. Thank you.
Yeah, thank you for this nice talk. So, I mean, regarding this subsidence, cumulative subsidence that you presented, so yes, I mean, we see that some areas is decelerating, and then so it helps for sea level, but there is also another type of flood, riverian flood, and then all this cumulative subsidence, will lead to, it will increase flood depths for those kinds of floods. I wonder if you will consider in future these aspects in your analysis?
Yeah, so for the second part of that project that I mentioned, we've got some groundwater and flooding experts working on the project with us now at BGS and in Indonesia as well. So that is part of the plan, to integrate that, yeah.
Yeah, we have one more question.
Yeah, hi. As a concerned citizen, because I live in Java.
Okay.
I want to ask, actually it's similar with the first question, like, are you also looking into the driving factors, what caused the subsidence in that different cities on the coastal of Java? And also I'm interested because you show in your slides that there is a deceleration in Jakarta. And do you also look into what triggered that deceleration? Maybe probably other city can learn from that. And yeah.
So this kind of whole area of study at BGS has been going on longer than I've been working there. But a paper and a research student that we had a couple of years ago looked into, for example, trying to disentangle subsidence in Bandung, and found that that could be tied to the textile industry, extracting groundwater for textiles. So we do have capacity and capability to kind of start disentangling those things. Obviously, having Indonesian partners is absolutely key to being able to do that. And then, sorry, your second question was about Jakarta, yeah? Yes, so I would hope it's due to better groundwater management policies kicking in. I don't actually know. Do you know it? Does that seem right? Yeah, I'm getting nods. So, so it's a nice example that policy can work.
Thank you.
Cheers.
So thank you again. We have time for one last question.
Thanks. So the DEM will have some uncertainty and some bias in it. Do you know how much that will influence the uncertainty of your population exposure projections?
I don't have a value of how much in my head, no.
Okay.
Unfortunately. I know that the vast majority that the INSAR's picked up, obviously, the city's the best, which is where the majority of people live. But yeah, you're absolutely right. Like, we don't want to miss out on rural populations either, because they'll be facing a different set of hazards and vulnerabilities to people living in Jakarta, for example. So yes, you're correct. I think uncertainty analysis would be a nice thing to include here.
So thank you again.
Thank you.
This brings us to the fourth presentation on upscaling INSAR-derived displacement parameters over agricultural land using multi-frequency SAR by Justis Lumban Gaul.
That's me. Okay. Hello, everyone. I hope you are still with me in this room in these critical hours. So today I want to start the presentation by giving you like the end goal, like the idea of the end goal. So our study aims to, as you can see from the title, so it's about the displacement parameterization. So we want to have a set of parameters that can describe the relative surface motion on a particular field, in this case, either in soft soil. So if you have that set of parameters and you make the realization, you can have something like this. So as you can see in this plot, you can see that the black line is the relative elevation changes over time, which it actually comes from two components. So if you see the gray dashed dot lines, it is the reversible component, and also the gray dashed lines are the irreversible component. If you sum them together, and then you get the black lines. And you see that for this plot, it represents one peat grassland parcels, and you can see the seasonal variability, where during summer it has subsidence, and then in winter we have seasonal uplift. But then, as I mentioned before, that this plot comes from a certain parameters that we call spam stand. So in this case, I'm not going to explain about the spams itself. I guess you can look it up in the Google or something. So, but the spams is the descriptive displacement model. So in this case, we use spams as our displacement model, and 10 is the number of parameters. And this number of parameters includes the displacement parameters and also the variance and covariance matrix of that parameters. Together with these spam stands, we can make a realization of this plot. And then, for example, if you are interested in the annual subsidence rate, then you can also estimate that annual subsidence rate from these spam stand parameters. And then you can create a map, basically like something like this. And then you have an idea of the displacement in your area of interest. And in this case, this plot comes from only using Sentinel-1 and in the pit grassland area. And as you can see, this is still not final because we still have areas where we don't have estimates. And that's what we want to do now. We want to try to expand our area to estimate more parameters in the other fields also. So if we reflect back to the problems with Sentinel-1, we have the phase ambiguity problem or cycle slips. If we see in this plot, this is a true data set from extensometer in one side. You see the lines is the daily extensometer readings. And if we resample those data into 6 days following the Sentinel-1, you actually see in the brown dots plot. But actually, and there is also like in a certain periods, there is this high jump in the elevation only in the 6 days interval. And if you have the wrap, if you wrap them, actually the brown dots will lie in the blue dots. So in this case, it can be easy to make a mistake in our estimates. And what makes it worse, actually, our measurements are noisy. So if we just inject a noise in this measurement, then we have the red as the simulated measured wrap phase in this case. So, and then second, we have loss of log. So loss of log is the permanent decorrelation. So we have a permanent coherent loss. So in this case, the first coherent segment and the second coherent segment are disconnected completely. So we don't have, and then we don't know what happened in between. And then it makes a problem because when we do the estimation also, we have an unknown shift during this loss of log events. And then what makes it worse is we don't know the truth, but actually, in fact, we won't always know the truth. And also, if you want to expand to the arable areas, then actually we have more frequent of this loss of log event, and also it will be harder to estimate our displacement. So in this case, maybe we look into other wavelength SAR missions as a complementary of the actual existing one. And we thought maybe L-band is a good option. So if we look at the same plot but using L-band wavelength, actually those measurements are within the wavelength range. So in this case, we have fewer ambiguity issues, and maybe it can help us to better estimate our parameters. And then let's go to the mission summary. So in this case, in this study, we use Sentinel-1 as the C-band, and then SAOCOM as our L-band data. So, but they have different frequent repeat cycles. So in this case, for Sentinel-1, we use everything. So we have 6 days interval or 12. And for SAOCOM, although they have A and B, but we only use one constellation, so we only have the 16 repeat cycle. Now, since the coherence is the main condition of interferometry, we want to check first and compare these coherence estimates between C-band and L-band. In this case, the area of interest is 20 by 20 kilometer in mostly covered by croplands. What you want to see is the daisy chain coherence estimate. So it's a pair of consecutive image. If we have 5 images, then it's between 1 and 2, 2 and 3, 3 and 4, and so forth. So we can see the video of the coherence estimate in time. But don't look it too much because you get dizzy, I guess. So but the point is like if you have high coherence usually it's during winter period when there is a bare field, and then once the farmer plants the seed and then the vegetation grow and then the coherence will decrease, and then we can get a darker image, which means it's lower in coherence. But now this is still in the space. But now let's see if we sample our fields, our several fields that have the same crop types. For example, in this case, we are interested in grassland and also in some cropland. What it looks like, the mean daisy chain coherence in time. So this is only in the year of 2025 in time series. The purple and the brown comes from the L band and the other comes from the C band. Here we can see clearly that our L band can maintain longer coherence, in this case for the grassland. But let's look into the cropland. So the second plot, the middle one, is coming from potatoes and beets. And in this case, this group of fields has the same characteristic. If you look at the picture, that it is a low vegetation, but it has a dense or a wide horizontally oriented leaves. And then at some point when the vegetation grow, and then we have total canopy cover. And then in this case for L-band also, we still have low coherence compared to Sentinel-1. And interestingly, for the third group, this is like high vegetation, especially if you see the left one coming from a group of wheat. Actually, in time, even when we have wheat on the field, like L-band still have higher coherence compared to C-band. But also, in this case, the characteristic of wheat itself, it has like a thin or narrow stems and also the vertically oriented leaves. So in this case, that causes the coherence to be higher than other also. Now we have this in time. And now if we already talked a lot about the loss of log, now we want to see this loss of log event more detail in the coherence matrix. So now what you can see is a coherence matrix. So coherence matrix comes from every possibility of interferogram pairs that you can make from your stack. And then it's only describing a particular parcel. So in this case, if you look at the picture on the right, this loss of log actually comes from that parcel. And then in this case, is an example of loss of log because of harvesting. So you only need to look into this red box. And in the right image, we have 14th of June and 29th of August. We have in June, it's still green, and in August, it's already bare field. So there is harvesting in between, and we can see that from the coherence matrix, we don't have anything. But then after September, in the middle of September, the coherence coming back because it's all bare field until like during that summer period. And then this is the opposite of loss of log due to plowing. So when the farmers seed the field and then the vegetation start to grow. But interestingly, like in Sentinel, we have like almost no correlation at all after the vegetation growth. But in L-band, it still have some degree of coherence. And besides this loss of log, we also have intermittent loss of coherence due to snow. So we don't classify this as loss of log because during the snow we may have a certain degree of decorrelation, but after that, actually the correlation come back because it's still the same field and it's still the same bare field. As you can see also, in this case, we have camera on the field that clearly show that in 6 January we have snow, and then after that it coming back, and then the coherence also come back. So this is okay. And then because we already know that we have a coherent segment blocks, and then in this study we only use that coherent segment block as our observation data to parameter for the parameterization process. And then with the coherent segment, actually, if you can see the top figure, we have the coherence matrix, and then what we want is we want to identify the red blocks on the bottom one. And then we do that by simple binary clustering and binary morphology structure. And then we found that coherent block, and then we use that coherent block to do the phase linking, and we have a set of phase as our observation. And since we want to also, since the idea is to use L-band as a complementary of our existing C-band. So in this case, if we have loss of log in Sentinel, for example, in the blue line, so the white one is the loss of log, and the blue is where we have observation data. And if we combine other data sets from other viewing geometry or other wavelength, then we actually can end up with a continuous time series for our estimation. But it's also good to notice that since L-band has longer wavelength, then the noise is also higher than C-band. In this case, for example, if you have an efficient number of look of 50, see the orange line. In C-band, and if you have coherence of 0.4, and then in C-band, maybe you can have a noise of around 1 millimeter, and then in L-band is 4 times bigger, so you can have like 5 millimeters. Okay, so enough about the coherence. Now let's go to the area of interest. So we are talking about the Netherlands, but maybe I can give you 3 facts about the Netherlands as a country. It is a lowland, so the highest point is just around 300 meters, but the lowest one is maybe around 6 meters minus, and it's mostly in the coastal. So this is also maybe interesting. And then the second one, it has a massive agricultural production. So as you can see from the map, it's mostly the land is either farm or grassland, the green one, which is also for dairy farming, still farm. And then the third one, it is a soft soil. So in this case, because it is a soft soil, then we have the behavior that you see in the first slides, that it's going up and down seasonally. And our area of interest is actually only a small part of this country. The first one is in the pit, grassland, and then the second one is in the north, representing the arable land, where extensive agriculture happened over there. So let's go to the first one. So the setup we have observation period from 2022 August to January 2026 in this area. And we see that we have a reference point that's marked in red dots. And it's an IGRS, the Integrated Geodetic Reference Station, where it has a corner reflector and also GNSS in one side. And also in this case, we use parcel geometry as a boundary for multi-looking, as indicated by the white-red box for that particular parcel. And after that, during the estimation, we do the contextual grouping according to the soil type and the water management zone. So you see the previous illustration where we have combined data set for multiple wavelength, but in this case, if the combined data set for multiple parcels. So actually the black dots on the left figure is a representation of a centroid of a particular field. And then if we do combine them together, and then we also have a continuous time series at the end. And at the end, we will have, actually we have estimate the parameters for each black dots, but for now, I will show you the results. Oh yeah, this is also, I forgot about this. This is also since we have the extensometer, so if we projected the extensometer to the line of sight according to the L-band, in this case, actually, surprisingly, we have a good agreement between those L-band data and the extensometer. And this is the result in that extensometer side of the estimates when we have the realization. Yes. And then if we just overlap with the extensometer and the observation, we actually have also, it is a good agreement, but there is still room for improvement. For example, in this area, we don't have observation. We have also missed the estimation error over there. And in the second one, we have also estimation error due to the loss of log itself. So if we have loss of log, actually, we also need to estimate the unknown shift between those coherent segments. And in this case, for the second one, probably we have like the errors due to the shifting itself. And then go to the second one. I will go faster, I guess. So the second one is about the crop areas or arable land. We use the same setup, actually. And if we see the data set, this is what it looks like of two different parcels having different crops during the year. So for example, in the top, as we already discussed, that low dense leaves, we still have loss of log. But then if we have like wheat, then we have still observation in the coherent segment. And then if we do the same estimation, we actually end up with the different parameters than the pit, because like if you see the pit, we have like annual subsidence of 6 millimeter, and then in this case we have, the top one we have nothing, actually it's like 0, and then the bottom one is around 4 millimeters per year. But there's also, of course, there's also still room for improvement in this case, because on the 2025, you can see that the observation and the model also can have a mismatch. And as conclusion, so longer wavelengths can provide longer and higher coherent, but the association standard deviation needs to be considered. And then in pit grassland, in precise, maybe in a controlled environment or in the controlled setup, we can use L-band observation actually as ground truth, as long as we know that the phenomena is within the wavelength range. And the last one is actually this multi-band or multi-mission INSAR observation opens new opportunities for modeling the displacement by leveraging strengths of each configuration. Thank you.
Thank you very much. We have time for questions. Yes. Oh, there is one.
Yeah, thank you for the very nice presentation. I have two questions. The first one is, for people that are working in peatlands and agricultural lands and using INSAR, so based on your coherence analysis, which do you think should be like the least coherence that one should apply in order to assess the formation? And the second one is, I see that there's like a decreasing trend in the time series that you showed. So what do you think that decreasing trend is due to?
Okay, I will answer the first question one. I guess for the coherence itself, if you have INSAR observation with a multiple wavelength, or in this case, even if you only have C-band, I think you can still work with what you have. And for as long as you have, like in this case, we use the contextual grouping to add more observation on the loss of log, because maybe neighboring parcel have different loss of log events in the period of observation, so it's okay. And for L-band in our study, actually in the grassland, the coherence is actually quite longer, and it can maintain a higher coherence also, so we can use almost continuous time series with less loss of log. So I hope that answered your first question. And then for the second one, in the time series, if you see the trend of subsidings, that actually comes from the irreversible part. So in this case, our surface motion variation have two components, so the reversible part and the irreversible part. So in peatland, I guess it's actually the peat are breathing actually. So in winter, it's just go up, and then in summer, it goes down. But during those time series, there are actually a trend of subsiding, because I guess in theory, if we have peat, and then if we have a certain groundwater level, then the dry part will oxidize, and then it will induce the subsidence. Yeah.
Okay, thank you.
Thank you.
Thank you again. We have, unfortunately, to proceed to the last presentation of the session. It's by the chairman.
I'll be here if you want.
John Merriman.
Yes, so hello everyone. My presentation has a lot in common with the presentation you just saw in terms of methods, but we're considering a different peatland area in Denmark, in the north of Denmark, in the Jylland Peninsula. It's an area called Store Vildmose, which literally means the big wild bog. It's actually the main issue with it is that it's not so wild at all, and there have been considerable efforts from the government to try and make it wilder than it currently is. So it's an area which in the early 20th century, or since the early 20th century, has been drained and used for farming and peat extraction. So currently its state is mostly a degraded peatland. And the Danish Nature Agency has basically bought back this and other peatland areas in Denmark as part of a restoration, re-wetting project, so to increase the water levels and gradually, let's say, reinstate its peatland condition as part of an effort to reduce the carbon emission from this kind of areas. In this context, a private company, Joe Partner, a land surveying company, has installed also some corner reflectors on the area, since deformation can also inform on the state of the peatland, so to monitoring the state of the peatland before and after the restoration process. And here in this, here you see all these are drainage channels. And an important thing, which I'll mention also later on, so there's been this restoration project has kicked in since fall 2023, and the project has consisted of 3 major interventions, which also impact the INSAR analysis. So we have basically a filling in of these drainage ditches, so all these light blue lines, a creation of some dikes, basically to contain the excess water during the winter season, and also basically an impermeable membrane here on the edge of this area called the ring fenner, again to keep in this excess water and re-wet this area. So to go basically from this situation, pre-intervention, to more of this. And if we check the GMS, of course, there are no natural persistent scatterers here, except the corner reflectors, which are not natural and which were installed there. So we have absolutely no measurement point here, although in principle we are covered by 2 ascending and 2 descending sentinel tracks. So the question here is it really true that, for example, the Sentinel-1 archive can say absolutely nothing about the deformation in this area? Is it absolutely necessary to install corner reflectors to be able to say something about the deformation? Well, again, if we look at the coherence, so this is in the season before the intervention, this peatland area is permanent grassland. So here in the winter, autumn to winter season, it's the coherence levels are pretty high. And instead in summer, there is growth enough to cause a loss of coherence. The only coherent objects are the corner reflectors, which were installed at the end of 2021. And then in fall 2023, there have been these restoration interventions. So here you see basically they've been filling the ditches by digging some soil just around the ditches and using that to fill the drainage ditches. These brown here you see here. And then they've been building these dikes and placing this membrane. So that causes loss of coherence and changes in the coherence pattern. And of course, indeed, the restoration seems to succeed in making this area much wetter. So here then we have also standing water on these fields, which also influences the coherence and causes loss of coherence even in the summer and spring season. So before the intervention, one could basically do something similar to the previous presentation. You could look at the coherence season roughly from October to April, and there, especially where their sentinel time series were denser, you can just run a multi-temporal, let's say, distributed INSAR processing. For example, we run as BAS-like processing. We modified it a bit to increase the coverage. So actually we created a separate interferometric network for each pixel, basically just considering all possible interferograms in which a given pixel is above a given coherence threshold. And we performed an inversion separately for each pixel. And we see a seasonal highly nonlinear deformation, so basically half a sinusoid corresponding to an uplift. And these maps for different seasons show deviations from linear deformation. So this is where we see this half a sinusoid. And the extent, so the amplitude of this sinusoid and these areas, they clearly correlate with map-up peat thickness. So where we have a greater peat thickness, it reaches up to 3 meters. We also have a larger deformation, which might be reasonable in the sense if peat behaves more or less like a sponge, where there is more water intake and outtake, there is more uplift and probably also more subsidence. However, it's impossible to continue with this approach, especially after the restoration project. And also we see only half of our expected deformation signal. So we resort to the Conroy and others approach, so the SPAMS model-based approach, which you saw in the previous presentation. And we consider the different parcels here. Indeed, here there are no crops, they're all grasslands, but they do decorrelate at slightly different times. And basically, if we sink the level down to a 0.205, then we will bridge this loss of lock. It is not, let's say, an unrealistically low threshold. It is actually, if we took an area which is just water, so a zero correlated area with the multi-looking factors we used here, it would still be the 88th coherence percentile of a fully decorrelated area. So we are not just working with noise. There is some signal, deformation signal there, and we will see this also when comparing to the corner reflector. So we do this coherence analysis, and here we can see for different parcels the periods in which we are under threshold, and here in the gray shade you see the number of parcels which are above the threshold. Indeed, there's only a handful of them left in some seasons, so we carry out an analysis where we at least have 5 adiacent interferometric pairs above our coherence threshold. We carry out our analysis. We also have corner reflectors, and those are persistent scatterers. So to have something to compare with, we do a persistent scatter analysis of our corner reflector, and we refer them to one of them, which is anchored underneath the peat level. So it's a stable reflector, and we measure the gradients, time series of gradients compared to that. And then we carry out a DS insert processing. So we do S-BAS processing, which within each coherent time window for each parcel, provided we have at least 5 consecutive coherent interferogram. We do this with our own in-house software there at DTUM. And the corner reflector time series look like this. So there are, let's say, 4 of them, and the reference one. 3 of them are in very good agreement with each other, so they have these oscillations. And then after the restoration period, they become more flat. One of them, this red up here, it seems to, let's say, a bit skyrocket, and I'm a little skeptical about those measurements, although I see it also in the descending tracks. And these are corner reflectors which let's say, are suitable for both ascending and descending tracks. And instead, if we consider a parcel, for example, a parcel containing this corner reflector, this is the corner reflector time series, which is complete. For this parcel, we only have some coherent segments, so these ones. And within those, our time series always starts from 0. Although, as you can see, there is a clear resemblance with the underlying deformation of the corner reflector. It's just disconnected. So we resort to, and we can do this analysis for all the different parcels. Each will give disconnected time series. So we resort to the STAMPS model to try and connect them. And as the previous presenter showed, we have our, let's say, reversible and irreversible components. And this model is driven, by the way, by precipitation and evapotranspiration information, which we downloaded from the Danish Meteorological Institute. And here, basically, we want to estimate 4 parameters, one which, let's say, regulates the wetting through precipitation, and one which regulates the drying through evapotranspiration. And then there is a time constant, and then an oxidation constant. This irreversible component is due to oxidation in the dry period. So we must estimate these parameters. I won't go into the detail of how we do that, but we do it as a combined nonlinear search for the tau parameter, and then we solve a least squares problem, a linear least squares problem for the other ones. And we perform this, we obtain better results by performing this estimate on a yearly basis and then stitching the yearly models together. So these are the, let's say, the SPAMS model fits for the 4 years we considered, and this is the model stitched together. And once we have estimated this model, then basically we can use this to estimate some offsets for each of the disjoint segments we have before, and we can obtain a reconstructed time series. So now we just added a constant offset to each parcel, and the solid line here is the output of the SPAMS multi-year model. And here the dashed line is the average of all the parcels, reconstructed parcel deformation time series. It is complete because we had, let's say, bridged that loss of lock. And if we now compare with the corner reflectors, well, as we saw already in the previous slide, it's not that the corner reflectors, the deformation pattern within this area is not at all spatially uniform. We saw that it's related to P thickness, and the corner reflector PS time series, they differ. So now in combining all the parcels, we cannot expect them to agree with any specific corner reflector, but we expect it to agree with the average trend of the corner reflectors. So indeed, these black lines are our inversions based on SPAMS and distributed INSAR. And here we have, instead the colored, are the 4 corner reflector time series. So indeed, well, especially the three corner reflectors which agree, they are in very good agreement with our inversion. Nor our inversion nor the corner reflectors seem instead to agree with one of the 4 corner reflectors. And yeah, one can also do a regression. Basically, the main deviations are due to some, let's say, jumps or let's say some poorly constrained time periods. Those are the areas where we really had to stretch the coherence thresholds to try and bridge this loss of lock. Those are also some the noisier parts of our inversion. But if we go back to our initial question, which is we look at EGMS, there is nothing on this area. It is an area which is undergoing a restoration program. It is of interest to monitor the deformation as a proxy for peatland condition. Can we really not say anything about this area with interferometry? Well, the answer to that is that actually, well, all in all, we can say a lot, because alone with the distributed scatterer multitemporal analysis within coherent seasons, we can reveal a complex spatial pattern of deformation, which is related to peat thickness. So that is interesting in itself. It could have guided the installation of those corner reflectors. They have been installed without looking at that deformation pattern, for instance. And also the Conway et al. Method, so this model, SPAMS model aided approach to reconstruct the average time series of the area, well, was very successful in that area. It mimics the deformation time series we see in the corner reflectors. So, so the answer to the question is no. Distributed scatter interferometry can absolutely say something about this area of interest. I didn't mention one thing. There's been a lot of talk in other sections about phase closure and the dangers in providing interferometry results in areas where there are no persistent scatterers. I can add that, well, first of all, the corner reflectors are, of course, not affected by these mechanisms, and already finding an agreement with them means that we are not sensitive to these effects. And also, we did check phase closures here, and they are grasslands, and there are no significant misclosures. So the analysis we conducted here, it's safe to conclude that, okay, we can trust these distributed INSAR scattering results. Thanks for your attention.
Thank you, John. We have time for questions.
Thank you. Hi, I'm not going to comment on the methods, but I was interested in those 2 big jumps you saw in 2022 and 2023. And I'm not sure what the situation was in Denmark, but those are 2 drought years in Europe. So I wonder if you could comment on...
You mean these ones?
Yeah, on whether, what the sort of, are you seeing a climatic signal there, and what does this imply to climate and peat?
Well, I mean, all the deformation in peatlands is, we assume, driven by the, so let's say, I'm an engineer, so don't listen to me about anything geological, but if it's a sponge sucking up water and releasing it, I mean, that is the driving mechanism behind it. From our point of view, I mean, we see these deformation patterns in both corner reflectors and distributed scatter interferometry. So regardless of what they are due to and what the peat is, let's say, reacting to, they are there, and we manage to measure them. I don't know specifically if there is another more complex interpretation of those patterns.
I also have a question or comment. I think it's very important what you said at the end of the conclusions, that in spite of criticism around about using distributed scatter methods to get information on the deformation, you show by this very nice data set allowing the comparison with the well-grounded corner reflectors that it is possible to overcome the different problems. Now, did you do anything special to make this possible in your processing?
No, we didn't do. We did basically a SBAS-like processing within. The only thing we did at the beginning, because we were a little aware of this issue, is here basically we check the consistency of our results with different constraints on the temporal baseline. So these effects, misclosure effects, generate inconsistency depending on the baselines you
only up to
you include.
60
Here, once
days.
a certain redundancy is achieved, the results are consistent. So it's a consistency check would reveal problems, besides computing, of course, the misclosures themselves, and there was no spatial correlated pattern as we saw in areas. So I guess if it were a cultivated area, one would be, well, pay extra attention to these kind of effects. But anyway, there are some consistency checks we can do as INSAR people when working with these areas, which we know are tricky.
Thank you. It's very important. More questions? Okay, yeah, Ramon.
I can just comment based on the previous question on the climatic relationships. So we see the same things indeed, and if you have very dry and hot summers, then particularly you have a longer period in which the land dries out, and peat is apparently very poorly permeable for water. So that means that if you have a dry summer, it will take a while and before it kind of recovers. So these dramatic peaks that we see in the hot summers in Europe, they make sense also from a physical point of view.
Okay. And I guess that irreversible component is the one which then kicks in as this oxidation.
Well, the irreversible component is so what you see, if you can see it very nicely in your graphs if you show the time series.
This one.
Yeah, this one. Yeah. So if you look at the black lines with this is the SPAMS result, right? So you see that a parcel is not able to kind of fully recover. Huh? So if you go, for example, for the black line in 2022-05, so it sinks down to September, so the late summer. Then the temperatures go down and precipitation goes up and it swells up again. But because it has dramatically went down, it doesn't recover all the way. So basically the irreversible component has kicked in quite dramatically because of a hot summer. So that means that if climate change gives us more hot, dry summers, the irreversible rate will accelerate. Yeah.
Thanks, Ramon. You got a proper answer.
So thank you again, everybody, for attending, and presenters for interesting presentations. So I think we close this on time. Don't forget, there will also be a related round table, I think, at the end of the afternoon sessions. And there are also related posters in the poster session in the late afternoon. Thank you.
Yes, exactly. Yeah, so it's good to have something. Is people are less shy.
this subject.
Yes.
There's a site in Scotia Bowland with a pit. This is with the algorithm, right, processing. So the yellow, the green points with MBPT, no, the sigma TS less than 0.4 or 7, or they are those areas. And the red ones here, this is the peatland with agriculture on top. And the sigma TS is more than 1. I know that you might have a unwrapping error, but in this case there's no unwrapping error, I checked. So could be that the phase closure thing.
And what we did is very
Smart
good
to
idea.
check.
So you
To check.
check with, you get still the effect, but you include 6 and 12 days, but then you also go up to 24 days and you look if it changes.
Okay.
So the velocities should get lower, and that's a clear indication that it is caused by
It's a closed phase closure.
And
Yeah.
of course you cannot include 1 year, then you will not have
Coherence.
signal, but still you can be aware of the effect, and it seems in his case it became small enough to change by adding more sequence, and so you're close to the robust.
So I'll do 6 days only, then 12 days only, or combination. No.
Probably, we did up to 60 days, so something
But
similar.
in the same processing, combine all this in the same processing, or different processing, different.
I mean,
the same data,
you
the
do
same
one
combination.
processing with 6 and 12 days, and
Yeah.
you do one processing with 60 days.
Okay.
And you have areas where you get the same result. That's what you trust.
Yeah,
You
okay.
get an area where you have factor 2 difference, or very.
So that's the phase closure. Okay.
Still be a little bit orange or something.
Yeah, but less than that.
But less. And so I think you just have alarm clocks ringing that don't trust this. It's not saying that you fully solved it.
Yeah.
But if up to 60 and up to 100 days gives the same result,
Then we know it's okay, it's right.
It's robust. If
Yeah.
that's possible, that's not necessary.
But in this case, the sigma TS, it's very now it's very high, above 1. So probably is not right. Right. I mean, this is indication not only phase unwrapping, but also error, but also on the phase closure.
Yes.
Okay. All right.
I think all these cases with intermediate, with coherence and like fields or sand or so,
They give it
can
this.
be affected by very significant effects as a result of the presentation. Also, and we can say this depending on how you do it, and so this test will use this 10 centimeter per year, 2 centimeter per year, which is still the wrong.
Still don't trust it, but it's just.
It shows you that 10 are definitely wrong, 2 are probably also still wrong.
So you cannot say anything about the formation information. You cannot say
I
just.
think it's really not.
You just eliminate them. Just.
That different patterns are not decorrelated for different intervals. So for a short interval, we have more of the patterns that we can use interface. So maybe some are
Moving.
above or below the surface, and so they add a different phase. And if that's decorrelated, it doesn't contribute to the phase, and so you have the different phase.
All right. Thank you very much.
Yeah, no, but it's a summer and yeah, no, but it would be very nice. Well, then it's much larger. Yeah, what I like
mitigate the effects by
Are you going to stay for the...
We must just take a couple of notes of what we want to summarize.
I think in other cases it will just show you're affected and you cannot solve it because you have to use long enough intervals that you don't have enough coherence anymore.
So I would summarize it as even in what Tazio showed and also the other so distributed scattering can deliver some complementary information. There are, however, some extra challenges. For example, seasonal coherence, snow or plowing, or many things. The ambiguity is. So it is, however, relevant to let's say so there's both. There can be some consistency checks, for example, concerning some disclosure or things which are utilized in measurements, but also there is the, let's say, the physical interpretation and knowledge of the physical processes. You know, even in Gideon's presentation, he had a very physical interpretation.
And he seemed extremely happy with the data that is available.
Yeah.
So I would have asked if more time would have asked him if that's really the case, or if he would like more frequent. Of course, more frequent is always better, but he seemed happy for his application with the data that he have available somehow. Sentinel, some experiment.
Then, of course, there's the L-band prospect, which has been mentioned now.
Yes,
thinking of
exactly.
Roselle, that I think it seems clear that it can help with some of these challenges, both coherence, help and complement. So it has a different sensitivity to some of these challenges, both ambiguities and coherence.
It's also the different sensitivity. So, for example, at L-band you can live with 0.1 coherence, you can still average and you get the correct phase. At the C-band you have 0.1 coherence and you can average and it's not the correct phase somehow. So you don't know exactly if wrapping effects are relevant, that the noise is more but that's just consistent observation.
Okay, so that I think were the most of our talks. Then we had one on risk, which was more related to the first session, actually, the one on risk from there in Java. I think Gela will have they will have their own set of. That's a total different. To go from interferometry to hazard and risk assessments. That is.
Yes, the others were strongly also including the technical aspects.
Strongly DS-ins are distributed
so
scatterers.
it was linked to a topic, but also an important part of the work was solving issues somehow.
Yeah.
I was a little bit disappointed that it was kind of BGS. I expected that the interpretation should be an important aspect, and she was, of course, the colleagues are probably the ones for the interpretation. Understanding, and she was more the processing.
Okay, good. But then I should summarize these things on a slide or two, and then I can nail it, and you can have a look at anyways these ones. And then I will be there on Friday.
There's this seed question thing. So we should have 3 seeds, 7 questions somehow.
For discussion.
I think so, yes. So
And, one should be on the use of the Yacin's methods. I think that the question I have for that's like, how do you, let's say, if we say that you need to use PSI, you need to use the Yacin's, how can one, let's say, how can one present, then it's not just the deformation times series, perhaps. So how to present what ideas?
In our services or in our also project work, you never have a typically you don't get this, but you get a gap. So it's very complementary. But also it gives a good confidence in the results. So it's not independent. So you do it with the same data stack, but it's still very independent somehow. The way you process a few interferograms with different intervals is not the same as a PSI or SBUS time series rate.
Okay, do we have any requirements, or could I another one, I would have also one on it. Recommendations for L-band.
This tests out with L-band.
And I was thinking, would we have any, or could a seed question be, are there any recommendations for forthcoming L-band missions like Roselle?
I mean, there's of course with the pulsar and SAP, you can already well use it, and it's in a way it's easy to use and better information. So it's really, I mean, it's complementary, but it's very high potential, and if you can only choose one or the other, you take all that.
A question on consistency checks, perhaps?
Yeah.
How could we ensure that these... What could we do to ensure that our measurements are credible and we don't end up on the front cover of
Yeah, I think in general that somehow consistency checks, and this can be comparison with interferograms of the same sensor. This can be comparison, not integration, but comparison ascending, descending. I mean, integrating is nice, but I think it's even better not to integrate it and to have two results and they show roughly the same. Nobody cares about the lineage.
Yeah, that's just to be sure that you're not making up the signal.
Displacement, and then of course with other techniques, not just so there's GPS, there's model understanding, optical, photogrammetry, and so on. So this confidence in the application cases is crucial.
Crucial for the credibility.
Exactly.
Okay, I will let us something. Let's go get some lunch. Thanks for the co-chairing.
Thanks for presenting the results.
Interesting session.
elhangzott egy bicchieri. There were 5 presentations, and now
Was added something?
no, it
No.
was reduced because now in the website there's like 4. Like
Really?
one is missing, so I'm not sure if it was cancelled or
But
it's
it is good if
it's
it's,
this one. I don't know this.
Which one it is?
Wuhan University. This one is no longer in the website program. So
Okay.
maybe.
So if it is, we can perhaps.
So we have 20 minutes extra for the
Because
coffee break.
Mahdi was asking for some space in the program. We told him if there is some missing presentation, we can give the chance to you for that time. He want to bring some topics. Mahdi.
Mati. Okay.
He sent email to some of our, I think he didn't know your email. He sent email
Okay.
to me, Lynn, Nexus, I think Michele, so all the chairs of
Okay.
decisions. He
Okay.
asking for.
So we would like to make sure that this one is missing because it's no
this
longer.
this one and this one.
Sorry, one more time.
The third one is missing, yeah?
Which one is missing?
This and this.
There are only 2 presentations? No.
No.
I think this one is missing.
Okay, in the.
But this one I don't know. It was in the program.
It is in
this
the
one.
program, yeah.
Hello? Oh, okay, perfect. Hello, everyone. My name is Maria Przółcka. I'm from Polish Geological Institute, and I have this great pleasure to welcome you on the Deformation and Displacement third session today. I will be chairing this session with Sami Esfahani from University of Leeds. And with no further delay, I invite first speaker, Dana Hajar or Yanjingyan. Welcome.
Okay, so good afternoon. So I will talk about sequential learning of SAR image time servers for monitoring Earth deformation. I will begin with mathematical modeling of multi-temporal SAR data. So here is a data cube. For one given pixel, with, for example, temporal observations, so from a homogeneous neighborhood with similar backscattering and statistical properties, so we can compute the second-order statistics of SAR images to get information about the coherence, the variance of SAR images, and also the phase differences. And in matrix form, so we can get complex full coherence matrix of SAR images that includes the information of the interferometric phase and also the coherence and also variances of SAR images. So in this way, so we can parameterize the coherence matrix, complex coherence matrix of SAR images by two variables: the module of the complex coherence matrix and also the phase, the interferon beam. Several multi-temporal INSAR approaches based on at least mathematical model, for example, the phase linking. The objective of the phase linking is to estimate P-1 phase differences from PSAR images. And the main idea is to minimize the negative log likelihood that depends on the full coherence matrix of SAR images. If we assume the module of the coherence matrix is null, so the method is equivalent to optimizing the following problem that depends only on the interferometric phase. That is why in practice, so we replace the module of the coherence matrix by the module of the sample coherence matrix, but this solution is not always optimal because the approximation of the coherence, full coherence matrix by the sample coherence matrix can be biased sometimes. Yeah, some other authors proposed to estimate jointly the coherence matrix and the interferometric phase. The traditional phase linking method considers the Gaussian distribution of SAR data, but the Gaussian distribution cannot be verified everywhere, for example, in urban area or in case of high-resolution SAR images. In this case, so we can use scaled Gaussian distribution to take into account the non-Gaussian distributions. But in both cases, so we can get the analytical expressions for the log likelihood. We can also get the closed form solution for the interferometric phase. Another state-of-the-art multi-temporal INSAR approach that uses coherence matrix is coherence fitting. This method consists of minimizing distance between empirical coherence matrix of SAR images and the theoretical coherence matrix. Yeah, so here is the theoretical one. We can see that in this theoretical one, there's interferometric phase information that we try to estimate. There are several options for the matrix distance and also for the empirical coherence matrix estimator. For example, we can use Kullback-Leibler divergence for the matrix distance. We can also use the Frobender's norm. So it's equivalent to the least square method. For the plug-in for empirical current matrix estimator, we can use the sample current matrix. And for non-Gaussian data, so we can use the M estimator and the phase-only matrix. With this method, we can also control the structure of the current matrix to take into account different temporal decorrelation mechanism by adding a regularization term in the empirical current matrix. For example, we can consider the low rank structure. We can also add the bending regularization or the shrinkage regularization. The bending regularization is to cut, so to remove long range decorrelation, and the shrinkage is to keep long range decorrelation. All these methods, all these multi-temporal methods are very performant. But the question is, when more images are coming, so how to integrate new images in the methods. So when more images are coming, so the vector of star images increases, as well as the current matrix. So in order to integrate new star images, we need to estimate the new current matrix. So that implies re-estimating of the past current matrix that has already been estimated. It's similar for the phase, because we need to estimate the new phase. So we re-estimate the past phases we have already estimated. So in this way, it takes a lot of time. So there's a need to develop sequential approaches. Indeed, in the state of the art, there is one sequential method, namely sequential estimator. In this method, we divide the whole temp series into small temporal blocks, and phase linking is performed into each temporal block. And after that, each temporal block is compressed to one virtual image. And final global phase linking is performed to link different temporal blocks. The potential drawbacks of this method is that it needs some time to get meaningful mini stack, and the method is initially based on Gaussian assumptions on stack data, and it lacks robustness against various temporal decorrelation mechanisms. That is why we were motivated to propose other sequential multi-temporal instar approaches. In following, I will present three contributions. So the first one is sequential phase linking based on maximum likelihood estimation. And the second one is sequential covariance fitting interferometric phase linking. And the last one is sliding interferometric phase linking. So the first method, sequential phase linking based on maximum likelihood estimator, can integrate individual star images. So when one new image is coming, so we add the new image in the vector of the star data, and then we update the covariance. So the new covariance, we formulate the new covariance as a function of the past covariance, and also the correlation between the new image and the past block, the new phase of the new image, and also the variances of the new image. So in this way, we can also update the log likelihood in an incremental way. In this case, the likelihood function depends on the new estimators I mentioned previously, and we can get the closed form solutions in this method. In summary, in this method, so the new phase is estimated with based on the past phase, the past covariance, and also the new images. So in other words, so we estimate the conditional statistics of the new phase based on the past. Here are some results. obtained from 3 different approaches, interferograms over the Mexico City with Sentinel-1 data. The first column is 3 interferograms obtained from the sequential phase linking based on maximum likelihood estimator. On top is a wrapped interferogram, and on bottom is a unwrapped interferogram. And in the middle is a phase linking based on maximum likelihood estimator. Is just the offline method, and the last column is a sequential estimator. Here, in the case of the time series contains 20 images, and for the sequential estimator, so in each temporal block, there are five star images. So here, the observation is that there's a good agreement between the 3 considered methods. Here, the objective is to do a relative comparison, because we want to check if a sequential estimator degrades the performance because we use less data. For further comparison, so we define several metrics. For example, the root mean square error and the structural similarity index for a wrapped interferogram and the collinearity for wrapped interferograms. And we look at also the computation time. The conclusion is the same. So in terms of performance, it's very similar between the 3 considered methods. But if we look at the computation time, so the proposed sequential estimator is the most efficient. The second method, sequential covariance fitting interferometric phase, allows integrating 1 block of star images. As shown here, the idea is similar to the previous method. So we can add a block of new star images in the data vector, and then we update the covariance matrix. So the new covariance matrix is decomposed into blocks. So 1 block of the past covariance matrix and 1 block of the new block of star images. We add also the covariance between the past block and the new block. And this method is based on the covariance fitting formulation. So we try to minimize the distance between empirical estimator and the theoretical occurrence matrix, so in which there's the phase information. In this case, there is no closed form solution, so we use iterative algorithm for optimization. So here is the results. Always over the Mexico City with Sentinel-1 images. This time the time series contains 14 images. And the first column is interferograms obtained with sequential covariance fitting with callback-Lieber divergence as a matrix distance and also shrinkage as a regularization option. We use phase-only matrix as empirical estimator of the covariance matrix. And in middle is the results with the offline covariance fitting method with exactly the same option. And the third column is interferograms obtained with sequential estimator. So here the conclusion is the same. So there's a good agreement between the 3 considered methods. Here is another result with other options. The first column is a sequential covariance fitting with this time Frobenius norm as a matrix distance with bending as a regularization. We use the same empirical estimator for the covariance matrix. It's a phase-only covariance matrix. And in the middle is the results with the offline method with the same option. And the third column is always the results with the sequential estimator. So the observation is the same. So with sequential estimator, so we can give very similar results with other state-of-the-art approaches. If we look at metrics we defined previously, in terms of quality of performance, so as said previously, the three considered approaches give very similar results. The proposed sequential current fitting estimator is always the most efficient, but in this time, the gain in computation time is not so significant. And another observation is about the different options provided by the current fitting method. The combination of Frobenius norm as matrix distance and also the banding as regularization, this combination gives better results than the callback-Leibler divergence and shrinkage regularization. With these two sequential multi-temporal approaches, we need to store all the historical data because the current metrics they depend on the past. So when we deal with very long time series, so it's very expensive in memory resources. That is why we propose the third method, sliding interferometric phase linking. So we define a temporal sliding window. So inside each temporal window, so we perform the current fitting. So but this time we add a penalty term to ensure that the phase limits to stay close in the overlap between between successive temporal windows. And we use the same optimization algorithm. Here is the result always over the viscosity with three different methods. The first column is the proposed sliding interferometric phase linking. In the middle is on-flight current phase linking with Frobenius norm as matrix distance, and the third column is the result with the sequential estimator. The observation is always the same. Yes, the three considered methods give very similar results, and the sequential method does not degrade the performance of the phase estimation. If we look at the metrics, so in terms of quality performance, it's very similar. For three considered approaches, if we look at the competition time, the sliding interferometric phase is much more efficient than the other approaches. So to conclude my presentation, so we have proposed three different sequential multi-temporal INSAR approaches. So the first one, based on maximum likelihood estimator, can integrate individual SAR images. And the second one, sequential current fitting phase linking, allows integrating blocks of SAR images. And the third method, sliding interferometric phase linking, does not need to store historic data, so it's very efficient in terms of memory management. And the three methods can provide very similar performance to other state-of-the-art methods. So if you are interested, all the codes are available with free access. Thanks for your attention.
Hey, thank you. We started 4 minutes late, so I think we have time for a short question now. Yes?
So in all of your methods, you are dividing your time series into different blocks. How do you select these blocks, the length of these blocks actually, how many images it should be in each block? And is there any quantitative metric to consider this, let's say, grouping of blocks?
You mean for the second and the third methods? So
yes, especially the third one.
Yeah. we tested the several values. We need at least 5 images to get a satisfactory accuracy for face estimation.
So it's just based on trial and error, no quantitative measures that you have used.
Yes, right.
Got it. That's, okay.
Thank you. We should proceed to the next one. Eugene Wang from University of Delft on near real-time displacement, anomaly detection, and risk assessment for instantaneous state insert.
Hello, good afternoon, everyone. I'm Yuqing Wang from TU Delft. Today I'm going to talk about the instantaneous state insert, also called ISI. It is a new way for the near real-time displacement monitoring, and this is basically the work of my entire PhD, and including the instantaneous state estimation and anomaly detection and risk assessment. So here we have this insert map, this typical insert map, and this is in the city center of Amsterdam. As you can see, there are a lot of green dots which are, we can consider they are stable, and there are also some red dots which are like with movements are the points we are interested in. And there are already a lot of ground motion services available like EGMS, where you can click a point and you can see a time series of it. Typically, we will say the average velocity for this time series. But from a perspective of monitoring, if something happened in the last image, you will not immediately see it through the average velocity. And also, on the other hand, now we have a lot of satellite missions, and there will be new observations available every several days. And for example, in Amsterdam, there are about 3 million observations per day on average. So this also gives us great opportunity to do the near real-time monitoring. So in this study, we explore the capability of INSAR to do the near real-time monitoring. And here is a case study. In the city of Amsterdam, there are a lot of canals, and on the two sides of the canals, it's a cables. And in September 2020, there is a collapse of the cables in Greenberg, Amsterdam. And actually, in the city of Amsterdam, the cables are over 800 kilometers, and they have a history of over 300 years. But they are they build on these wood piles, and they are under poor conditions. So you can see sometimes there will be some collapse. And there is an insert time series before the collapse happened. And in the a few months ago, before the collapse happened, there is actually a little acceleration. If we are able to detect this acceleration timely, we may able to take some measures before it collapses. And here is what we the idea what we want to achieve. Like in a traditional method, we have this insert map, and if something happened in this area and it happened in the newest acquisition, it's difficult to say on the average velocity. And what we want to say here is that, for example, we have this map, and when the last new images comes in, we want to we can do the anomaly detection, and we can get some warnings based on the last acquisition. And here we can see, for example, there are a lot of warnings in Greenberg wall, and we can zoom in and we can go have a look, and we can see the anomalies being detected in this area. And for each new acquisition, we would like to achieve this. So the detected anomalies will also be updated for each new epoch. And to do this, we need to have a method to do the the sequential time series estimation. So we first start with this modular 2pi or the wrapped interface, and we need to have a model for it. So we need to do the parameter estimation first, and depending on the model we used, we could get different unwrapping solutions. And here, basically, we will use a static parameters, for example, a constant velocity, and we assume these parameters are time invariant. So basically, it doesn't change with time. And if we want to do the near real time, the easiest way is that we can do it incrementally. So we have a stack of images, and we do the batch estimation. And when for example, we have 50 images at the beginning, and when the image 51 comes in, we reprocess the stacks again. And every time there is a new acquisition, we reprocess the data. And in this case, we get the like a parameter which is time invariant. I think now a lot of like ground motion services, they're still doing this kind of update every few months or every year. So still a lot of like available services are still using this method. And this is kind of an example of what we will get with this method. So this is an arc between 2 point scatters in Amsterdam. Here you can see this is a time series of this arc, and we can see something happened between 2017 and 2018. The incremental bench method somehow can capture this behavior, but it lags behind the anomalies because it uses time invariant parameters, and these parameters need time to adapt it to the changing behavior. So this is what we will get, but we can also do it alternatively. So we can do it, for example, we do an initialization, and when the image 51 comes in, we can use the new observation to update previous estimate. So in this case, we store the estimates for epoch 51, and when the epoch 52 comes in, we use a new observation to update our previous estimates. So we only need to store the current observation and the previous estimates. We don't need to store the past observations. So in this case, it is very computationally efficient. And we can do this recursively so that we can get the instantaneous state for each new epoch. But there is a key thing in the recursive method is that we still need a state transition matrix to describe it. For example, from epochs to epoch, you need a state transition model to describe it. If you have a state transition like this is what you will get. And if you have another state transition matrix, you could also get to another different solutions. So this is very important. And here for the state estimate, we can actually estimate the instantaneous state. Here, for example, we have the instantaneous position and the instantaneous velocity. And this is time index, so we have it for each epoch. The easiest way to have this state transition matrix is that we assume the velocity at this epoch is the same as the last epoch. Here it's like a linear model. It assumes it's a infinite smoothness. But here we have this ISI state transition matrix, and it assumes the velocity is autocorrelated, which like in reality, we assume the velocity is correlated to the to its past value, which means the velocity is related to its past behavior. Here, based on the autocorrelation model, we have the two parameters, the sigma for the instantaneous velocity and the decorrelation time for the instantaneous velocity. Basically, the the sigma v describe like how variation the velocity can be, and the decorrelation time describe like how long this velocity will sustain. And we call this the smoothness doublets, and this the smoothness doublets makes the smoothness like explicitly. And this also somehow by input different smoothness doublets, you can get actually different unwrapping solution. And here is a result for the instantaneous state solution. You can see the solution better captures the dynamic behavior, and also the same ambiguities are estimated. And right after the state estimation, we can do the anomaly detection immediately. We also don't need to wait. We can, after each observation, we can start the anomaly detection. So for example, we have the estimate at epoch t-3, and we can do a prediction for the next epoch. And when the observation comes in, we can calculate the predicted residue. And based on this predicted residue, we can somehow estimate we can do testing to evaluate an observation at a specific epoch is an anomaly or not. And we can do this epoch by epoch. So this is right after each estimation without waiting for the next evaluation. And here, let's go back to the K-walls monitoring. Here, this is a picture just before the collapse happened. So if we do the near real-time algorithm, if we detected this kind of anomaly, we may be able to take some measures before its real collapse. And there are two parts of the K-wall collapse. And here you can also see the subsidence signal on the instantaneous state solution. And it was to mention that this instantaneous state solution shows consistency with the bench solution. So this is the estimation of average velocity, but we evaluate this average velocity after we do the state estimation. And it has consistency with the bench estimation. So this means even without hindsight, even without using data in the future, we can still get a similar estimation. And also, it is much more computationally efficient. And here is some result for the detected anomalies. After initialization, we can do this estimation and anomaly detection epoch by epoch. And in the end of this time series, so this is a 2 years time series before the collapse happened. In the end of this time series, a few anomalies are detected and somehow capture this dynamic behavior. And after we detected the anomalies at each epoch, we could actually evaluate the risk of each epoch. So here, for each epoch, we could detect anomaly, and we could represent it. For example, if it's anomaly, we represent it as 1. And if it's not anomaly, we represent it as 0. And in this case, we can have adjacent observations. So it's like a window. If we have here, I give an example of 4 adjacent observations. If we use this for adjacent observations, we can use this window to evaluate the risk of anomaly at a certain epoch. For example, we also came up with this weighted anomaly score, and it put higher weight on the last epoch. So in this case, because anomaly like a few epochs ago maybe not that important, and here we have we put more weight on the last epoch, and then we can evaluate the risk level. And here is an example. For example, there is no anomaly detected, and then there is a new image comes in and is detected as anomaly. Then we increase the risk level, and another image comes in, and if it's still anomaly, we increase the risk level. So in this case, if continuous anomaly detected, we will put a higher risk level for it. And here is some results. Here is the end. We can say actually the risk is increasing from 0 to 3. And here is what we mentioned, the smoothness doublets is really important. And here are some examples. If we put different smoothness, we could get different results. So these are the two modes of the ISI method. So one is anomaly detection, like for example, the figure A and figure C. Here you would assume the behavior, you put a higher smoothness, so the behavior is kind of steady, and then you would detect more anomalies. But if your purpose is to kind of perfectly fit the model, we also have the particle following mode, which you can see the model fits the observation. Then in this case, no anomaly will be detected. So this will depend on the user case if you want to if your purpose is to detect an anomaly or to find a model. So to conclude, we have this instantaneous state insights framework for the near real-time displacement monitoring, and currently it has 3 main functions. So one is we estimate the state for each new acquisition, and then we also do the anomaly detection. So these two are both near real-time. And then the smoothness doublets is also something new. So instead of using a fixed parameterization, for example, like a linear model, sinusoid model, or a breakpoint model, we came up, we propose this smoothness, we can impose the smoothness constraints on the signal by just choosing different smoothness doublets. So that's the end of my presentation. Thank you very much.
Thank you very much. Maybe some questions?
Excuse me.
Thank you. I have a question. What happens if your deformation between the last and the previous image is 1.5 centimeters?
So in that case, I would assume, so it's 1.5 centimeter, like for Sentinel-1?
Yeah, exactly. I assume you are considering Sentinel-1, right?
Yeah, so it's kind of like half cycle. And in this case, like without prior knowledge, you would assume like you don't find this cycle slip. But without prior knowledge, if you already know that happened, then when you have this message, when you have the new observation, you can actually choose a different sigma v and tau, we call it the smoothness doublets. This smoothness doublets actually can be different for each state transition. And in that case, because something changes, you can also choose different smoothness doublets. In that case, you can also get, it also depends if you want to detect that or not.
Yeah, so my question is, can you detect an anomaly of 1.5 centimeters if you have it in the next image? So that's basically the question. Or you need prior knowledge, otherwise
yes, I think in that case we need prior knowledge.
Okay, thank you.
Okay, thank you.
It's related to the previous question, actually, but just thinking, if you can confirm I'm right, I understood it correctly or not. Before we have a steady state model, so whatever the results, even recursive results, was based on that model. So now we get rid of that, but instead the results are now defined based on the smoothness parameter. So we have we don't have linear assumption anymore, but we have smoothness assumption.
Yes.
And for example, in this case, if you have really abrupt change and you don't know it in the smoothness parameters, you cannot detect that. Is it correct? Or I missed something?
I think like if you don't know anything, of course you would not break your assumption about that. But if you already know like something happened, you can actually put your smoothness like more rough. In that case, you can also capture the dynamic behavior.
Thank you.
Okay, now we proceed to...
Can I?
Sorry?
A fast one, Maria?
Very fast.
Yes. Your evaluation, your classification of risk is purely on the time series. So it's on the movement. So you don't take it into account which is the object that is accelerating. So it's purely intensity.
That's a very good question. So for the current strategy, it is purely based on INSAR data. But maybe in the future, we would like to consider if what the object is and may also include the spatial information. And that will give us, like, we would know the risk, like, also from the, like, geotechnical perspective. Yeah.
Okay, thanks.
Okay. I remind you that there will be time for discussion in the end of the day for the roundtable of the formations. And now I invited the third presenter, Alexandro Lapadat, who will tell us about the multi-track INSAR datum alignment.
First, thanks for being here, choosing this session. We all trust INSAR measuring millimeter line of sight motion, but when we try to decompose that motion to 3D, the viewing geometry becomes our limitation. So line of sight is not equally sensitive to all directions. It is mainly strong for the up and east-west direction, but then the north-south becomes the weak link. Without any alignments to this, what we could do is to actually take into account what the Earth is showing us. So on the Earth, deformation happens on the surface, constrained by the ground geometry, and also constrained by gravity. And if we take those into account and postulate those assumptions, we might be able to recover what the east-up decomposition is failing to do. So this is one aspect of the decomposition, but actually any decomposition has another weak link, and that's related to multi-track alignments. So multi-track line of sight data does not automatically share the same datum. And if there's any offset between those two datums, that would be absorbed into the 3D decomposition. So my job today is to basically answer the question whether we can estimate 3D motion, but also align line of sight data at the same time within a decomposition. And we'll do that for the test case of Jakarta for land subsidence. So conventionally, many INSAR studies in Jakarta have mapped the city using the east-up decomposition, and most of them show a vertical velocity map, much like this one, where we have great resolution on the vertical component, but then there's nothing in the north-south component. Many times they don't even show any east-west motion. So this is an incomplete view of the 3D kinematics of subsidence in Jakarta. And what we aim is to move from such maps towards such maps. And such results are remarkable, I think, in two ways. First of all, each of these cells have associated a horizontal velocity vector. And as you can see, they also have the sensitivity of the north-south component. Second, each of these cells comes with a quality description, which allows us to say whether and where deformation is meaningful. So the question is, how do we get to such results using just INSAR data? And I will start by introducing some physical assumptions to the classic decomposition problem. So taking an example of a subsidence ball, what we could do is to take all our multi-track line of sight data and start computing these ISO lines. The ISO lines basically define the direction along which we assume deformation to be 0. Consider it just like a contour line for elevations, but for the deformation. A second step, what we could do is to discretize the ground surface with squares, and these are called regions of uniform motion, or in short, the RUMs. And then within each RUM, we can assume that all point scatterers share the same displacement and velocity. What this does for us, it defines these local spatial units where multiple observations from different geometries can actually be combined. And number 3, we can make an assumption on which direction motion is supposed to happen in a subsidence ball. So in terms of gravity-driven motion, we can say that positive horizontal motion is pointing towards the ball center downslope. This allows us to define for each RUM a transversal longitudinal normal coordinate system. And this framework is basically called the strap-down decomposition, in which line-of-sight observations can be decomposed into the transversal and normal directions along the iso displacement lines, because along that direction we have 0 deformation. The mathematical description of this work is given in the work of one of my colleagues, Witzke Brouwer, but for today, I'll mostly focus on how we expanded that in the case of Jakarta for the multi-track datum alignment. So let me start by introducing the input data set we used at hand. We have in both images Jakarta and the metropolitan area outlined in red. And we used Sentinel-1 ascending and descending velocity maps, which were estimated over the full time span of Sentinel-1. That's 10 years, 2014 to 2025. Now, each of these images comes with their own datum, which is defined by the mean velocity. And then, if we look at and compare the color between the two images, we might see these apparent color differences, which relate to the datum offset. So I think a logical question at this point would be, what would happen if I just take the data as it is, plug it through the strap-down method to see whether I get good or bad results? So we did that, and what we obtained is a transversal velocity field, so the horizontal velocity field, which is dominated by some red dots, which correspond to negative velocity. And negative transversal velocity means outward motion from a subsidence ball, which is kind of physically impossible in the context of gravity-driven motion. Then if these datums would be aligned, parts of those negative velocities will turn and become positive. So that would mean they will point towards the ball center. Now, having seen the impact of having misaligned data and just doing a decomposition, in the next steps, and the last part of the presentation, I will show how we actually align this during the decomposition. The very first step is to choose one of your tracks being your reference datum. Here we chose the descending track and we fixed it. And then the ascending track started moving relative to this one. By doing this, we basically sampled the TLN solution space, so the transversal longitudinal normal solution space, by applying a very small correction to the ascending track in increments of 0.1 millimeters per year. So then the question is, when do we stop? There are iterations, but when is our best solution achieved? So we look for that correction which minimizes the number of RUMs with negative transversal velocity, which means that we basically minimize outward motion from subsidence balls. Right, and by doing that, we are able to basically get the most optimal solution in physical solution. Here I have an animation showing actually each iteration and the results from the strap down. So below we have the transversal and normal velocity field, and here the associated standard deviations. What we see is that as the ascending track is shifted, the transversal velocity field is changing dramatically. We have this red region shifting from one side of the ball to the other as we go on with the increments. then the optimal solution is reached when we minimize this number of negative transversal velocities. And in case of Jakarta, this is at about 1.2 millimeters per year. So what we learned from this is that actually horizontal motion is mostly affected by datum misalignments. And this value in the case of Jakarta of 1.2 millimeters, in the range of -2 to 2, in which we search for the solution, these transversal velocity values could be biased with maybe 5 times more than that small offset. So applying this correction and running the final strap down lets us to go back to the final field. Right, I went a bit further. So this is what we expected from the beginning and what we look for. A 3D velocity field purely from INSAR with horizontal motion and 2 sigma quality description. Now, if we look into it for the subsidence patterns, we see that it is dominated by 6 major subsidence regions. And all of them show more or less the same patterns. Vertical velocity becoming stronger towards the ball center, and then all this horizontal motion pointing around each ball. The maximum subsidence in Jakarta over the last 10 years reached about 7.8 centimeters per year. And also horizontal motion around each subsidence ball is not negligible. It exceeds the 2 sigma confidence, and it's more than 1 centimeter per year. Now, outside of these balls, we have a mean velocity of 1 centimeter per year, which is not negligible in context of ongoing relative sea level rise. And this result is basically a static representation of the Jakarta's land subsidence, but what we can do as a final thing is to visualize this as a time-evolving 3D land motion. And I would like to capture your attention on the coastal region of Jakarta, which over the last 10 years was dramatically subsiding. And the only thing which was keeping the population from there away from floodings was a seawall. So you can imagine what could happen if that seawall breaks or if there's any kind of storm surge going over the seawall. So this kind of concludes that we are able to estimate 3D motion, but we are also able to visualize it in a different way than before to actually have a feeling of what's going on at each region in Jakarta, but not only. So this brings me to the conclusions. We have shown that the strap-down decomposition allows the reconstruction of 3D motion, including the northward component. And with the 2 sigma quality information, we were able also to point whether and where motion was significant. Second, by modifying this method, we were also able to align datum offsets and not let those errors basically propagate through the decomposition. And with the final result, we saw that Jakarta over the last 10 years was dominated by 6 major subsidence regions with values reaching from 7 centimeters per year in the vertical domain and 1.5 centimeters horizontally. Now, the key message that I want to bring along is that even though INSAR is weakly sensitive to the north-south motion, the Earth is actually giving us the chance to put constraints that might allow us to move from the line-of-sight observation to quality-informed 3D land motion. For more details on all the aspects behind these results, I linked this manuscript preprint, and also for the savvy people looking into land subsidence, we're happy to share the data over Jakarta with everyone. Thank you very much.
Thank you. So time for questions. There.
Thank you so much. I want to challenge your assumption. So in Jakarta, many tens of kilometers, and you have centimeter level displacement subsidence. Can you justify it's only gravity-driven horizontal motion? For example, depending on the aquifer depth and a groundwater extraction can induce the removal of loading induce rebounds of the crustal motion. So there can be potentially more complex response of the crust than just gravity-driven flow. I think this might be able to be tested, like some sort of like final element model, but I don't know if you have considered that.
I think it's a legitimate question. We didn't really look deep into it, but all what we know about Jakarta that it sits on soft soils. So I think the most logical response of soft soils when you basically reduce the groundwater is to subside and not have kind of a rebound effect around. It's mainly because you suck all the water out, so all that effective stress is kind of pulled by the gravity downwards. But yeah, it could be checked. We share that data, and we hope that people can do cool stuff with it.
Thank you.
I think the soft soils answers my question in this case, but I also would like to challenge the assumption. You're assuming that Young's modulus is isotropic. And there are a lot of cases geologically where it's not the case, like bedding in sedimentary sequences or foliation in metamorphic sequences. You might be able to geologically, if you have some a priori knowledge about the geology, adjust, from your purely circular case, but you're also assuming that that's isotropic.
Yeah, we started with the most simple assumption, and we didn't look very much into the geophysics of the problem, rather than the most simple way of understanding it. Yeah.
I'm not sure if you can see me. Yeah.
Yeah, sure.
Just a question. I don't understand this method very well, but am I correct in saying when you're trying to do your datum correction, you're just adding linear offsets to the data? But we know often these aren't physical linear offsets, they're ramps or bilinear ramps. And does your method account for those kinds of offsets?
So they don't, but there's a reason for that. It's mainly because our initial datum is basically the mean velocity, and that can be seen as a plane. So what we do is basically to search for that specific datum, which produces what our assumption is on subsidence poles, which is we don't expect, horizontal motion go out of the subsidence poles. So that's why they are basically linear offsets, yeah.
Can I ask a quick second question? Sorry, Sami. So just also to test your method and the robustness of your method, you say, in this case, you set your descending as a reference and change the ascending.
Yeah.
If you did the opposite, do you find the same answer?
Yeah, exactly. I've done that, yeah.
Okay.
Yeah. So the nice thing about it is you can really choose any kind of datum. You should be able to end up to the exact same solution.
Any other question? Yes.
So you have now tried combining two tracks with each other. How is the stability of that datum alignment considering n tracks, or if you have whatever 5, 6, 7, 8, 9 tracks, that grid search you are doing now would be very expensive, no? And probably also unstable. Can you comment on that?
That's a good question. The situation in Jakarta is that we only have 2 tracks. I expect more computational time for that. I don't expect that to fail, mainly because with more observations, your RUMs, your region of uniform motions, will basically be better constrained. So I think in terms of more data will basically produce a better solution in terms of redundancy, but definitely it will cost more, yeah. And it's something to check. I happen to work in Jakarta where there's only 2 tracks. Thank you.
Thank you. So we should proceed. I take opportunity to advertise for my talk in the next session because it's about the validity of this assumption that in what conditions works and what conditions not. So could be relevant if you're interested. Next talk is Alison Siedel from Karlsruhe Institute of Technology, on derivation of geophysical source model for gas storage cavern, convergence-related surface displacement from 10 years of INSAR at the storage cavern site.
All right, thank you for introducing me. Yes, I'm Alison, I'm a PhD student from Karlsruhe Institute of Technology, the Geodetic Institute there. And I want to show you today my part of my work as a PhD there. So, very long title. I'm doing geophysical modeling, displacement modeling of surface deformation at storage cavern fields, basically. So, why do we do that? Why do we need monitoring? Well, so these storage caverns, in case you're unfamiliar with them, they're artificially created spaces and salt layers to store gas and oil for energy storage, basically there. But because they're in salt and the pressure is kept lower than the surroundings, they keep shrinking. So they experience convergence, and that translates to the surface then. And to monitor this, and this displacement has to be closely monitored to prevent damage to infrastructure and so on. And there are many traditional geodetic methods, leveling, GNSS, and lately also multitemporal INSAR that are used to monitor this displacement quite successfully. And so it's the monitoring part. Then there's the modeling that is also commonly often done to predict the displacement in all three directions, displacement vectors basically, and also to determine long-term trends and so on. Conventionally, those models are very simply parameterized by using a linear trend in time and sometimes with a seasonal variation, and in spatially just assuming a subsidence bowl. So could that not be enough? Why do we need geophysics? So I was, at the very beginning of my PhD, asked, why do we need to model that? So with a complicated model, or why do we need to model that at all? Isn't that enough? And I want you to keep this question in mind while I introduce you to our area of study, the cavern field Epe in Germany. All right. Yes, here you can see Epe. It's a very big storage cavern field of more than 100 caverns that contain gas and oil on the image. Each of these diamonds is a cavern. The white ones are the gas-filled caverns. The black and blue ones are the liquid-filled caverns. They're a little bit separated. The liquid-filled caverns more in the western part of the field, the gas-filled caverns more in the center and right part of the field. And keep this distribution in mind because that's also going to be relevant. Where do I have to point it? Okay, sorry. Okay, then there's something that makes Epe a bit more complex because we do know about a second strong source of displacement there. That is a fen, a marsh area in the western part of the field that has strong displacements that can be related to groundwater. And those signals superpose. And then the first question that's actually relevant for monitoring is, how can we identify if deformation is caused by caverns or by groundwater? I want to show you a bit about the measurement data we have in Epe. Here first is the leveling. There are annual leveling campaigns. We have very dense spatial coverage on infrastructure and so on. And the measurements are taken once per year. And on the right, on the plot, you can now see a few slides of 1-year displacement differences. And what you might notice very quickly is that the amount of displacement, but also the spatial pattern, really changes throughout the years quite significantly. Yeah. Now we can look at the GNSS stations. There are currently only 3 in the cavern field, so no good spatial coverage, but it provides us with a good temporal coverage, and also with the 3 displacement vectors, also very relevant. And here we can see for the station in the center of the cavern field that we do have some horizontal displacements eastwards and northwards, and some vertical displacements that seem to show kind of a linear trend, maybe with a kind of a break there where the linear trend changes, and seasonal variations that are more visible in the east and west directed displacements. Now we come to the INSAR data, the data I processed myself. We have a very good coverage in terms of tracks, so we actually have 4 tracks available there. And I processed basically 10 years of Sentinel-1 data of all these 4 tracks with persistent scatterers and distributed scatterers. So the processing algorithm is stems-based and with a dedicated DS pre-processing algorithm developed by my colleague. And what we can see spatially is that all 4 tracks, we can see the strongest deformation in the center of the cavern field. The patterns slightly change depending on the look geometry. Really doesn't like me. Now. And we can see these different patterns. Not too complicated yet. It still could be a simple subsidence bowl if we only look at the mean velocities. But if you look at the time series, we get a very different picture. So, for example, we have here a time series of 4 different points throughout the cavern field. And we can see that if we look at a point in the center of the cavern field, this is the green curve here. We can see a very step-like behavior, some seasonal trend, but mostly a negative trend. Then if we look at the point in the fen, so this marked area there, the pink one, the star, then we suddenly see a very strong seasonal response, seasonal pattern. And one could think, as in the green and in the pink one, you can see this, in 2018, this strong drop. One could think that's related, but if you look more closely, you can see that the timing of this strong displacement change here is rather different. So maybe not the same source mechanism. But what you can take away from here is that, actually we have a very spatial, temporally complex displacement field, and it would be interesting to better identify the causes and, link the displacement to the causes. So, here another slide of a little bit more background for the cavern-related displacements. In general, why the surface moves above the caverns. So these caverns, as I said, are artificially created in salt layers, and the pressure inside of these caverns is always kept lower than the surrounding pressure, because that ensures that the caverns are sealed and the gas doesn't escape. But that also causes the caverns to shrink. And throughout the year, due to we want to use it as a storage site, the caverns are filled up. They get more pressure, and they're emptied in the winter when the gas is needed, and then the pressure is lower. So since we expect that this pressure difference is the cause for this cavern convergence, we would expect that throughout the year, with these changing filling levels, also the subsidence and the cavern convergence changes. And yeah, that's a bit what we could already see in these seasonal patterns. But it's even more complex because not all caverns in such a cavern field have the exact same filling levels, the exact same pressures, the exact same behavior. In EPE, there are many different providers, provider companies that use their caverns a little bit differently. You can see it on the plot on the right. And not only do the cavern providers use their caverns differently, but also over the years, you can see, depending on the year, for example, minimum cavern filling level changes quite significantly. So for 2018, you can see it was a very cold winter. The caverns got really, really empty. And in the 2 subsequent years, the caverns did not get so empty. So based on that, we expect very complex behavior, and we would need actually a good spatial temporal coverage for monitoring. So here are the answers on why we might need a more complex model, because the measurements we currently have are not really sufficient to really depict the complex displacement field, especially if we look at the horizontal displacements that we don't get from leveling and from INSA only with orbit combination, and then also not in north-south direction and so on. And it is these horizontal displacements that are problematic for the infrastructure. So that's those that we really want to know about. Yeah, and the second one is the signal source identification. How can we really make sure that the signal we have here is actually cavern related? And this is also kind of important because, especially in EPE, there are some people that like to paint the narrative that the displacement field there is way too complex to do any kind of interpretation and to link the displacements to the caverns. And I strongly disagree, and I want to show you this here. So I think I have to speed up a bit. Okay. So the thought is that we have these cavern filling levels. They are publicly available, only mean levels per provider, and we want to link them to the 3D surface displacement. Yeah, those models we use, they rely on local parameters, but luckily we have all this multi-temporal INSA data, long time series that we can use kind of as ground truth to run an optimization to get these local parameters. Very quick chapter, because we know about these very strong other displacements that are not cavern related, and we have them here. We, of course, don't want to use this to fit the model parameters to something else that's not cavern related. And yeah, one could exclude all the points that would be expected to show those behaviors, or all points in the FEN. But on the other hand, then we have a huge data gap where we would expect a horizontal maximum, and that's also not so good for the model parameters. So what I did here was use independent component analysis and to kind of split up the signals to different sources, and it did work quite well to identify 3 components, but 2 components could be linked to the FEN in terms of their spatial and temporal pattern. And this I used to use this FEN component and subtract everything of this FEN component from the original data. So this is not a perfect separation. There's still residual groundwater-related displacements left if you really look into the data, but it removes most of it, so the modeling works better. Now, the model is two parts based. One is basically based on simple salt deformation modeling, very commonly used models to describe salt deformation as an elastic part that deforms, and then an inelastic part, also primary and secondary creep. And the second one is a geotechnical model, the so-called Sroka-Schober model, that then translates the volume loss to the surface. Yeah, here's some equations. Basically, for the cavern volume change, we use these three elements. And we assume that the total cavern volume change is a sum of all these three elements. And these stress-strain models, for these stress-strain models, we use the pressure difference as the strain that the cavern experiences. No, it moves again. Yeah, and the pressure difference. But yeah, one issue is we don't know the actual pressures. So we do have to make assumptions for the cavern, pressure inside the cavern, and also for the lithostatic pressure. And this is a big, big source of inaccuracy for this model. Has to be kept in mind. And to account a little bit for that, I also made the option to add another parameter to be derived for each cavern, just to be a constant to add to this pressure difference, because this pressure difference is basically what drives this model, so to fit it a little bit better. One could say it is, okay, because we don't know really how, the exact lithostatic pressure, so we might have a lot of uncertainties there. On the other hand, we might also overfit a little bit because that introduces a lot of parameters. Okay, most of the values of these models, we just use literature values for salt rock. We actually only derive two parameters for this model. For the steady creep part that has the biggest influence, that are these A and N parameters. And this N is a very important one because that one describes the exponential relationship between the pressure difference and the cavern convergence, and with that, the surface displacement. Okay, with that theory, we create a cavern volume model for each individual cavern, depending on their provider.
1 minute.
1 minute. Okay. Okay, I have to be really quick. For the liquid-filled caverns, we use a linear model. This is terrible. And for the geotechnical model to translation to the surface, we have two local parameters that describe the geometry, basically. Now, this, here you can see the three components, the result of the model. Vertical displacement really looks like a subsidence bowl, but what's interesting here is the east-west and north-south directed displacements that are really irregular due to the cavern placement, due to the different types of caverns that are not what you would usually expect if you do the conventional modeling. Now I do have, come on, start. The delay is terrible, I'm so sorry. Huh? Could you? I'm so sorry. I brought a beautiful video for you for the displacements in 3D. And what I think you can beautifully see here is, down here is the filling levels. And as long as the caverns are relatively full, even in the winter, not much displacement is happening. But as soon as they get really empty, then you can see this sudden increase of displacement. And I think that's really fascinating to see. And I would love to show you more, but yeah. Here's the, some validation. Basically, the error is low except for the fan, but there we expect it because our model does not include any groundwater-related displacements. Also, the time series really fit surprisingly well to the INSAR data very closely. The temporal curve looks very, very good, very close. The displacements, the residuals, sorry, are rather small. Not again. And if we combine, if you look at all the geodetic methods, time series in the center of the cavern field, so we have the leveling, the GNSS, the INSAR, and the model, they all fit together very well here. Here for the horizontal components, we have less validation, but we have this one GNSS station where also the trend and the general direction fits very well to the GNSS. And here, look at the residuals in the fan. Those also show some correlation with the actual water level measurements there. Okay. Quick summary. So what this model is not, what it cannot be used for and should not be taken as is a replacement for actual displacement measures. And currently, and in generally also not, it cannot ever completely accurately forecast surface deformation everywhere in the cavern field, especially in terms of legal disputes, in terms of building damage and so on. So that it should not be taken for.
Thank you so much. Thank you, Ale. Jeszcze, okay. Jeszcze two last words, yes? Sorry, I interrupted you, yes? I interrupted you? Yeah. Okay, please proceed. Sorry.
Okay. Okay. Some limitations of the model. Currently, the derived parameters do not have much physical meaning because we only use these filling levels. That could be resolved if we had individual pressure levels for the caverns, but those are not provided by the companies, usually. Come on. Okay, but there's a lot this model can do. It can casually relate the cavern usage to much of the displacement in the cavern field. It can provide physically funded estimations for displacement where no measurements are available, especially for the horizontal components. It can support differentiating different sources and help interpretation of the measurements, and especially also reveal how strong the low filling levels affect the surface displacements. And it also proves that it's worth it to look at long time series INSAR data more than just mean velocities. Yeah, future improvements, it can be more complex. Here's the video again. Thank you so much for your patience.
Thank you, Alison. It was very complex. Luckily for Alison, we have some extra time because of the change in the program, and we don't have last presentation. So we do have some questions, time for questions for Alison.
I'm wondering, you show one of the first slides, you show the time series of when distributed scatterers, and then you see, and I think a lot of your pixels are distributed scatterers.
Yes.
Do you account for the phase bias error?
Yeah, actually we do a bit of, currently a lot of dedicated unwrapping. We look at non-closure phases in an S-bus graph, and really try to weed out pixels and also scenes that cause non-closure phases, and just then really make sure that we don't have non-closure phases there. Okay, I think that thing hates me.
Okay. Does anyone has a question? Okay, thank you very much.
Okay, thank you.
Does anyone would like to comment or have a question to previous presenters? Because we have like 5 more minutes. If not, I invite you for the coffee break. And we have also one last session about the formation after the coffee break, and in the evening, roundtable discussion.
here, speaker.
Okay.
And
Yeah,
the
this-
before speaker, she was.
Yes.
Doesn't work.
Okay, it has to be.
Doesn't here.
Okay.
Okay.
Okay, it has to be oriented.
Yes, yes.
And this is what?
This one, the last point.
Okay, so just for the slides.
The next slide, yeah.
You can't use it as a point.
No, because the charger, the battery is lower.
Okay.
Okay.
It's kind of tricky. Just one.
No. Just
Okay, so there is just one. It has to be oriented to.
Okay. Change the slide, not here. Doesn't work.
Toward this one.
There. Okay, that's fine. Okay, sounds great.
And that's all you have to know. The pointer is this one.
Just in case. Yes.
Ouais. Parce que moi, tant pis, il va tenir, je pense. Tu vois, il me reste 14%. Je pense. Oui, ça pourrait marcher. Okay. So you have the titles, yeah, for you.
Yeah,
it's
my
okay. I have time. Is it your bottle?
No, not mine.
Thank you. When and there's anyway good audience still at this time of the day.
Especially for the round table. Yes. One minute.
Is everybody there?
Some is not here. There's nothing in a hurry.
Sami is giving two presentations.
Yeah, it's amazing. It's there. Okay, good afternoon. So I think we'll start. So welcome to everyone. We'll start this last part of this very wide session about displacement and deformation. I hope you still have some energy for that. So we'll go for the first speaker. So this is Deodato Tapete. He's going to talk about synergies and results of XNL band SAR research and institutional support during emergency for A. Yeah, you will finish the title. Okay, thanks.
Yes, thank you. Good afternoon. It's my pleasure on behalf of the Italian Space Agency and in particular of the team in charge of this international cooperation with JAXA to present the activities that we are doing for many years now. In particular, I'm in charge of the joint research activity, which is one of the activities that this agreement between ASI and JAXA encompasses. So between Italy and Japan, there's a long-standing cooperation in the space sector. This is implemented by the two space agencies. In particular, there's a common interest in the use of synthetic aperture radar satellites. You may understand the reason, given that we have, both the countries have satellite assets, Cosmos SkyMed and ALOS. So you see that it's since 2009 that we have established a memorandum of understanding that was also followed by an implementing arrangement. And this implementing arrangement has been renewed several times as a proof that there's a common interest in continuing this cooperation. And the focus is about disaster risk management, because another commonality that we share between Italy and Japan, unfortunately, is the exposure to several disasters. So the purpose of this cooperation in particular is about three main activities. So acquisition by Cosmos SkyMed first and second generation satellites, as well as ALOS 2 and more recently ALOS 4 during emergencies. So there's a mechanism by which Japan may request through JAXA Italy to collect data during emergencies over the Japanese territory, and the same happens for Italy. Second point is making available some collections of these two assets in L and X-band to perform in synergy research activities on topics that relate the disaster risk management cycle. And I will come back later on this point in the presentation. And third, but not less important, is the collection of archives over the Japanese and the Italian territories. So equipping both countries with an archive that allows to perform pre- and post-event investigation as disasters happen. And as you can see, the cooperation since 2009 has developed to account for the evolution of the respective satellite assets. So second generation in the case of Cosmos SkyMed asset and ALOS 4 in the case of JAXA. So these two are the novelties that have been included since 2019 with the first second generation satellite launch. So I will briefly recall to the benefit of you all about the key important specifics of these assets. In the case of Italy, we have our flagship Earth observation SAR program called Cosmos SkyMed. Please recall that Cosmos SkyMed is an acronym to encompass the whole system. So the combination of first generation, typically indicated with CSK acronym, and the second generation satellites, CSG. But in LA, we refer to the whole system using Cosmos Skymed. As you see, and probably you know very well by your own experience, this system has been in place since 2007. We have made a great evolution because so far we have disposed 2 satellites of the former 4 of the first generation, and we have already replaced them with 2 fully operational second generation satellites, and we have the 3rd that has been launched early this year and is close to complete successfully the commissioning phase. And as you can see in the bottom right part of the slide, you see the current orbital configuration. So continuing the collection every 16 days for each satellite, then 8 days combining 2 satellites, up to 1 day for the tandem pairs. Cosmos Skymed second generation was not only about replacing with better technology the former satellites, but also expanding the portfolio of the imaging modes. So we improved the strip map mode, adding the dual pole and the quad pole functions that were not available with Cosmos Skymed first generation. In strip map mode, you could strip map image mode, you could only collect single polarization data. It was the strip map alternating mode that was dual. Now, strip map at 3 meter spatial resolution is also provided in dual pole or also with the special quad pole. We have improved also with respect to the very high resolution imaging modes because we have spotlight data that now reach less than 1 meter spatial resolution, also for civilian purposes. Remember that Cosmos Skymed was born and was conceived since the beginning as a dual mission, so serving also military purposes. In this table, you see basically summarized all the improvements that we have made, and this is the full portfolio of technical specifics that our colleagues at JAXA may request in the case of emergency response. While for the creation of the archive over the Japanese territory, I will show you there's of course a predefined agreed imaging mode. With regard to ALOS 4, our colleagues were very pleased last year 2 years ago to let us know about the successful launch of ALOS 4. ALOS 4 now is fully included in our agreement and does conserve to the benefit of the bilateral cooperation. Probably you know better than me all the specifics of ALOS 4 that we are very eager to see very much used as the years pass since the launch. You see also the complementarities that there are between ALOS 4 and Cosmos Skymed first and second generation satellites. So you can easily understand, apart from the combination and the synergy of different radar bands, there's also advantages from the synergy in using different imaging modes. And here you see clearly the various modes. So I would say that also ALOS 4 encompasses the various opportunities to suit the different applications, spanning from the spotlight up to the scanner. I have to say that, of course, for the benefit of our cooperation, the strip map suite is the one that is mostly useful for disaster management, but I will also say that the scanner option is pretty useful. We saw, not as part of our cooperation, but as part of a multilateral cooperation with regard to the 2023 Turkey earthquake, because in that case, scanner data were provided by JAXA, of course, by ALOS 2 at that time. Here is a slide just to recall what's possible with regard, for example, to the various imaging modes and the various type of disasters. So in case of volcano eruptions, as opposed to flooding events, we span from very site-specific observation scenarios up to wide area assessment. That's another functionality that makes this cooperation very successful and meaningful to both the parties. So let's start looking at the three main activities that our implementing arrangement encompasses. The creation of archives. So Italy, through Cosmos SkyMed system, regularly collects strip map image, HH, mode data at 3 meter spatial resolution over the whole Japan territory. We cover both in ascending and descending orbit. The effort here is to ensure that the Japanese territory is fully covered across the year. That's the key point. The idea that both the countries and us, their space agencies developed since the very beginning was to have at least one full coverage in both geometries in order to be sure that as soon as an emergency activates, we have at least a pre-event image scenario. As you see from the efforts, as of June this year, the amount of standard frames that have been delivered is huge. These happened seamlessly from the first generation to the second generation. So you see the archive that we have built over Japan, of course, for the Japanese institutions and the Japanese research community, but this is also part of our catalog. Similarly, JAXA covered the Italian territory with ELOS 2, and now with the launch and the successful decommissioning for operation of ELOS 4 makes over Italy. Again, the approach is the same, of course, given the different ways we collect data with our assets. In this case, we collect strip map 10 meter spatial resolution dual pole, so HH and HV mode, for coverages, making sure that, again, the Italian territory as the Japanese territory is fully covered. And as you see, again, in a huge effort from ELOS 2, I have to underscore in this case that the effort was even more appreciated because, you know, the life of ELOS 4 over the past years, ELOS is not so young, and anyway, over the past years was targeting Italy, providing without interruption collection of data. Although, as you know, as SR mission goes longer than the nominal lifetime, the percentage of the data that can be collected decreases significantly. But this is why all these efforts are made. The point is having a consistent and regular data tasking over the whole territory. That's the important point, not just focusing on some areas. And this aligns very much with the activity that the Italian Space Agency already since 2011 was doing. So collection according to the so-called Map Italy project. Of course, over Italy, with Cosmos SkyMed data, we collect at higher, much higher temporal revisit that we do with ELOS 2 because, of course, of the national focus that we have, the fact that we can use all the satellites. So over Italy, in addition to that coverage provided by ELOS 2, we have every 16 days on both geometries the full Italian territory covered. Again, strip map image mode, 3 meter spatial resolution, single pole. That was the predefined observation scenario that was defined according to the user, the institutional user feedback, and in particular the National Department of Civil Protection, because you may understand that disaster management involves deeply the bodies in charge for the government to manage disasters. So second activity is the joint, still emergency response. So in this case, we collect data on purpose as soon as one of the two countries requests data for an emergency. So this was a very effective mechanism, because in addition to our own ways to collect during emergencies, both countries could count on the other country capability to collect in very urgent response way. Compared to Fringe 2023, I will not repeat the results that we achieved over the previous emergencies, but just to mention that we span from earthquakes to mud flows, using both interferometric techniques, especially in those areas like central Italy covered heavily by vegetation. So the added value of L-band data for us was crucial, alongside the high resolution provided by Cosmos SkyMed, as well as the higher temporal revisit provided by Cosmos SkyMed, but also change detection methods. And here you see just these examples. But more recently, there wasn't a time at Fringe 2023 to mention this emergency, because that was one of the most alarming and warning emergencies that we have in recent years in Italy, because you may think that floods just last for a few days. Unfortunately, in Italy, that we are not a tropical country yet, I would say. With the climate change, we are experiencing floods that extend for weeks, and in this case, for months. This was a very catastrophic disaster affecting half of one of our widest and largest region. So our main aim was not only depicting and delineating the flooded areas. You see here the map that was produced as part of the national and European civil protection system activated during emergencies. These maps are produced using Cosmos SkyMed data as part of the national system for civil protection on behalf of the Italian civil protection department, and including CIMA Foundation, who's our center of excellence and competence for the hydraulic risk. But I also want to show you this other map that is not so common, but unfortunately is becoming common. In this case, we are mapping the flood duration. So it's not only where we have flooded areas, but for how long those areas are flooded. This was the very first event in Italy where this type of assessment was crucial. So we needed to repeat several times, not just for a few days, but we did it for weeks and months in some areas. Also because the Emilia-Romagna region is very famous for the productivity in agriculture, and not only, also for the tertiary service, is an alluvial plain, mostly dominated region. The soil was very much saturated, and it took in some areas months to evacuate waters. In this context, we produced several of these mapping products, and here is the contribution that JAXA provided. They included specific acquisitions over some of the mostly heat-affected areas, such as Ravenna and Faenza, and provided us other images to increase the temporal frequency, because we needed even with the simple change detection methods to see the gradual evacuation of water in order to inform how to evacuate people or allow them to come back home. And I would say that something similar happened in this emergency in 2024. This time it was the Noto Peninsula earthquake emergency. It was JAXA requesting data. As you can see from the timeline, the earthquake happened, I would say, as usual, in the worst possible period of the year. Unfortunately, we experienced that. Disasters do not look at the calendar. It was the very first day of the year. We were contacted in emergency mode. You see how JAXA, according to the same multi-sensor data principle, included several acquisitions, and in this case, collection from first and second generation satellite data were helpful. And you see here that the combination of data at different epochs, so frequent according to that timeline, allowed, for example, our Japanese colleagues to see the effect along the coast. The earthquake exposed a lot of coastline areas. So I now conclude my presentation referring to the joint research activity because of course, both Italy and Japan have a strong consolidated INSAR communities. We include specific research activity line in our implementing arrangement because everything started from disaster management. We included this topic. But as things changed over, I would say, more than a decade now, we also expanded our portfolio to encompass climate change-related topics because we acknowledge that disasters now have much relation with climate change-inducing factors. Land cover, land use, because these data are also helpful in the preparedness phase to understand if changes in the land use, land cover may affect the future susceptibility and also potential impact of disasters. And also, this is also an effect of our huge involvement in the Committee on Earth Observation Satellite Working Group on Disaster. We have included also the recovery and reconstruction phase. And we moved also towards the time series analysis because you saw that the archive very much underscored the point of having at least 2 or 4 coverages a year, while we recognize that in some areas, we know very much those areas are more susceptible than others to disasters, and we need more frequent observations. You see here an examples over Rome, Phlegrean fields in Naples, areas affected by landslides in the south of Italy, an area that some colleagues from the Italian community know very well in Apulia region because there are also flood susceptibility. And as you can see, an excerpt of the amount of data that were taxed on purpose. And we hope with the community to use this data to develop research. And for those of you who attended my presentation 3 years ago, we have moved further in the use of multi-sensor SAR data to address disaster risk management. So our interest is also more strengthened, given that, as you probably know, SAOCOM, the other L-band important mission that we have at the moment in the SAR portfolio is including Europe and Italy, because it is a bilateral cooperation between Italy and Argentina. So over Italy, and not only, but also in Europe, we are collecting regularly this data. So you see, we are strengthening X and L band synergy, providing collection of data. And as you can see, I show you again the orbital configuration of Cosmos Sky data, but now you see 2 blue dots because the SAOCOM data are on the same orbital configuration as Cosmos Sky data. So you see now a multi-sensor scenario here. Halos, Cosmos Skymed, SAOCOM data. So in conclusion, for us, this is an exemplar of long-standing partnerships between space agency. I'm very glad that ESA wanted to assign our presentation to this topic, because Fringe is also about cooperation. It's also important to recall that the activities that we do at national level and in bilateral cooperation serve also in preparation of the ESA missions. So here we are already developing codes and algorithms that we know for sure not only are applied to Sentinel-1 data, but also in future for Roselle data and of course for NISR data. And with this, I thank you for your attention.
Thank you, dear Dato. For time's sake, because we have 5 minutes late, so yeah. So I propose you just save your question for the round table discussion. And now we welcome our second speaker, Samir Asfahan. Sorry. And he was talking about exploiting the gradient direction constraint for 3D decomposition of insular life-side deformation in subsidence areas. Please.
Hello again. So I have a quite good introduction by colleagues from TU Delft last session, so I'm directly jump to the main point. Some recaps. If you have one track observation for each pixel, we have one equation, 3 unknowns. We cannot solve it. If you have descending, ascending, we have then 2 tracks, still 3 unknowns. We cannot solve it, except if we have some assumptions on that. Some common practice is ignoring the north component. There is a logic behind that. We say that INSAR has low sensitivity to the north component, so let's ignore that. Then we have 2 equations, 2 unknowns, and solve it. Or somehow we should put another constraint on the direction of the horizontal component to solve it. If we ignore the north components, of course, we make errors. Most of the people know about that, but I just show it what that error looks like. If we have 2 equations, 2 unknowns, we can solve it. Where is the... Okay. We can... We can solve it, and yeah, this is perhaps better. Yeah. So we can solve it, this equation, and then if we put all these 2 equations together, we can derive the error or bias that we cause by ignoring the north component. How this looks like is a long equation, but the error that we make in the up component and east component, it depends on the incidence angle of the ascending and descending track and heading angle of the, or ground heading angle of the ascending and descending track. But I make it a little bit simpler. Assume if you're working in an area with the same incidence angle. It's not the case, but just to make the equations a little bit simpler. If the incidence angle of ascending and descending is exactly the same, those complicated equations become much simpler. And you see that here, the error that you make in the up component and east component is, of course, some scaling factor to the the real north component that we ignored, and depends on the sign of the difference between the heading of ascending and descending, of course, tangent of theta, and difference of the cosines of them. I put these 2 equations. This is for incidence angle of 40 degrees for ascending ground heading and descending ground heading here, you see. And then you see this is the scaling factor of the north components that will leak to the vertical and east components if we ignore the north component in the composition. So I put also some cities here, Krakow, Iceland, New Zealand, based on the current satellite setting of the Sentinel, just for example, that you see how much error we make if we ignore the north component. In most of the mid-latitude areas, just a couple of numbers to keep in mind. Something around 20% of the north components would leak to the up component, and something around 0 to 5% of the north component will leak to the estimated east component. So the vertical component is more contaminated by the bias here. Anyway, if we can go also, instead of ignoring north component, say if we know the direction of the horizontal component based on some other constraint, then we can write the equation based on gamma. Gamma here is the azimuth of the direction of the horizontal component. Then we have again two equations, two unknowns, but we need to know what is gamma. That's the constraint that we should make in the decomposition. Here is the one that also we see in the previous session, that I call it gradient direction constraint. It means we assume that, this is, I'll put in here in yellow, the horizontal gradient of the vertical deformation is aligned with the direction of the horizontal deformation. Or here, the arctangent of derivative with respect to north to derivative with respect to east is equal to the arctangent of the north, the fraction of the north and east components of the formation. Here also, this is I just yesterday looking for some image for this. This is, I see that we have this visualization at Fringe 2009 in one paper that we show this direction of the horizontal deformation and some AI representation of that. What this constraint mean, that the horizontal deformation is always towards the slope of the deformation field, not a slope of the topography, just a slope of the deformation field. The main question is, of course, if the point is, if we have this, these are a couple of questions. Under what condition is it valid? So we can use it. If is it valid, how we can compute it? Because it's a bit how to compute tilt. This is important. And if it is valid and we have a tilt, then we can estimate the horizontal components. How precise we can do that? First question, under what condition is it valid? Let's first look at very simple point source. This is a proof of that, but for the point source, Mogi-like source, it is exactly the same. So the direction of the tilt and direction of horizontal deformation, analytically we can prove it that is exactly the same. So for these kind of sources, or we use a lot in the modeling of, for example, volcanoes, this follows the physics of these simple models. But what about if we have more complicated source of reservoir aquifer? So if we discretize the reservoir in different patches, then we should prove that if this condition should want to be valid, we need this constraint to be valid, and it is not necessarily valid always. So we put a lot of, I try to expand these summations to try to prove that in what conditions mathematically this is valid and what not is very complicated, and we couldn't really find any mathematically proof of that, and it's not in general, these two are not the same thing. But at some conditions could be an approximation. That is the main point of this presentation, that at what conditions we can approximately use this constraint. We did some test simulations, still continuing for different mechanisms, but it gives some good insights that what kind of parameter is important for this constraint to be valid. This is simple disc-shaped reservoir or aquifer, everything homogeneous at some depth. We discretize the disk with a very small cuboid, and then based on the response function based on the pressure change, we do the integration, we simulate the surface deformation, east component, north components, the amplitude or magnitude of the horizontal component and up component. And if we take the sorry that they don't have a title. One of them is a direction of the tilt, one of them is a direction of the horizontal component. So this is a difference, almost zero, plus the standard deviation plus minus 1 degree. It's not exactly zero, as you see that it's not exact point source, but so far so good. If in plus minus 1 degree is good constraint that we can use. A little bit more complicated ellipsoidal shape source, the error become bigger, and the depth of the source is 300 meter. Same source, if we go to 2,000 meter depth, the error that we make, this constraint become more valid when you go more in depth. For the deep sources, this is more, we can say this is more in general, is more validity we see in this constraint to very, very shallow sources. A little bit rotation, still you have errors in the source in 500 meter. Rectangular source, we don't have that much in nature, exactly rectangular source, but if we have still, you see the mean is 0 for all the pixels and plus minus 4 degree, still it's a good approximation still. I'm starting to go a little bit to more random shape sources, but very still smooth. Still you see plus minus 2. A little bit more complicated shape at 500 meter depth. We see that still the mean 0, plus minus 5. But this plus minus and standard deviation, you see, you can sometimes have around, at some locations, 20 degree difference between, but it is approximately, they show the same direction, the tilt and the horizontal deformation. The same source, instead of, what was that, 500 meter depth, I'm going to 3,000 meter depth, and you see it's very, very, this constraint now. It seems that we go more in the depth, the more validity of this constraint we see in the complicated shape sources. Very complicated things, it's just, we put the roughness of the source in the parameters, and it's just randomly make a shape for us. Not very realistic, but it's good to see that if the shape of the reservoir or aquifer is very strange, how this behaves. So plus minus 11 degree standard deviation. So if we said plus minus 3 times standard deviation, it means plus minus 30 degrees. It's quite a lot. The error that we make if we put it in the 3D decomposition could be high. So for complicated shapes, it's a little bit tricky to use the assumption. If we go deeper with the same shape, much more agreement between that. So in general, the more go deeper, we get better agreement. And the final simulation, some heterogeneity in the reservoir. So for all the simulation that I show you, it is assumed, for example, pressure change is exactly the same. There is no fault in there. There is no any special variation on the thickness of the reservoir, on the bedrock. Everything is the same. So when you start to add heterogeneities, these errors become bigger and bigger. I'm not trying to show different things, but the thickness of the reservoir or aquifer, the variation of the bedrock depth, all of them can contribute to this agreement here that is valid or not. What we learned from the simulation so far, for deep sources, is valid, more or less. For a smooth, simple reservoir aquifer geometries, it works. This is the third one. I put it as a hypothesis. It looks like, it seems, the behavior is like that, but it needs more verification. It seems that for deformation dominated by volumetric strain, it works. But when any deformation you have, or any source that you have deviatoric stress or strain, then this start to show that you cannot use this constraint simply. But for very shallow sources or complex geometries or strong internal heterogeneity in the reservoir aquifer, this again you start to see deviations. Overall, for many realistic geophysical sources, the assumption is approximately valid, but not always. So assume somewhere in some sources we have, for example, deep source volumetric strain just subsidence, then we say we want to use it. It's a chicken and egg problem because we need the direction of the tilt to put as a constraint. But tilt is derived from the vertical deformation, but we don't have a vertical deformation. So for the tilt, we need the vertical deformation. For the vertical deformation, we need a tilt. So how we propose to do it, just based on iteration. So in the first iteration, we just do the classic approach, ignoring the north components. Of course, we make errors, we solve, but this is just initial point to start the algorithm. We get the vertical component, then we take a derivative of that. Then we have we can compute the tilt, we can compute the direction of the tilt, then we can put it as a constraint in the equation and solve it. And then we have a new vertical component, we can compute the new tilt, and then we can compute the new horizontal deformation, and then we iterate till we converge. And then at the end, we have a 3D, the full 3D component, similar to the approach that we see in the previous presentation in the previous session. There is a small remark here. Even if we know the tilt and if we know it correctly, fully correctly, even from auxiliary data, assume we have a precise GPS and exactly we know what is the direction of the horizontal deformation and we put it as a constraint, still when this direction is close to the north-south, or it is close to the heading angles, ground headings angles, the equations, the matrix that we should invert, it's 2 by 2 matrix that we should invert to solve the problem, they start to show instabilities, ill-conditioned system. So it's very sensitive to noise, very low precision. It's not ranked effect. You can invert it and solve the problem, but you get crazy numbers that is not really physically meaningful. The precision is very low. So for those areas that still the direction of the tilt, it is close to the north, so plus minus 2, 3 even sometimes the degree, we need more restrict assumption or constraint. We go again for the same constraint, but here instead of say we fix the direction, we also fix the scale. We say the deformation in the direction of the tilt is some scaling factor multiplied by the direction of the tilt. This K then is estimated based on the adjacent pixels, and then we interpolate on those pixels that have a problem. So for the pixels that we don't have this ill conditioning, we assume that this K is dependent on the soil and mechanical behavior of the region. So we assume that areas close to each other have the same properties. We test it. We're looking for some area that we have GPS data to solve it. The initial case studies of this study was a couple of megacities in Tehran that we have a poster for that. But the point was, in any of these locations, we have just one GPS or a couple of GPS outside the subsiding area, so it's not possible to use it. The Groningen gas field in Netherlands is a very good case study because there are lots of data, both INSAR and GPS, already available openly, and we can use it for at least validation to see how this assumption works here. So this is the final results of the algorithm. Tilt, north-south gradient and east-west gradient, and it's the magnitude of the tilt. In it is millimeter per kilometer. We forget to put millimeter per kilometer per year. So this is the actually strain rate, similar to a strain rate. It's not a strain actually. It's a tilt. It's a gradient. But then we use this tilt in this iterative approach to decompose the north-south component and the east-west component of the deformation. And then on the location that we have GPS, we can compare it now with the horizontal components that we derive from GPS. These are GPS. We took one of them as a reference point. Here, you see, it's a reference point, is a zoom in that area, and this red box, we assume it as the reference area of the insert data. And these are the results based on what you see in the horizontal axis is the GNSS or GPS results, and the vertical axis is the components east to west, north, south, and vertical components that we get from our approach. What is the red and blue here? The red ones are the ones that are ill-conditioned in the system. So the direction of the deformation north component is more or less in the north-south direction. The system was ill-conditioned, so we need more constraint. This is also comparison, because when we look at just these plots, it's a little bit dispersion you see, so you can say it's not very precise, but we fixed the horizontal direction here just based on GPS. So we get, instead of using our approach for the gradient deformation, we constrain it based on the horizontal components that we get from GPS, the direction. And we see the results, at least for the ones that we don't have this ill conditioning problem. It is quite similar dispersion we see. So we can argue that even if you constrain it based on the correct horizontal components from GPS and this method, they both give the same results, same dispersion. I think I don't have time, so I wrap it up. So this is also the poster, still the poster is there. So we did this on different megacities in Iran. This is Tehran, Mashhad, Isfahan, to come up with not only gradient of vertical deformation, but also use it to decompose to north and east and compute the gradients, the strain tensor in these areas. Some take-home message, of course, for simple, Mogi source is exact, approximately valid for many realistic subsidence systems, enables retrieval of the node components from dual-track INSAR, most reliable for deep, smooth volumetric deformation sources, but we should use it with caution and validate whenever possible, particularly in regions with complex and mixed deformation mechanisms, especially when we have tectonics and subsidence together or any kind of isolated deformation of structures. These assumptions perhaps not valid for those mechanisms, and we use it, then we get a mixed or biased results again. Thank you.
Okay, thank you, Sami. We're still a bit late, of course, but if there is a very quick question, we can have, and Hugo, you can come if you want for the next one. Yeah.
Thank you, Sami. I have a question regarding whether you looked into using not tilt, but maybe the principal strain or principal strain rate directions to do this for the more complicated situations.
How? I don't get it. How we can use the direction of principal strain for that?
So that can be derived from INSAR and would be the direction of maximum deformation, and in complicated cases, that would not be aligned basically with the horizontal motion or the tilt that you have. So I feel that could be a next step towards
we should look at it, but I can imagine a lot of different situations that the direction of principal strain is not necessarily the same as the direction of horizontal deformation. And then I don't know how then we can use the principal strain for as a constraint, or we should discuss it. I think it's interesting.
Might be issue for strain measurement as well, so I don't know. Yeah. So maybe we can move on and we can continue discussing about that. So next talk by Hugo Vatin. Thank you, Sami. So it's going to be about slope processes in Tibet from large-scale processing.
Okay, so hello everyone. So my name is Hugo Vatin. I'm a third-year PhD student, currently working at the CRPG in Nancy in France, and supervised by Simon Daou and Jérôme Lavé. And today I'm going to show you some of my results on the periglacial dynamic of the Tibetan plateau. And what I want to show you today is that the Tibetan plateau is affected by widespread slope processes and that are not currently documented at large scale. So let's have a look. So the Tibetan plateau is a high elevated area with a periglacial environment, and in such environment, the uppermost part of the ground, also called the active layer, freeze in winter and thaw in summer, which leads to a cycle of heave and subsidence of the ground. So this type of ground are called seasonally frozen ground. So it's in pink in this figure. It's covered approximately half of the Tibetan plateau. And you can see that the other half is made of the blue color, which is permafrost. So for permafrost, it's exactly the same structure at the top. You got an active layer that freeze and thaw, but below it, you will find a permanently frozen ground. Okay? But currently, with the warming climate, we can have some warmer than usual summer temperature that can melt the uppermost part of the permafrost, and this can lead to permanent subsidence of the ground. On slopes, solifluction processes can take place in periglacial environment. So solifluction, if you don't know what is it, it's the slow downslope movement at speed of millimeters to centimeters per year of the soil due to freeze-thaw processes. So here you got an example of which kind of landform it can create. So a big, low-bait landform that you can have just here. So if we put some sensor of one on this lobe and look at the displacement in the parallel and the normal direction, you got here the plot. So if we first focus on the red line, you have the component in the perpendicular of the slope. And what you can see, it's heave in winter and subsidence in summer. And if you look at the parallel of the slope component, so the downslope component in blue here, you have stabilization in winter and movement during the thawing season. This kind of movement have been observed thanks to INSAR. So I just show you an example here in the northeastern part of the Tibetan plateau from Dao et al. 2020, where you can see here on this complex, on this moraine complex, a cross section where you can see on all the east-facing slope are going eastward in blue, and all the west-facing slope are going westward, which is typical what you can find for gravitational motion. But it's not the only place where you can find this kind of observation. There is several examples in the bibliography. For example, in Norway, Iceland, or other places in Tibet. And what you can see in all of these places, it's, for example, on the field, some low-bait landform, typical from solifluction. Or if you can't go to the field, you can go on Google Earth and look at this low-bait landform from Google Earth, and here in Iceland or other places in Tibet. The question today is, can we observe the systematic periglacial slope processes across the Tibetan plateau? And if yes, what are their magnitude and main controlling factors? So for that, we took advantage of the FlatSim data. You got a presentation about that yesterday. So FlatSim, it's an automatic, it's a service that automatically processes Sentinel-1 data based on the NSBAS processing chain. It produces a lot of different products, like interferograms that we're going to use today, but also loss velocity maps, phase delay time series, and a lot of validation data set. And why are we using this data? What are the advantages? In fact, they are produced using a really large amount of beam that can then help to construct really long tracks. So it helps to have a good phase continuity over a really large area. It can also help to find the good path for the unwrapping. Another good point is we got a really early atmospheric correction using ERA5 data that will help to reduce the fringe rate and facilitate the unwrapping. And we also include in the network 3 months and 1 year temporal baseline interferogram that can help to limit the biases in the time series. So for this study, we use approximately 30,000 FlatSim interferogram covering this region here at the east of the Tibetan plateau, covering permafrost and seasonally frozen ground area. And the dataset is ranging for 2014 to 2020, and with a ground resolution of approximately 120 meters. However, doing an INSAR processing in periglacial environment, it's pretty challenging. You can have unwrapping error. So when in winter the ground is freezing, it can be really strong and really fast, and can lead to high fringe rate, and that can be really difficult to unwrap. There is also fading signal, because you can have rapid change in soil moisture in summer, and this combined with multi-looking lead to fading signal. We also need to adjust all the tracks to a common reference frame to remove the discontinuity between the tracks and reference everything to a stable area. Okay. And the last point is biases with the east-west up inversion that is not suitable when you want to look at really shallow slope processes. So we need to find a new reference frame. So let's start with the minimizing the unwarping error. So you got an interferogram here where you can see a strong phase gradient associated with basin, just here, that are just freezing. It's a winter interferogram. If we unwarp it using our growing region algorithm, what you can see, it's several unwarping errors that are highlighted here with the red arrow. So we need to find another solution, and this solution is to reduce the phase gradient by removing a model before unwarping. So for the model of deformation, I will use the raw flat sim time series that I will decompose and extract the seasonal component that I will use as a model of deformation. So the goal is here is to find the coefficient alpha multiplied by this deformation model that we have to remove to the initial interferogram to maximize the coherence on the reduced interferogram. So when we achieve to find the good alpha, we can then unwarp this interferogram. You can see that there is no deformation because we remove everything. And then we can add back the deformation model to recover all the deformation. So we do that for all the interferogram. So we start an iterative time series inversion to identify inconsistency in the network, remove the wrong interferogram, and we run a final time series inversion with automatic correction of the unwarping error. Now, let's talk about the fading signal mitigation. So we used 3 months and 1 year interferogram in our network. However, when we look at the residual between the interferogram and the reconstructed time series, so the observation and the time series, what you can see is that there is still some residual, positive residual here for the 1 year interferogram. However, we really trust our 1 year interferogram. They should be less affected by systematic biases. And we should have zero residual here. And moreover, they are really well unwrapped thanks to the previous methodologies that I show you. So we choose to overweight them using the time series analysis and to remove the residual here on the 1 year interferogram. So now that we have a good time series, what we can do is to make the temporal decomposition of our data. So with linear, for example, and an amplitude. Here you have an example of the linear. We need to remove the discontinuity between the tracks before doing anything else. So for that, what is done classically in periglacial environment is to make a filter in space and time. However, if the size of the filter is too narrow, you will remove some periglacial deformation. So what we did is to take a large filter just in space, and we weighted using a proxy that is based on the seasonal deformation amplitude, because it can give us information about the areas that are stable, okay, that are not freezing and thawing, and the areas that are unstable. And we want to reference our data to the area that are stable here. So we use the weighted Gaussian filter on our time series, and then we can redecompose it and get some loss velocity maps that are well referenced on stable area. Now, let's look at the reference frame. As I told you, it's not suitable, the east-west up decomposition, so we need a local reference frame, and we're going to use the parallel and perpendicular reference frame. So for that, we add 2 rotational matrices. The first one based on the aspect of the slope, and the second one based on the slope angle. So we need to have a DM for that. And we make the hypothesis here that we don't have lateral displacement, and that's work for our gravitational motion. Okay, so now here comes the result. You are looking here at the seasonal amplitude in the perpendicular, reference. Okay. What you can see, for example, in this area where there is a star here, it's the time series. You have the freezing in winter and thawing in summer, with a maximum of thawing in the 1st of October. And what we can try to understand is what controls the spatial repartition of this seasonal amplitude. You find them on a really low angle area, usually in unconsolidated sediment, next to river network or water bodies, because you need to have water availability to make the freeze and thawing processes. So now let's look at the velocity in the parallel of the slope. This is a map. What you can see here is widespread e-slope processes across the Tibetan plateau with velocity ranging around millimeters to centimeters per year. Okay? And what we can see when you go to Google Earth on one of these rate points is really smooth mountainous area. And if we zoom a little bit more, you will be able to see this lobate landform. And it's not only on this rate point that I show you here, it's everywhere in the Tibetan plateau. If we look at the time series, so now at the bottom here, we can look at the time series in the parallel and perpendicular direction. So here it's the perpendicular direction. You can see the eve and subsidence of the ground and repeat cycle year after year. And if you look at the parallel component, what you can have is a winter stabilization and movement downslope in summer with amplitude here around 1 centimeters per year. We can even, with this methodology, we can even go deeper in the processes that are affecting the slope. In fact, solid friction is a mix between different processes. One of them is the frost creep. So you got the ground that eve in winter and subside in summer, and which lead to a displacement of the particle from the top to the bottom that depend on the slope angle and the amplitude of the eve. So for this pixel, for example, we got an information about the eve for all the pixels. The other component, it's what we call jelly friction. In fact, in summer, when the ice lenses are thawing, it can induce shear next to the thawing front. So this is the second main component. So as I was telling you, we can calculate the frost creep. And for this pixel, for example, if we take the slope angle and the amplitude, we got approximately the 27% of frost creep and 73% of jelly friction. And it's not only limited to this pixel. Everywhere in the Tibetan plateau, jelly friction seems to predominate the movement. And we got some other observations that can highlight this. In fact, these displacements are not everywhere. They are mainly focused for the high velocity in permafrost environment that is highlighted in blue here. So you can see that all the red area are in this blue area. So this highlights the really important ground thermal regime. The ground thermal regime controls the displacement here. If we look at the velocity versus the mean annual air temperature, you can see that we have a really high velocity where we have really a low amount of temperature, of mean annual air temperature. And this corresponds to the area where you can have really deep ice lenses formation at the bottom of the active layer. So to make it clear, this is a cross-section. And with this low temperature, you have the formation of deep ice lenses, ice-rich layer that can form at the bottom of the active layer. And in summer, when everything thaws, it can lead to shearing at the bottom of the active layer. However, as I was telling you at the beginning of this presentation, permafrost is thawing. It's thawing across the Tibetan plateau. So here you got the map of the downslope velocity with highlighted permafrost area in blue. And what you can see, it's all this area also subsiding, and subsiding is a synonym of permafrost degradation. So what we think is that with warmer than usual temperature, the upper part of the permafrost degrade, which lead to subsidence of the ground, and this can lead to a deeper shearing zone that can lead to movement on the surface. So to conclude, we observe widespread e-slope processes across the Tibetan plateau with velocity ranging around millimeters to centimeters per year that are mainly controlled by the slope and the ground thermal regime. They are mainly driven by seasonal basal shearing, and we can wonder if it is a long-term behavior of the ground or a transient response to recent warming. Thank you very much.
Thank you, Hugo. Actually, we have time for questions. Yeah, there.
Thank you very much. Very impressive result. I'm not familiar with that area. It seems like snow cover is not a problem for you in the processing.
Excuse me, can you repeat?
Snow cover.
No, in fact, it's really dry, the Tibetan plateau. And when there is some snow, it's really dry also. We have some trouble for really few days, but we just remove them and it's all right. But yeah, no problem with the snow, so it's pretty nice.
Thank you for the presentation. I have a question regarding the stitching technique that you used for the common reference framing. Is the Gaussian function that you are implementing doesn't necessarily smooth your results? I mean, doesn't just reduce the extreme values and also reduce the extreme values that you have in the subsiding and uplifting regions?
So it really depends on the size of the filters that you use. So for that, we made a semi-variogram of the biggest basin that was moving, and we took the semi-variogram result as a variable to take the size of our filtering. We don't want the Gaussian filter to filter our periglacial processes. So you need to take it larger than the processes that you are looking at.
Hi, thank you very much for the presentation. Do you have any in situ data that you are going to compare with, or?
That's a really good question. In fact, in the Tibetan Plateau, there is no study that are currently looking at these processes. There is one study, but it's really, really old and not in this area. In fact, I went on the field in September last year to put some humidity and temperature sensor and some, it's strange, but geomorphologists use tubes that they put in the ground to see the ground deformation. They come 4 years after, they dig a hole and they look at the deformation of that they can see in the tube. So I put some there, and I need to see in few years if there is if it fits with the result here.
Thank you very much.
Very short question, please.
Thank you. I was wondering, in my experience, accumulation or growth doesn't go at the same rate as thawing. Did you have any experience or problems with that? Because it affects the rates that you're estimating at the end of the...
You mean the speed of growing and freezing? Yeah, it can be different depending on the region that you're looking at. So the thawing can be really long and continue a really long time due to the fact that you have ice lenses in the ground and you have the latent heat that makes the thawing really long. And for the freezing, it's the thawing starts when you got the first diurnal positive variation, okay, positive temperature with the diurnal variation, and the thawing starts when you got the mean temperatures that start to be below 0 degree. So it depends of the temperature of the air.
So maybe the model that you use to fit may be too simple for...
Yeah, it's too simple. You need to do something else. I just use seasonal one here. Yeah,
thank you.
Yeah, thank you, Hugo. We have to move to the next. So next presentation. Thank you. Yeah, we're given by Sami again, and it's about adaptive multi-scale estimation of differential subsidence from INSA for improved hazard assessment. Please.
So sorry that I have two presentations in one session. So I'm very tired. I don't know about you. I hope you can tolerate this one also. So adaptive multi-scale estimation of differential subsidence over INSAR for improved hazard assessment. Hopefully today morning we see a couple of presentations, very nice presentations that exploit angular distortion, tilt, different kind of hazard assessment. So make it easier for me to directly jump to the problem. I asked AI to give me some statistics about the different papers in last years that focusing on subsidence area and the hazards and risks. This was the results about all the papers that use INSAR for subsidence monitoring. That, of course, all of them use displacement and velocity as a common metric. 20 to 40% use try to do something more than just velocity. Some hazard and risk assessments. around 50 to 35, that I think is overrated. My impression is smaller than that's 35%, but they use differential settlement and angular distortion as a metric, and very small number also go even more advanced methods to really specific to one structure or really higher order or curvature of each one structure. But more and more we see, I think the sign was today and also the posters yesterday, that we see more and more these results that based on INSAR we want to give some metric, a little bit more in the users community to use it for the structural engineers, for the civil engineers, that, for example, angular distortion or differential settlements and different metrics for that. If angular distortion or tilt is increasingly recognized as a primary hazard metric for infrastructure and buildings, how can it be estimated optimally from INSAR observations? I think there's a lot of studies and different ways to do it. Today morning we get a very good overview of how different ways we can estimate the same parameter. In general, as again today morning we saw, there are two different approaches. One is relative deformation approach. I call it point-to-point. Keep one point with the adjacent or neighboring pixels, somehow estimated relative deformation divided by length and come up with what is a differential settlement. Another way is a gradient-based approach. So we take derivatives of the formation field and somehow model the formation field as a continuous field and take a derivative of that, and that derivative, it's a tilt and it's a gradient and related to angular distortion. Is not exactly the same thing. I'm focusing more on this second approach here, but in the end, some comments on that one also. Some general background, estimation of a strain and gradients in general, also in the tectonics and the force of science from geodetic data. It needs some sort of interpolation, perhaps not explicitly sometimes, but implicitly we always do some sort of interpolation to estimate the gradient, and makes sense because if we want to take a derivative of a continuous function, we should, the definition of that is the fitting a surface or line to that and see what is the slope. That's the definition of derivative, and so we should somehow have interpolation field and then fit some basis function to that, usually linear. So in one dimension just a line, but in 2 dimension a plane. So this is a schematic example in 1 dimension in space, and assume we have a deformation field. Then most of the methods somehow they have some neighborhood area, some window, and then in that window estimate a line, and the slope of that line is a derivative. It is 2 things are important. What is the base function that you use to fit? It can be more complex than linear also, but usually we use just linear fit in the local around the point, and the window size. So important thing is the assumption that base function that we use should be really represent the behavior of the deformation field in that window size that we use. Or in 2 dimension, I told you we can estimate the plane and then derivative with respect to x and y, give the gradients or tilt. The true deformation field must be well represented by the chosen basis function within the interpolation window. These 2 base function and interpolation window are come together. I mean, in that window, this should be the same, should be valid. This is a very simple example. Of course, when you have a very smooth deformation and then you put a window, in most of the windows you see, the linear assumption is valid. So in all of these windows, of course, the full deformation is not linear, but in each window you can simply estimate a line and then take a derivative and compute it. But if you have a very complicated deformation with respect to the window size that you use, of course, when you then the line that you estimate is not really representative of the strain or of the derivative in that window. This has a problem when you have working on the multi-scale deformation field. So you have a small faults, big faults. You have then in subsidence, small subsidence due to the buildings, local infrastructure, large regional subsidence all together. And then if you just use one window size everywhere, sometimes you underestimate the gradient or the risk. The whole idea is if you have a really multi-scale subsidence field, how we can then do it adaptively. So the idea of this adaptive window sizes start with an initial window size quite big, perform hypothesis testing on the base function validity. It means we estimate the line or plane or any other base functions, but we take the stochastic parameters about the noise, and we do some hypothesis testing, some misfit testing, that if this function in that window is valid or not. If not, we make that window smaller. It can be like quad-tree decomposition, really make the window divided by 2. But in my code, for example, I put the scaling, for example, 90% small. I mean, if I start with 100 meter, then next time I go with 90 meter. Slightly reduce the window size. Some mathematics, the general is if you are in the window, you have different points, you have all your measurements. You have 3 unknowns, the 2 of them are derivatives, is the estimation of the plane, and then you have this design matrix. Simply you put it in the least square framework, but we use the variance covariance matrix of the noise. This is an important issue in this method. It is all depends on, you should somehow estimate the noise parameters. You need a good stochastic model, good statistical model for local areas, because these windows are local. So the stochastic model should be good representative of the noise variations in the local areas that you use. And then you have this general misfit measure or test statistics, overall model test that it follow chi-square distribution, and we can do the testing. QI, the variance covariance one, is important. It captures the noise variability. It's nice because it allows the error propagation. So when we finally estimate derivatives, we also have uncertainty of that. Differentiate between gradient of the noise and the signal. That's a good thing, because if you don't put it there, we can have a correlated noise in a space, for example, due to atmosphere, and then we estimate the gradient of the atmosphere. But if we can model atmosphere under a stochastic model, our estimation is more sensitive to real signal of the formation. It is but demanding. We should pay a price if we want to do this. We should somehow estimate it from external sources or from the data itself. I will explain later. Let's look at very simple simulation. I try to somehow simulate multi-scale deformation. So here we have a couple of persistent scatters that they don't have, if you see around them, they don't have that much points. So around them, they have a high gradient of deformation, but very, very local. Then we have this regional scale deformation that is very smooth in the large area. And then here also we have some linear infrastructure, for example, like tunneling, and then very small deformation. So if we estimate just with the fixed window size, this is the true gradient. This is because of the model, so I know what is the real gradient of the in these points. This is the real gradient in the microstrain. If you don't know how to interpret microstrain, it is 10 to the power of -6. It means millimeter per kilometer. So microstrain, if 1 microstrain, it means in 1 kilometer you have 1 millimeter deformation. So this is, I call it microstrain. It is. Okay, it should be animation, but now the picture. Anyway, so. With the fixed window size of 200 meter by 200 meter, the true gradient is that one. What we estimate is this one. We see in the large regional estimate, we underestimate, in total, everywhere we underestimate. The window is too large to capture the really gradient of the formation. If you go very small window size, 50 by 50 meter, we very well capture this linear infrastructure, but we are very sensitive to noise, atmosphere, and scattering noise that we have. Actually, we estimate the tilt of the noise instead of estimate the tilt of the deformation, because the window is very small and we are very sensitive to noise. The number of observations in the window is smaller. So we should go somewhere in between. We need an adaptive approach. So when it is needed, get the window smaller, and if it's not, go bigger. So this is based on this iterative hypothesis testing approach. It gives better results. It's still some underestimation, and we miss some points. We miss these 3 points. They are not there. Why they are not there? Because it keep estimation and make this window smaller, but at the end we never get a good fit. Always the test is rejected. He said, I cannot explain this point by fitting the line. So in the final results we don't see that. But this is a good thing, because for those points that this test, even in the very small window, is rejected, at least we know this indication of something could happen there, but we cannot precisely and reliably estimate the angular distortion or gradient. This is also some byproducts from that. For example, the window size or the number of iterations. For example, in some areas you see there are 14 iterations, so it makes the windows smaller to then finally get a fit at some point. And for some points also, you see, for example, for those three points that we don't have any point around them, at some point it reached to the a small window that there is no observation in it, just one single point, so you cannot estimate the tilt. Of course, you can estimate angular distortion based on this approach that get the neighboring pixels and subtract and have angular distortion, but based on this gradient approach, we cannot estimate it. Let's look at some real case studies. This is Tehran, my home city. It is very affected by very large subsidence because of the water extraction. It is average over 10 years, something around 50 centimeters per year, but it was much, actually more than 80, but it is close to 18 centimeters per year, and some years even more. This is a general deformation there, but I want to show you in the city for monitoring 2 of the metro lines. I have a project that you use PSINSAR for monitoring a buffer around these two metro lines that they were constructing there. And for that, I make a buffer. I show you the results in this yellow buffer. We make for whole metro lines different small buffers, and in buffer by buffer, we go to the details of the study. For these 3 buffers in the city, so of course the formation is much smaller. It is around 20 millimeters per year in the city. It's not like the outside of the city, the formation is very large. This part that you see, this is actually the extension of that large deformation that slowly is reaching to the city. But we have here we have a metro lines. And you see, here you can see by eye, we have some deformation around it. But there are also other deformation here, some regional subsidence here. There are some big things here. Here, first with a fixed size of 200 meters, I estimate the gradient or tilt. It is, you see there, again, it is a microstrain. It is quite smooth. If I go for a smaller window size, 50 meters, I very precisely, around the metro line, I see a lot of tilts, but I get also a lot of sort of noise. This is what we expected. So when the window size is very smaller, you are sensitive to noise. You get the correct gradients when you have a high gradient deformation, but also you get a lot of noise. And also in the north and east components of the gradients, you clearly see all these crazy patterns, ups and downs, green and blue. That is just the effect of the small window size that you have. This is using this iterative approach of making the smaller window size only when it is necessary. In these areas, if you consider noise that you expect from INSAR, we do it based on some variogram modeling in the far field, in the location north of Tehran in this study that is not affected by subsidence and other deformation. And based on that, we estimate the noise, we put in the covariance matrix. So this, accounting for that, in these areas, with very large window, it can estimate, so it's not that much sensitive to noise. But in this area, the system understands that, okay, here we have a big signal, the test is rejected. You make the window smaller and smaller and smaller, and then you get high gradients where you need it, and not that much sensitive to the noise. And also in the north and east component of the tilt, also you see much more clean results, And also it's highlighted the areas that you have the formation. These lines are exactly in the line of the metro and constructions. Couple of big sinkholes happen in this area that we estimate the gradients in the last couple of years. So it is really highlight the risky areas, but still needs validation. It is really recent results on this gradient estimations. When you zoom in, you see a lot of patterns and there's more validation. Some points on these missing points that I already discussed. For these ones, at least we know that something happened here, so then we can perhaps go with this point-wise approach for gradient estimation we see today morning, and then we have some indication of tilt, but this is, again, AI generated. I have idea that I want to discuss yesterday. I didn't have time to make a slide. I just explain what I want to say to AI and ask him to make a visualization for me. Not bad, so I'm not very happy with that. Still, there are something that I don't like it, but it gives a general idea. If we have one single point from one building, it can have a uniform settlement, or it can, with the same amount of the formation, it can really have an angular distortion on the building. When we take this single building, single point observation, and get another point far away, not far away, adjacent pixels on the street, and then because of resolution, and then we compute differential settlement, in both scenarios, we get same number as an angular distortion. But in this scenario, we don't have angular distortion. In this scenario, we have angular distortion. So this is general message. We should be a little bit careful when we estimate these parameters from INSAR, especially with low resolution data. When we have high resolution, tens of pixels, persistent scattering is one structure, that's another story. On the structure, you can really estimate the tilt. But when you have 1 point on one building, then, of course, based on these methodologies that we see today, or in this methodology, you can somehow have it, but I would call it differential settlement. That's it. Not anything more than differential settlement. When we call angular distortion, civil engineers, structural engineers understand it differently. Angular distortion for them is a distortion of the building. But differential settlement doesn't mean necessarily angular distortion. So I think in the community, more and more we see angular distortion. It's a good measure, but I think we should really be careful about the interpretation of that. The angular distortion is estimated from INSAR is not necessarily angular distortion that civil engineers understand. This was my final remark and general conclusions. This adaptive multi-scale estimation enables more optimal differential settlement mapping from INSAR. It is error-aware processing. It means it can differentiate between signal and noise. It has a quality description, computationally efficient, and the point that I made about caution that we should have about interpretation of the angular distortion. Thank you.
Okay, thank you, Sami. One quick question. Yeah, Madi. Yeah.
Hi, Sami. Thank you for presentation. I would be careful regarding, because I mean, this angular distortion is not something that we have created. I mean, this has existed in civil engineering community for ages,
yes,
right? So therefore, I mean, we shouldn't say that, okay, if we, I mean, now we have some things that, okay, we can estimate, but maybe not at the building level.
That was my point. So we should not just generalize it, because we can take 1 point and estimating differential settlement and divide it by the distance and call it angular distortion. But with low resolution, it's not angular distortion necessarily.
But it's the same concept for them. So actually, it's a very valuable.
Yeah, it is valuable, but it's not angular distortion. That's my point. In this picture, I think my point was you can have the same number without angular distortion. If you have one persistent scatters on this building doesn't have any angular distortion. But it has subsidence. If you have with C-band, we don't get that much point around it on the building. Another point is here, here. And then this building, with respect, this picture, I said I'm not happy with that because it showed the surrounding area is subsiding also. I assume the surrounding area is stable, but the building is going down. Then you estimate the differential settlement. That is correct. This is differential settlement. But if you divide it by length and call it angular distortion is not angular distortion because the building is not really, there is no distortion on the building. There is no strain, there is no stress. But if you have this situation with the same numbers, you have angular distortion. This is actually my point, that with low resolution INSAR, when we interpreting the these metrics that we do it, and it is very interesting. I'm also, if you see my poster, I use for all angular distortion, I call it, but I'm criticizing that approach myself because this is not necessarily angular distortion, and it can be sometimes confusing. If you have the auxiliary civil engineering tilt meter and the building, they say, oh, we don't see any angular distortion, but INSAR show angular distortion. Why? It can be problematic for end users. So I said we can call it, but it's not that much simple to get with low resolution INSAR just one point and take a difference and divide it by length and say it is angular distortion. The best thing is we call it differential settlement. That makes sense.
Okay, we'll take one last comment and then we'll come back to that, I guess.
Yes, so it's a great discussion. We have to be clear about the terms what we use. So the civil engineers, but I'm asking, I guess, the question to everybody here. The civil engineers I talk to, they talk about differential settlement, but even tilt, which is not really bad. Yep. They call it differential settlement. Is it correct? So then, okay, so we should really be very clear if we have enough data to talk about angular distortion and then use it.
Yeah, that is all my point, actually. All my point that is we should call it tilt, we should call it differential settlements, and these are all useful. But if we want to go one step further and call it angular distortion, we need to do something. We need either high resolution or we need some assumptions, especially with low resolution with C-band, that you don't have couple of pixels or persistence as over one structure. You have just one measurements, and it's not necessarily angular distortion.
Okay, so yeah, I guess we need to move to the next speaker. I don't know where she is. Yeah. Okay. So this is Molly Zepker, talking about coherence analysis and displacement time series in the Cascadia, constrained by L-band NISAR.
All right, well, thanks for sticking around. We're going to look at some NISAR data now, so switch up the topic a little bit. And we're going to look at NISAR's application or promise in vegetated regions like Cascadia. So this is work done at Scripps, but in collaboration with the NISAR science team. So first, a little background on the Cascadia subduction zone. It's a 1,200 kilometers convergent plate boundary that stretches from Northern California here up towards southern British Columbia. And this area is capable of producing megathrust earthquakes, so think magnitude 8 to 9. And paleoseismic studies in this area have indicated about 18 of these great quakes in the last 10,000 years, with a recurrence time of several hundred years. So Cascadia poses this huge hazard, so it is heavily monitored with onshore and offshore sensors like these GPS stations and seismic stations in cyan and amber. These stations are great, but they don't provide super dense spatial coverage, and that's where we would really like to use INSAR to shine. So there has been some work done with the Sentinel data in this region to look at slow slip events, but the C-band data typically decorrelate, so it's harder to look at some of these long-term tectonic signals that we might want to study to better understand this subduction zone. So we're going to look at a few stacks of NISAR data here. So we're going to start in southern Cascadia near the Mendocino Triple Junction, which has hosted lots of these earthquakes in the past few decades. And these are smaller stacks right now with this descending pass with 3 RSLCs, this ascending with 4 RSLCs, and we're going to compare a couple of the interferograms to some Sentinel C-band interferograms that we can produce. And then we'll go to this deeper stack up north here. So all the data that we processed, we started from the RSLC NISAR product, and we used GMT-SAR to do our alignment with a geometric alignment using the orbits, and then further cross-correlation. We use 60-meter pixel spacing, and we filter with a Gaussian wavelength of 160 meters. So just a quick overview, just to remind everyone, the differences between Sentinel-1 and NISAR. Sentinel is a C-band instrument, so a 6-centimeter wavelength, so the radar echoes will mostly return from vegetation and small branches. NISAR has about a 4 times longer wavelength at 24 centimeters, so it better penetrates through the vegetation canopy to the thicker branches and tree trunks. So these aspects of these systems have opposite pros and cons. So the Sentinel data typically decorrelate quickly in vegetated regions, but they're less susceptible to ionospheric phase delays. And the opposite in NISAR, L-band should maintain coherence in these vegetated regions, but it is more susceptible to ionospheric phase delays. So let's first do a coherence analysis between Sentinel-1 and NISAR. So this is a 24-day inepharogram taken from late October to late November. And you can see the Sentinel coherence is pretty decorrelated along the coast where there's that thick vegetation, but there are some areas of the image where it maintains some higher coherence where the ground is exposed or it's more built up. NISAR has a higher overall coherence across the scene. These are the average coherences. If you take the same exact pixels in both scenes, it's about the same average too. So when we look at the phase of this inepharogram, you can see that both NISAR and Sentinel maintain this coherent phase across the inepharograms, and the signal that you're mostly seeing in the Sentinel is due to troposphere, and the signal we're seeing in NISAR is due to that ionosphere, as expected. So now, if we look at an inepharogram that spans 72 days, you can see the Sentinel, again, pretty decorrelated, basically completely near the coast, some areas built up. NISAR also pretty decorrelated. These are the average coherences across the scene. But this time when we look at the phase, you can see that indeed Sentinel has decorrelated along the coast, though it is maintaining some coherent phase in more inland, away from the coast. NISAR, on the other hand, as anticipated, has this nice smooth spatial coherent phase across the inepharogram. Again, ionosphere here. So what we've seen from this quick example, not an extensive coherence analysis, but we have reconfirmed our thoughts that the NISAR data will maintain coherence longer in these vegetated regions. So next we're going to go to this deeper stack of 11 RSLCs at the top here. Seattle is, I think, right above or right at the top of our scene, just to orient everyone. And we have 11 RSLCs, so we can form 55 inepharograms, and these are the correlations of all 55 inepharograms. So here, blue and purple is low coherence, and the yellow or oranges are high coherence. So one thing you will notice is that only a few of these inepharograms have pretty high coherence across the scene. If you look at the ice products, they tend to have slightly higher coherence. So we hypothesize that the slightly lower coherence than expected is due to slight misalignment using our GMTSAR software. So we're still working on tweaking that moving forward. But if we look at all the inepharograms, you can see that they look pretty nice. You can make out tons of fringes due to ionosphere. So you can see some days are more flat, and some days you might have 14 fringes of ionosphere going across the scene. So this is just a visual that even at these kinds of latitudes, ionosphere really is the largest noise source that we're going to deal with in these data. So when we unwrap all the scenes, you can see now the scale bar is -30 to 30 radians. So we do still have these large phase ramps going across, so we have to do something about that. So Conveniently, or rather on purpose, NISAR was designed with 2 frequency bands, a main band typically at 20 or to make 40 megahertz over solid Earth applications, and an additional sideband of 5 megahertz. So we can use these 2 frequencies to form interferograms at the high frequency, and at the low frequency. And we can find the phase difference between those 2 interferograms and then scale it by the frequencies. This ends up being about a factor of 11. And then what we do is we mask areas of low coherence, so coherence less than 0.1, to deal with some outliers. This is because if you have outliers in the data, they will be amplified by this scaling factor here. And then finally, I filter that ionosphere estimate with a 10-kilometer wavelength. And when we apply it to our data, we get interferograms that look like this. So again, notice the scale bar. This is from -10 to 10 radians now instead of -30 to 30. And you can see that most of these look much flatter. So there are exceptions with this one, which I believe actually looked pretty good before the ionosphere correction. And then a lot of these artifacts in the corners are due to low coherence areas that my masking did not fix very well. So now that we have 55 interferograms that have been, in theory, corrected for ionosphere, or as best as we can at the moment, we can compute our line-of-sight velocity over these 11 RSLCs, which ends up being about 4 months. And just to convince you that our ionosphere correction is doing something, I first computed the average velocity by stacking the 55 interferograms without correcting for ionosphere. And you can see this 150 centimeter a year phase ramp going across the scene. So if untreated, the signal does not simply just average out over time. So once we correct the ionosphere, you can see we've reduced that 150 centimeter a year ramp, though you do still see a little bit of a residual phase ramp across the scene, as well as some areas of decorrelation, mostly due to the volcanoes in the region. So still work to be done, but the ionosphere correction appears to be doing something. Okay, we've corrected our ionosphere. Our line-of-sight velocity estimate isn't perfect yet, but how good are these data? Are they performing as we think they are? So if we go back to our corrected unwrapped interferograms, one thing that we can do is a very simple metric is just taking the standard deviation of the phase across every interferogram, and I'm actually going to exclude this one. And when I take the standard deviation of all of our interferograms and then average that, we have about 2 radians of phase variance across the scene, which is about 3.7 centimeters. So for context, in Sentinel data, we typically have about 2 centimeters of this RMS, or standard deviation of phase. So with the ionosphere, or residual ionosphere in these interferograms, we're doing a little bit worse than that, but it is more or less expected. So just to get some more data for what our residuals are in our individual interferograms, these are the 2 NISAR stacks, or NISAR outlines in Southern Cascadia, in ascending up here, descending down here. This was from a previous talk I had done earlier on. So these ionosphere-corrected interferograms have some artifacts that have now been fixed, like this banding on the side, and some of this these blobs here are outliers that I hadn't dealt with previously. But we can do the same exercise by computing the standard deviation in radians and finding the average standard deviation in centimeters. So for the ascending, we have about 3.4 centimeters, and then 2.5 in the descending. So in the 3 stacks of data that we have so far, we have anywhere from 2.5 to 3.7 centimeters of residual noise. So what does that level of noise mean for future time series, and will we be able to achieve something much better in the future? What we can do is we can use those noise levels and we can project that to a future time series. So what I've done is I have simulated a noisy displacement vector in blue, where I impose a standard deviation of 2 centimeters, and our true velocity for the simulation is 0. We can then estimate the velocity based off of our noisy vector, and then we can compute the misfit between our estimated velocity and our true velocity. So we can do that, say, 10,000 times or until convergence, and then we can compute the mean of all of those velocity residuals and then repeat that exercise for different time series lengths, 1 to 6 years, as well as different levels of noise. So making a simulated displacement time series with 2 to 4 centimeters standard deviation. So the results of those tests can be summarized in this plot right here, where we have the number of acquisitions on the x-axis, and for NISAR, there are about 30 acquisitions in a year. So this is from 1 year out to 3 or 6 years. 6 years. This is the average velocity residual on the y-axis, and then the colored curves are different noise levels. So one of the project goals is to hit a 2 millimeter a year accuracy for our displacement time series. So for these different levels of noise, you can see it takes anywhere from 4 to 5 years to hit that goal. So one thing I'll note is that the official NISAR lifetime is 3 years. But what I want you to take away from this, and maybe this is already well known, but this is just a visual, we want longer and longer time series to do more accurate science. And that's part of the reason why Sentinel has been so successful and such a great data set for all of us. So just to go back to some of our initial data sets, we have that Seattle footprint up in the north, so we saw this line of sight velocity. And then for the stack in southern Cascadia, I only had 6 interferograms and I computed a line of sight velocity, and you can see that this velocity is on the order of 100, or it's probably more like 50 to 70 centimeters a year, and the stack that averaged more data has a much smaller noise residual. So between this stack where you're averaging 55 interferograms and this one where you're averaging 6, we should have a factor of 7 improvement, but I think between these two line of sight velocities, it's closer to about a factor of 10. So the early takeaways, NISAR does indeed maintain coherence longer in these vegetated regions, and we do see the higher phase quality in these areas. So if we are getting more data in these vegetated areas, there's lots of new science and applications that we can now look at, which were previously we were unable to study. So according to that noise simulation exercise, we need about 4 to 5 years of data to reduce our current level of noise to hit that project goal. But I do think as we get more and more data, we refine our ionosphere correction algorithms and we get a little clever with the data, we can meet that much earlier. So the ongoing work, at least for the GMT-SAR workflow, is refining perhaps a secondary alignment, to correct better for these ionosphere effects. It might help with the registration to boost our coherence. which will be important in certain vegetated areas. And then we are also working on refining that ionosphere correction with better outlier removal techniques and filtering and masking across the scene. But all in all, NISAR is an exciting data set, and I look forward to seeing many new science applications from this whole community. Thank you.
Thank you, Molly. We can have a few questions, please.
Hi, thanks for the talk. Yeah, you probably are anticipating that question, but you mentioned that there's a lot of noise left over, but I would have still been interested in just seeing a general assessment, or maybe you looked at it, if that map you had from Northern Cascadia that was corrected from the ionosphere, if that matches the GPS velocities that you see, or might have been already good enough by chance, maybe.
Yeah, I have not done that yet because I saw the residual ramp and I just figured that was not correct, but that would be the obvious next thing. So maybe next week when I get home, that'll be my task. Thank you.
Thanks, yeah. And then from the time series, you only get that that reduction of the noise residuals in the way you simulate it if it's not correlated noise, right? But would you expect that the noise that is left over to be correlated enough to kind of hamper that noise reduction?
Potentially. I think there's some other things that we can do with the correlated noise to reduce that level, that, the 3.5 centimeters to begin with, so then that's smaller when you would actually feed it into that kind of simulation or compute your own SBAS or stacking time series. So harnessing that correlated noise, I think, is going to be key. Yeah.
Cool, thanks.
Yes, thank you very much. Very interesting work. I was wondering, so one way to deal with that, with ionosphere, is to try to mitigate it or to get rid of it. But in many cases, you could also work with an error signal as long as it is properly described in a stochastic sense, right? So if you would, for example, have a variogram of the typical ionosphere that you get in this region over the years or so, that would be able, you would be able to already make statements because you know the error bar. So I guess my question is, did you consider evaluating the variograms of the ionosphere and get some statistics on how the signal behaves?
So the answer is no. We have not done that yet. You can see, though, from, sorry, I'm going to go back a few. There is quite a distribution of levels of ionosphere across this one scene and even in the 4 months. But that would be interesting to look at it in a different, in a variogram, yeah.
Okay. One last question, please.
These are not the first L-band acquisition over there. We have the ALOS 2. Did you compare or did you try to see what's the difference between NISAR and ALOS 2?
I made 2 ALOS 2 ScanSAR interferograms, and I tried to correct for the ionosphere by doing split spectrum, but the bandwidth isn't quite large enough to do that successfully. So I ended up just removing a ramp in the ALOS, and then I decided it was apples and oranges, so it wasn't quite a fair comparison to look at a whole stack of the ALOS 2. But that would be a good addition to a future project, actually computing more accurate time series.
Okay, thanks again, Molly, for your presentation, and also the other 3 presenters for this session. I think it's time that we end this session and move to the roundtable session. So we do have some questions. I also invite all the other chairs for the displacement and deformation to come to the podium, please. No, not this one. I think it was for yesterday, I think. This one is for the yesterday. No, not this one. I think that we uploaded.
So you can sit.
I don't know. You
I
stand.
stand. It's good as a change.
I don't have a slide for the seat questions.
Yeah.
We just take them on the fly. You take it?
Yeah, this one. How we can get started?
Too many chairmen. I think too many chairmen. Too few chairs for the chairman.
We don't have enough microphones and chairs, so I don't know.
Yeah, we prepare, let's say, the 6 points. There are 5 we already clarified. So you see we have some keywords that also wait for your, let's say, comment recommendation, especially to ESA. And you can see actually for this kind of point already being discussed for the past 3 days, and especially for our displacement and also deformation session. Please raise your voice. If you have any comments, suggestions, let us know. Also raise up your hand, please.
So to help, there are a few key points, and there is one about EGMS. We saw several talks about that, so we would like to have your feedback about how you use this data. If you use them just for validation, or at which scale you use them, just for local scale, or maybe you try to look at that at other wavelengths, spatial wavelengths. So just speak up. Yeah.
So for most of the morning, I think both of the 2 sessions in the morning, like half of the questions were about geolocalization or like persistent scatterer location accuracies. In general, I was just wondering because I think yesterday we had a presentation in one of the 2 halls about Sentinel-1 geolocation accuracies, but I don't really know, like as far as I've looked in the literature, which is not very deep, the geolocation accuracy of all the different sensors to me are relatively unknown. Especially, I haven't seen it discussed so much in the presentations today outside of the questions. And I feel like it's very relevant to know because many of the applications that we then went into were done on building scale. But to my knowledge, there have been cases with different sensors where the geolocation accuracy can even be much more than a single pixel level. So 20 meters on a 3 meter resolution pixel. I just wanted to reiterate that as I've looked at it in my work, the higher resolution you go, the more this becomes an issue or a topic to talk about. And any level of quantification on that anybody already knows, they are welcome to tell me about, because I've looked a little bit into this and I think it's a little bit of a gray area for me as I've looked into it. Thank you.
To continue on this PS geolocalization, about 10 years ago already, at least that's the earliest I know, efforts have been made to combine INSAR points with point clouds. And most countries in Europe now have a national point cloud data set. And linking them is actually relatively easy. And from that, you can actually find, well, let's say the closest point, taking account the different coordinate systems, right? Radar versus the XYZ of the point cloud. And you can link them and then directly assess your error. And you can directly see that it's not homogeneous as it's published in ATBDs, right? So to me, this is largely solved as long as you have a point cloud, right? I think this is a good way to go, at least for a first step. And I'm kind of surprised that this has not been included already, because the method is there. I don't know. you can apply it to a whole country on a simple laptop within an hour for EGMS. So I don't know why.
Another comment about EGMS, or maybe just the fact, for example, it could make a transition, the fact that it's in East-West component, for example, we saw many things about decomposition. So would you have any comment about some evolution to have on that?
So for EGMS, I use it mostly for the validation, but the problem is that it's not updated very fast. So I think it was last month that we got the new updates about EGMS that was updated until the end of 2024, I suppose. But if it can be some procedure that speeds up the process of the let's say updates of EGMS, it's really much better. And also I have another comment. I'm from Lund University in Sweden, and somehow some parts of Sweden is at the same latitude to Denmark. So in Denmark I don't see this problem, but once you go to Sweden in order to just analyze the time series of deformation for 3 months of the year, exactly for the winter season, all of the images are masked out. So basically you don't have any information, and we don't have that much of snow at that time of the year in at least southern part of Sweden. So it's something maybe that can be considered in order to increase the frequency of the observations in some countries as well.
Oh, just on top of that point as well, one of the things that could be really helpful as recommendation for EGMS going forward is to, provide all the uncertainties. They don't provide all the uncertainties, so it's hard to do our time-dependent models and know how well they're being constrained. So you get an RMSE on the velocity, but not the individual time steps uncertainties. Particularly important when we're going to higher, with this bigger vision, if you might be aware of, a global ground motion service. When you're moving to higher straining areas, those time-dependent uncertainties become much more important.
Maybe I can react to your comment. Of course, you're right, quality information is very crucial, but maybe moving a little bit to the second point, what we saw in our session is that several authors did not just trust the standard deviation or a measure, but for example, you have a time series, but then you also look at a couple of normal differential interferograms. And this clearly shows you if you strongly underestimate the velocities, for example. Or you know that in an agricultural area or in a grassland, phase closure may be an issue. So you run tests with different stacks to see that your solution stabilizes if you include a certain duration into the averaging or time series derivation. So not necessarily high-level mathematical numbers, but just simple qualitative, quantitative checks which give you a good confidence, and not just you, but I think it's good to provide such measures also to the customer, to the user. So he also gets confidence if he sees that, for example, you have ascending and descending, so integrating it in components is nice, but not integrating it is also nice. You have two independent observations, and they show a similar result. They confirm a pattern of a landslide, for example. So low-level confidence information is also, I think, very crucial.
Can I just add a bit more to that? I think for you and I in academics, we can do that and we understand how to do that and what it all means. But as a national agency, we see others using INSAR who are not necessarily experts, so government departments, or even in the insurance sector in the UK uses it, without necessarily understanding what it means. And this is where my concerns are, actually, where the non-expert users just trusting the information. And so, yes, I agree, there's quality measures need to be there, but how do we simplify it enough so that a non-expert understands is, I think, the point.
Perhaps I can add to that. I'm very happy that you say that, Iqbal. I deliberately put beyond just error bars there, because it is something, if you want really some quality measure that it is successful, there are a couple of things these last couple of days I discussed with different people. One is it should be universal with respect to different methodologies. The most simple one is error bar. Error bar is something that we can have 10 different methodology, but finally at the end, somehow with some kind of estimate, they put error. The metric is the same, the methodology is different. But when, for example, if you go to phase closure is something particular just for some specific methodology. For example, in PS INSAR, we don't have phase closure. So very useful, but we should somehow translate on this information as some universal about all different methodologies that for end users is okay. Like error bars, for example, if you want to quantify the success rate of the ambiguity resolution or unwrapping. All methodologies do unwrapping, either in a space or time, in a space-time. At the end, we need some quality measure that it is universal. Of course, in different methodology, we assess it differently. But at the end, it's the same thing. And this is missing. We as experts, sometimes all of us, we see the map, we see the time series, and immediately say, oh, this is unwrapping error. End user don't have that insight, and they don't care actually. They just want some quality measure that they say they can rely on this information or not. And we have different metrics for different methodologies in very advanced scientific, but we don't have something that it is accepted and it's a standards in the community. And I think it's my idea. It can be recommended to ESA. ESA as an agency can promote that, can bring people together and come up with somehow. We should start from somewhere. It's complicated. We have different methodology, different assumptions, but come up with some common quality measures, not only for dispersion and error bars, reliability, unwrapping errors, geolocalization, different kind of things. So if other people have same idea, if you support this, it's perhaps too good that we can add it to the, and if you disagree with me, also say that we know that it's not supported by whole community.
Yes, error bar are important, but also we may want to know what is the smoothing of the result, the temporal smoothing of the time series. More importantly, if we want to look at transient deformations, there is a difference between the time series measurement and the time series models.
Thank you. Maybe to push back a little bit for the sake of the discussion. I don't think that we can go to quality description at these advanced levels, actually. I think from the perspective of ESA, the quality description on what the data actually are basically the SLC data, the real and imaginary parts, if you would like to see it like that, that's important. That's something that ESA should deliver. But it depends so much on what kind of application you have, whether you're looking, we saw examples, people looking at a tunnel or a bridge and looking at the whole of Cascadia, and so all these kind of products, information products stemming from INSAR have their own qualities, and sometimes it's a velocity and sometimes it's something else. So I think it's a dead end if we're going to give the task to ESA to come up with something that is good for all of us, because we're not going to find it, right? I think we have to acknowledge that with the same data, you can make thousands of different products depending on what your application is. And if you know what your application is, then you can decide whether a certain product is optimal. You can talk about quality, but if you don't know who's going to do what with your product, in my opinion, quality is not defined. So I think instead of kind of moving upward the ladder and trying to get metrics, quality metrics to advanced products, I think we should leave that to the experts who are working with the data, and then you get the skills and the data together. So that would be my contribution. Thank you.
I can go in the same direction, actually. Actually, in France, we did this exercise to systematically compare eGMS with some sort of post-processed flat sim products, for example. And I think this exercise is really interesting, and maybe we just can also encourage people to cross-compare data, because, as you said, depending on what you want to see, what you would to look at, it's very important to know up to where you can push the use of eGMS. And on the contrary, when you have SBAS solution, how high frequency things you can try to extract from your data sets. So in fact, you learn more than from this comparison than just using one and forgetting about the others. So, okay.
Well, for eGMS, there is a validation done specifically for typical applications and things that you can do and observe with eGMS. So maybe it's a thing of making that more visible to other users, so people can know what the data can be used for and what it cannot be used for. And with respect to the quality description, I think it should be done together with the users and not leave it to the experts alone, because they don't understand always how users look at the data and interpret quality.
May I say my opinion? Because I think it's a spectrum of different products, in that some of them is very on the part of users, some of them like SLC's ESA, and then, for example, angular distortion on the user part, so, or even more advanced technical things on the user part. But I think in between there is something that it is really on the data side. For example, the decisions, again, I say we make about unwrapping. I know that unwrapping, it depends, we need assumptions about unwrapping, and these assumptions can come from the users, but this is the advanced methods that we use for unwrapping. I think none of us users can really quantify quality or come up with a quality measure of that. If there could be argument that we never can have a quality measure for unwrapping error. It is universal for different methods. That's argument that we can discuss, but I think we can do something about that to at least come up with some common metrics, like error bars that we do for dispersion, some common error bars for quality or reliability of unwrapping. Of course, there are some approximation technicalities. That's the reason it needs research. We don't have it now. We know what for our experience, all of us, we are experts. We know unwrapping. We look at the results and say, oh, I think here is unwrapping. It's more prone to unwrapping, but we don't have a metric that we can quantify that, and everyone can, as a standard, use it. These kind of metrics, I mean, of course, all different products that we come up with INSAR, I also agree that we shouldn't go for quality measure for all of that. But these kind of things, I think it is important. The question is, ESA should be involved or not. That's also, that is my question. Of course, as a research, the community should do these things, but still I think ESA as an organization that can lead this kind of research or invest a little bit on that, the same effort that he put on eGMS or this kind of products.
Just a comment, following up what both Ramona and Annalene said. I think it's not just a matter of quality, but also fit for purpose. And fit for purpose is maybe more important. That I think it's great that all of these people are using this data who maybe don't understand it, because that means that INSAR is becoming mainstream a bit more like GNSS and other technologies. But that also means then education. It also means that when we're delivering a product, that we're making it understandable and findable, but also documenting what it can and cannot do. And this is what we, of course, are also trying to do with EGMS and other products. But fit for purpose is really the key.
Hello. Thank you very much for this amazing conference. And I would like to make a suggestion. There are technologically active countries like Cyprus and Iceland, and we have a local infrastructure with GNSS stations, permanent stations, and corner reflectors which produce valuable data. Do you think about integrating this valuable data to EGMS in order to improve accuracy and quality of the data which provided via EGMS?
No, I think Michele can answer about this expansion of EGMS that we have. Yeah, I mean, at the Europe, they are discussing about expanding this EGMS to also other countries. But I mean, of course, it cannot be done globally at the first stage. But they are considering, you know, this expansion of this EGMS to other countries. Sorry, I didn't get the point. No, I understood that he wanted to include to expand EGMS to other regions. I'm telling that, I mean, there is a program. I mean, there is a recommendation for this, to expand it. But I mean, to the local infrastructures and all these things. So this needs high resolution data and all these things. So it's all now based on Sentinel-1.
Cyprus is part of EGMS, but the quality of the data, because it is at the edges of ETRF, it's not so high. So our suggestion is to provide data-related GNSS data.
No, as far as I know, there has been a sort of validation part for this EGMS, and it's documented. Whether, I mean, Cyprus is included or not, I don't know. But I mean, if you look into the report of EGMS, there has been a tremendous validation activity for different processes, landslide, subsidence, land cover, and all these things. And also there was some period that actually they were asking for feedback from users. So if you recognize some problems in your country, then please communicate this, and then they will consider these aspects.
Yeah, thank you. Thank you.
Hi, just to go back about the use of AGMS by non-experts, just to add some points. Well, I'm from the Spanish Geological Survey, and we are in some projects working with civil protection stakeholders that want to use INSAR data for preparedness and land planning and so on, but they don't know anything about INSAR. And one of the two aspects that we see that it's important to them to understand, one of them is that the absence of PS or points doesn't mean the absence of movement. Because sometimes when they saw the AGMS, they say, okay, here we don't have points, so this is stable. And also when you saw the AGMS to someone that doesn't know about it, the ramp scale, that it's now the default, it's plus 2 millimeters per year. So you are seeing, 20 millimeters per year. You are seeing like a lot of red spots, and they are sometimes scared. So maybe the default to be a bit wider. Thanks.
I just wanted to comment on the validation. I just looked at the validation report, and I know in the Netherlands we have lots of corner reflectors. With the presentation on Groningen, I know there are many, many out there. And I see in the validation report there were 6 corner reflectors used over mainland Europe, only 6. And I know every country has many, many corner reflectors, and it would be very, for a user, it would be great to look at EGMS and then also be able to switch back to the corner reflector that is in that country. And I know in the Netherlands we have tons of them, but there are none of them included in the validation report, which I think is weird. And I can say the same for other countries, but okay. But for a user, it would be great to see, hey, I see the corner reflector in there, in my view, and I see it matches the validation data that we also have superimposed on this, and we can directly see. Now there is a report with 6 corner reflectors in the validation report. I think that is a huge discrepancy and a huge potential as well. So, just putting it out there.
I can just comment on that. The validation exercise is a commercial contract done by a consortium who won a tender put out by EEA. So this is not something that is done by EGMS. It's a separate independent validation program. And it's, as I said, they put in a bid, they outline what they're going to do, and then against other bidders. And so this is not something that has to come out of the people who are making the validation. So.
I think it's very interesting discussion and comments. Actually, this is a follow-up comments for previous what mentioned for Cyprus and also for validation. I think it's good also for calibration to consider corner reflectors, because when we are talking about this PS geolocalization error, if some countries already have started, I mean, having good, well-established corner reflectors, maybe they can be integrated in the processing, and hopefully, I mean, they can improve this geolocalization error. So this can be also in the process of, I mean, calibration or tuning of the accuracy of the PS points. So beside validation, also that one. Thank you.
Excuse me, I think I would like to bring the discussion on, I think ESA expects us to come with some recommendations for them. They are not responsible for the EGMS service. So is there anything ESA can do concerning the problems we mentioned? I don't know, ionosphere was mentioned, there is an upcoming ROSEL mission. Is there anything we would want to ask ESA to do in preparation for that mission which could help us in our applications? Or we say geolocation is critical for infrastructure monitoring. Is there any annotation which could help us in this problem? So I think we should maybe try. I know we are already past the time, but do we have any recommendation for ESA? This is what the outcome of the round table is supposed to be. Ramon?
You do. Yeah. No, so I want to make an argument, and maybe people can think about it for the next couple of days. So we had a very interesting talk about ROSEL a couple of days ago. And Julia Kubanek there explained that there are different options how to time ROSEL together with Sentinel-1 Next Generation. And so one thing is to kind of densify the sampling. So we're now in a 6-day orbit with 2 satellites, and so you could go with ROSEL right in the middle, then you have better sampling. But the other option, and I think this is I would be in favor of that, is to do this what they call convoy. And the idea is that they fly ROSEL with a 1-minute difference than Sentinel-1 Next Generation. My argumentation, why I'm in favor of that, is that in terms of the temporal sampling, we're already going to make a step forward, because we're going to have 400-kilometer wide swath with Sentinel-1 Next Generation. So with different revisits, we're going to get many more sampling over time already. But I think that what we've seen also during this Fringe is that in many cases the problem is in the interpretation of the signal, right? So whether it's phase closure or how it presented the differences between L-band and C-band for the penetration, or ionosphere, all these kind of things. And if you would have a systematic setup where you would have within 1 minute C-band and L-band following up on each other, it would be an excellent way to kind of rule out a lot of these kind of particular explanations for the signal. So I would like to urge everybody to think about this, and of course this is way for the future, right? It's not for now, but I think it's a cool idea. And if we would have 1 minute differences between L-band and C-band looking at the same area, we're really going to learn what we're aiming for, right? Just to give you one example, how we're talking about PS geolocalization here, but this is basically, if you think about it as from the perspective of a corner reflector, it makes sense. You can touch the apex of the reflector. But in many cases, the things that we call PS are not necessarily touchable things, right? It's a virtual point, and it's repeatable over time, but it is not a point that we kind of pinpoint on a bridge. Okay, this is the third bolt from the left, right? So that is all related to the interpretation of the signal. So I would like to urge you to basically maybe discuss this among each other, and if we can make a strong plea to ESA to consider this very strongly, it could be a recommendation. Thank you.
Yeah, I mean, regarding to what Ramon mentioned, so maybe my question seems a bit strange, but I just wonder, can we ask ESA to also consider the needs of those users who require higher resolution data than like X-band? Because at the moment, for example, this higher resolution, I mean, has been in the hands of Germany, I mean, Italy. Now Italy, I mean, it was a good cooperation with Japan, that, okay. But for a lot of applications, especially, for example, when we go to civil engineering application and all these things, at the end, this higher resolution data is the ultimate solution. Can we, I don't know, can we hope that ESA one day enter into these things, because for Germany, I personally campaigned a lot, I failed. So up to now. And so do you think this makes sense at all to ask ESA to also consider some generation of the higher resolution X-band data in future? Or are we happy with C-band and L-band?
Maybe as a feedback to ESA, it is also important to state that what they do at the moment is really great. So we have long time series of consistent acquisitions, and most of the work shown this week here depends exactly on this type of data. So it's of course good to have good ideas, and we can do better if we have a second system. It can be like Ramon suggests, give additional opportunities if it is coordinated with the first system in a special way without giving up any of the systematic acquisition schedule. But we should really also ask ESA to continue in this way. So I think the role of not just ESA, but also JAXA and other agencies now, NISAR is also in this direction to have a really excellent background of a lot of data everywhere, including archives. So very often you have a process, and the first thing you're interested in is looking at the history. So there's a new landslide, and so what the user wants to know first, how was it 10 years ago, 20 years ago? Is it already there? Is it just getting a little bit faster, or was it already similar? So these archives are also extremely valuable, and at the moment the responsibility for this depends on the agencies, and ESA really takes a leading role with Sentinel, with the Copernicus programs, also the EC. So that's also very important. Of course, having new ideas is not a bad idea anyway. Yeah.
More comments? If not, I think thanks a lot for giving us this feedback and all suggestions, remarks. And I wish you have a good evening, and we see you tomorrow. Thank you.
I think that's an important point.
Who is going to do the...
Important to, of course, it's boring, but
it's to keep it up.
Yeah, it's the most important. No,
I am there.
He's here.
Are you? No, I am there for sure.
Do you want to make a...
Space? Are you also not there? Okay.
I think it's per session, not per...
Okay. I took notes of the discussion.
For all these, okay.
Is it one for all the four?
For these is a round table.
I thought we were supposed to present all the displacement sessions.
These for each.
I think that's what I understood.
So who is there on Friday? I am there on Friday. So 1, 2?
I am there.